Hi everyone and welcome back to PrepFusion. I'm back with another video. So in this video, this is the part 4 of control systems. So we have covered already. If you have not seen already, we covered part 1, part 2, like all the control systems, right? In around like 25 hours, 25 to 30 hours, we have covered the whole control system. Now, it is of course not a substitute of the full course. Full course is like around 100 to 110 hours. Of course I cannot explain every single thing in detail, right? Every small things I've gone in a fast pace. Like for maths and network theory, I was very slow. I explained every single thing, right? Of course there also I was fast, but I was kind of slow. But here I have went a bit fast because control is like a very high scoring subject, and most people have already studied a bit about this, right? So what I try to do, I try to bridge the gap, right, between a great student and between an average student, right? So I hope you have watched the previous part. You will realize like what kind of content we are teaching, like it is something else. Like uh why? So I can show you a few questions, right? So in state space there are many questions. Okay, of course I have told everything regarding state space, whatever are the important parts. And if I go into the solutions of the questions, so we have discussed like state space is not that difficult. The questions of state space will be pretty straightforward, and you will be able to solve it. If you just watch this video, you will be able to solve all these questions, right? Many questions has came in state space. But what happens in in controllers and compensators, right? If you see in controllers and compensators, there are a lot of questions. Okay, it is not just from the topic of controllers and compensators. Actually the thing is, it is a mixture. It mixes root locus, Nyquist plot, polar plot, phase margin, those topics, right? And basis of control system also, it is a mixture. So there are many questions, like you will see like the way that we have solved, right? You will not see that solution anywhere else. So I can show you a few questions like I believe, yeah, this, right? This is also, this is not the question. Yeah, this question is actually pretty great, right? Is this no not this question? This question is again okay, but there was one question I have forgotten. Hold on a second, let me find out that question. Where is that question? This one. Okay, just go and search the solution of this question. You'll never understand it, right? This is the PYQ solution, second question of controllers and compensators. Pause the video and try the solution if you have already studied it, right? If you go and see any PYQ book, you will not understand it, right? Just the way I have explained it, you'll understand every single thing. Okay, in a book these solutions will not be there properly, right? So I have taught you with intuition as well. You can see this question. I can show you this question, right? Where is that question? Like there are a lot of questions from controllers and compensators, because in gate IN, right, the weightage of controllers and compensators are very high because they focus on controllers and compensators. So if you see, uh, where is that question? This question is done. Yeah, this question, not this question, sorry. Where did it go? Yeah, this question, right? This question was a very good question in gate 2025, and even I asked with AIR1, who got rank AIR1, he was also not able to solve it. But actually this is not a very big question, right? The question solution is very elegant, but it will not use any normal standard formula. It will be something non-standard. So they like to ask, of course they will ask the standard questions as well, but in between they'll provide some non-standard questions, right? You will not be able to solve this question if you know all the formulas. No, you have to use bit of brain. You have to use bit of uh, like what do you call that, thinking ability, right? Instant thinking ability. So these are the things. I hope you watch the video, and of course if you do enjoy, if you are enjoying this R-PYQ series and anything else, if you want anything else, you can obviously comment down below. You can like the video, you can hype the video. That will help us to reach to more audience. That's the small request from my end, because we're providing so much of content to you guys. Okay, so with that we will start with the state space analysis. Let's start with state space analysis. So there are a few basic terms like state variables, state equations, state diagrams. So we'll understand them one by one. So yeah, what is state variable? So let me take a example. Mm, there are no real life examples here, right? Okay. So uh, let's say this is my capacitor and this is my resistor RC. Okay, and I'm providing it some input voltage Vi, and I'm measuring the output voltage VO. So your output actually is a function of a lot of things. It is not just a function of input. it is also a function of the state variables in the block. What is my state variable? Whichever element has the capability to store energy, that would be your state variable. State variable are present in the system which are responsible for changing the state of the system. So here, right, why it is a function of x? It is basically, in this case, our state variable is the capacitor. Capacitor can act as a state variable because it can change the state of the system. So if I'm providing it some input unit step, right, all of it will depend what is the initial value of my capacitor voltage. Was it 2 volt? Was it 1 volt? Was it 0 volt? Accordingly, my output also, voltage will also change. And capacitor has the capability, as it can store energy, right, it has the capability to modify the voltage waveform, correct? You know, if capacitor is present, the voltage waveform is like this, correct? So state variables are responsible for changing the state. So these are, so it all depends, right? Initially, let's say if it was 0 volt, then the output will be something else. If it was 2 volt, then the output would be something else. So state variables are those variables which are responsible for changing the state of the system. What is my system? This. Okay. Now state variables and state equations are not unique for a particular system. There can be, like, you can assume, I can assume my capacitor, like I can assume 1 by Cs to be state variable, someone else can assume Cs to be state variable, right? They are not unique, but ultimately what will happen, uh, for certain state variable, you will derive a state equation that involves the input and the output. Those are called as the state equations. So you will solve the state equations, ultimately you will arrive at the same answer for both the cases, right? Let's say I am Anish and this is Himanshu sir, correct? For both the cases, we assumed different state variables. I assumed Cs as state variable, 1 by Cs, and Himanshu sir assumed as Cs. It will not matter ultimately. It will not matter because ultimately, like, for this state variable, you will get some equation. For this also, you will get some equation. Ultimately, you will solve. I will show you the solution as well. But at the end, both of them will get the same answer. So that's why state variables are not unique, and this property is very, very important. This will be utilized everywhere else. Okay. State equation, it is a first order differential equation which relates the change of state variable with respect to the state variables and the input. So yeah, this is kind of a equation, right? First order differential equation is this, and it will relate the input and the change in the state variable. Okay. So here, right, what you can assume, what is your input? Input is Vi. What is your state variable? Maybe the capacitor. So how can I solve, how can I write a first order differential equation? So what I can do, I can assume a current, right, I. So Vi will be equals to I, hold on, voltage across the capacitor plus current across the resistor into R. So Vi equals to Vc. What is the current? This current is same as the capacitor current, which is C dVc by dt. C dVc by dt. So this is simple here. What is my state variable here? My state variable is Vc. So because I have written a first order differential equation in terms of Vc, so it becomes a state variable. Okay, so Vc, voltage of the capacitor, becomes a state variable here. Now why am I talking it is not unique? So this is my state equation. Vc is my state variable and this particular thing is my state equation. Why am I saying it is not unique? So you could have assumed something else as well, right? You could have assumed your IC to be your state variable, correct? That is also totally possible. So if my IC is state variable, then my minus Vi equals to Vc plus IC into R. So what will be your Vc? So I know Vc equal to C dVc by dt. Sorry, IC is equals to C dVc by dt, right? IC equals to C dVc by dt. So Vc would be equals to integration of IC dt, right? So this will be, so not minus plus Vi. So Vi will be equals to integration of IC dt, like Vc is 1 by C, also don't forget to do the 1 by C as well, plus IC into T, IC into R. But this is not a differential equation. So I have to actually differentiate both sides with respect to time. So this will become dVi by dt equals to IC by C plus R into DIC by dt, correct? So it gets converted into a state equation. So this is also a state equation. So as you can see, for this state variable, what is my state variable? IC is my state variable. I am getting this state equation. So state equation and state variable are not unique. State equation and state variable are not simply unique. Okay, that's what you can see. So for these two things, I'm getting different equations and different state variables. But ultimately, right, if you derive IC as a function of time, and here also if you derive VC as a function of time, uh, and after deriving IC, if you derive VC as a function of time in this equation, both of them will come out to be same. Okay, your final result will not change. So that is what my state equation, that is what my state variable. Now state diagram is nothing but the pictorial representation of the state equations. So here I have a state diagram, I guess. Yeah. Uh, Hold on a second. Let me show you. Yeah, what is the state equation here? They have not shown you the state equation. Okay. Let me write the state equation. This is my state matrix form. This is my state equation. Okay. So say state equations are sometimes put in matrix format. So these are not super important things, but it's good to know, right? I will move on from this point in a quick manner because these are not super important, but understanding the basics is always important, right? So state equations are sometimes written in terms of matrix format because there are multiple state variables in a system. So maximum number of state variables, maximum independent number of state variables in a system will be equals to the order of the system, basically the number of poles in the system. So maximum number of unique state variables, that is not unique, sorry, independent state variables, like one state variable is not dependent on the other state variable, will be equals to the order of the system. So here this is the first state equation. What is the equation? X1 dot x1 dot equals to x2 dot. Just give me 1 second now. Let me turn off the internet. This will be x2 dot equals to minus 2 x1. So I'm just solving the matrix. So you should be very good in matrix. So before starting state space, I will highly recommend, I hope you have watched the linear algebra video, right? You must watch the linear algebra, right? You must revise the linear algebra, otherwise you will be very weak in state space analysis. So x2 dot equals to minus 2 x1 minus 2 x2 minus x2 basically. Okay, x2 dot basically means like dot, right? X dot basically means dx upon dt, that's all, right? Dot means I'm differentiating it with respect to time. Okay, I forgot to tell you, that is it, right? So yeah, these are my state equations. Okay, don't forget you have input as well, right? So in the first row it is 0 times u. So in the first equation I don't have any u, but in the second row I have 1 times u, right? So second row should include u, so this will include u as well, right? Plus u. Okay, u of t. So everywhere I have bracket of t, I'm not writing it, right? I'm not writing it. Everywhere we have bracket of t. Now here, correct, here what we can do is, you can see, right? So x1 dot is equals to x2. So if I assume my x1 to be okay, so I should explain it like this. This will be better. So what was my equation? Let me write the equation. X1 dot is equals to x2, right? So first we started off from here. So x1 dot equals to x2, right? This is my equation. Actually, the thing is, if I take the Laplace transform of this equation, you have to consider the initial conditions as well, like the Laplace unilateral. So there are two kinds of Laplace transform. I think I have mentioned it. Have I mentioned it? No, I have not. Okay, great. I have not. So there are two kinds of Laplace transform. You will study this in signals and system. If I'm doing unilateral Laplace transform, that is from 0 to infinity, right? So you have to consider the initial condition as well. Okay. So actually it will not be exactly s into x1. That is what we have studied in the first chapter, in the first part of control, right? There we assumed that there was no initial condition of my state variable, but of course here we will not assume it. We will do it properly. If there is an initial condition of the state variable, then you will not be able to calculate the transfer function. So state space analysis is useful wherever you will not be able to calculate the transfer function, because classical method will be used everywhere whenever you are able to calculate the transfer function. But classical method fails whenever there are initial conditions in the system. And of course, capacitor will have some initial condition. Inductor will have some initial condition. So any system will have some initial condition. So your classical method actually fails. So we can modify our classical method to implement the initial condition with the help of state space analysis. Okay. Also, classical method is only valid for LTI system, and classical method is only valid for CISO system. Basically, CISO means single input, single output. Everywhere we have seen that I have a block diagram, I have a single input and a single output. It is not supported multiple input, multiple output. It does not support, but state space does support it. That's why state space, understanding state space is very, very important. So where was I? I was here. I was calculating the Laplace transform, right? So if I was calculating the Laplace transform, I will obviously this will be s into x1 of s, that is fine. Also there will be an initial condition. If let's say this was d square x1 of t, this anyways you will learn in Laplace, don't worry, you will learn this in Laplace. And then what will be the Laplace transform of this, right? Laplace transform of this will be s square into x1 of s, okay, minus s into x1 dot of 0, the value of the first derivative at t equals to 0, minus x1 of 0, the value of the function at t equals to 0. Okay. So I think no, it should not, this should be dot. I guess this will be dot. So how can you remember it? Basically, right, you remember that I cannot write s into x1 dot, because like that will you're already multiplying by s, also you are taking the differentiation. No, that is not possible. So you will only write this. That is how I remember. Okay, that is how in my brain I remember it. Already I am multiplying by s. This will not be a derivative. This will be a simple term. Okay. So what about for it like this? You will learn in Laplace in signal. Okay, don't worry. What about triple derivative? So for triple derivative, because this might be used in state space somewhere. So if I have triple derivative, right? So the Laplace transform would be s cube into x of s, that is fine, minus s into, as I have triple derivative, it will be not s, it will be s square into x of 0, then minus s into x dot of 0, then minus x double dot of 0. That's how the pattern is formed basically. Because I'm multiplying by s square, so I will not differentiate it, right? Here I'm multiplying by s, so I'll differentiate this once. Okay, because overall it was triple derivative, right? And here nothing is there, so I'll differentiate it twice. That's how the pattern is followed. That's how you can remember it. Okay, very important thing you have to remember. So you're actually Laplace transform x2, right? It is not only s into x1, it also includes the initial value of the state variable x1. So your what is your x2? Sorry. So yeah. So what is your so I can rewrite this equation, right? I can rewrite my x1 in terms of x2 and x1. So x1 would be equals to 1 by s into x1 plus x2, this, right? So that is what my x1 is. So x1 is addition of this and this, that's all. So x2 is s is already there, that's a node in the state diagram. So what I will do, I'll multiply a gain of 1 by s, so that at this node I'm getting x2 by s, and already this node already that the initial condition is considered. Okay, we will write x1, okay, in terms of x2. Now similarly you can write the same thing for x2 as well. So x2 equation was given to you, right? Okay, this is just one, yeah, equation was given. X2 is minus 2x1 minus 2x2 plus u of t, correct? So if we solve it, okay, I think, yeah, this is not the correct equation, or is it? Yes, this is the correct equation actually. Yeah. So what they have done, they have assumed a third state variable. Okay, so this is just a way to solve the state diagram. You don't need to understand all these things, just you need to understand how am I forming the state diagram. And don't worry, they will not ask you any questions from state diagram. They will very rarely ask you questions from state diagram. Just you need to understand what does this state diagram represents. So x2 dot, we have assumed it to be x3. Okay, so x2 dot is equals to x3. So I can again use the same Laplace transform. If I use the same Laplace transform, I can write that my x2 dot will be equals to, uh, if I use the same Laplace transform, I can say x2 of s will be equals to x2 of 0 plus x3 of s upon s, right? That is what I have done here, right? Same thing I have done. Okay, same whatever I have done here, same carbon copy I have done. Now, interestingly, my x3, right, x2 of t and x3 of t are same. X3 is nothing but this value, right? That is present over here. X3 is this value, right? Now, as soon as you have drawn this particular part, now you can replace your x3 with this relation. If I take the Laplace transform, right, here there is no derivative term. If there is no derivative term, then I can simply take the Laplace transform, no problems. This was done only to uh, discard the effect of derivative, that's all. So here, if I take the Laplace transform, simply this will be my equation, and I can see that my x3 of s is equals to this and this. So x3 of s is here, correct, which is equals to minus 2 into x1. So I will write a gain of minus 2 into x1. Then it is minus 1 into x2. So I will write a gain of minus 1 into x2, and plus into u, the input, right, plus 1 into u. So I have a plus 1 into u. So basically these are all incoming nodes, right? That's why you have to understand this is the effect and these are all the cause. So first you have to write properly the equations. So what did I do? Simply these were my two state equations, right? X1 dot equals to x2, x2 dot equals to this. So what I did, first I resolved this one, okay, and this was the state diagram. Then what I did, I don't like this thing, right? I don't like this thing, this equal to this. There is too much chaos. So what I did, I assumed another state variable. That is fine. You can assume another state variable. Later on, you can remove it. Later on, you can remove it. So x2 of t equals to x3 of t, and you can write your x2 in terms of x3. That is what I have done over here. And finally, you remove your x3. What is your x3? X3 is basically this value, right? I can take the Laplace transform because there are no derivative terms here. Very easy. So ultimately, you have written your x3, and that is your state diagram. So that's how you make your state diagram. That's it. We don't need to give this much time. This is the important part. Now, what is my state space representation? So I have told you already, this equation is called as the state equation, where I write the differential equation, basically the derivative of the state variable in terms of the state variable itself and the input. Okay, there can be multiple state variables. Now there is another equation that is known as the output equation. So output equation includes the state variable, that is normal, right? These are not derivative, just normal state variables and the input. Okay, so output will be a function of the normal state variable and the input, that's all. So this will be called as the output equation, and this will be called as the state equation. Okay, this will be called as the output equation and this will be called as the state equation, correct? So yeah, now I was just in something else. Yeah, now there are few things regarding order, right? So first of all, this this is called as my state, sorry, this is called as my state space representation. That's how I am representing the whole system, output, input, state variables. Now this state representation will be written in matrix format. This, right, is called as the state vector. Okay, why? Because it is a column vector, that's why it is called as the state vector. The order of it will be n cross n, n cross 1, sorry, not n cross 1. It will be a column vector, column matrix, where n will be the number of state variables, that's it. And this n defines the total number of memory variables in the system, initial values, order of the transform function, order of the differential equation. So these are all the definitions of n. I hope you can understand it basically, right? Because let's say I have two energy storing element LC. So the order would be 2 here. How many? So how many state variables? I have 2 because these two are my elements, right? That can store the energy, that can change the state. Okay, so that's how this comes. Next is the uh, this, right? Where is it? Where's the second one? Yeah, this x dot is nothing but the differentiation of the state vector. That's it. Okay, no, nothing fancy. Now your u is the input. Okay, now in up until now what we have been studying, we have been studying for single input, right? Only there was single input, but whenever we had multiple input, let's say I have an input here, all of us, and we had a disturbance, we solved a p/q, right? Where I had a block here, another adder here, and there was a disturbance d of s. How did I solve it? What I did, I made this to be 0, then I resolved the transfer function, then again this made this to be 0, then again I resolved the transfer function here, and then I simply used superposition. Because my system was LTI, I was able to do it. That was valid because my system was linear time invariant. But here we don't have that uh, we don't have that, what do you call, that boundary. We can have multiple inputs. So u will also be called as the input vector. It will also be a column matrix only. Okay, that's how this is u. So there can be multiple inputs. Let's say simultaneously I am providing step input, impulse input to the system. So there can be multiple inputs. That's why m is the number of input variables. Don't worry, slowly you will solve few questions. These things you don't have to remember. Okay, you don't have to remember. Automatically this will be in your head. What is y? Y is again the output variable. There can be multiple outputs. Up until now we have been studying that we are taking output only from one place. We can take output from multiple places, right? And find out the transfer function using the matrix equation. Okay, so yeah, 5 is the most important matrix. Okay, this is the most important matrix. This is called as the system matrix. By the name itself you understand, it discusses about the characteristics of my system. So this is the most important matrix. What is the order? It is a square matrix of n cross n, where n is the number of state variables in my system, or n, you can say, is the number of energy storing elements. Most important matrix. Okay, so there are many properties of this, right? Basically the eigenvalues of this matrix are actually my poles of my system. So there are multiple properties of system matrix, which of course we will use slowly. But for now, I hope you have got the idea, and this is the most important one. And this will be a square matrix. And B matrix is basically the matrix that relates the input and the state variables. If you remember, this equation you have to remember, right? What is the equation? State equation. X dot equals to A into X plus BU, and Y is equals to C into X plus DU. So this equation you have to remember. This is in matrix format. I am not writing it, but it is understood by you that it is in matrix format. So B is called as the input matrix. How can you find out the order? Like if this has a order of n cross 1, right? This has a order of n cross n. So what will be the order of the multiplication? It will be n cross 1, right? So what will be the order of this multiplication? N cross 1. So if U has a order of m cross 1, it is also a column vector. What must be the order of B? It has to be n cross m, right? Then only overall the multiplication order would be n cross 1. So that's how you can calculate these orders, correct? So yeah, that's all basically. That's all, right? Yep. So yep, that is the thing. Basically we are done. So that's how you can calculate the order. Similarly, you can also predict the order for C, because here what is the order? It is P cross 1, right? Number of outputs, where P is the number of outputs, and this is n cross 1, X is n cross 1. So C has to be P cross n. Then only overall the multiplication order would be P cross 1, right? Similarly here also you can derive order of U is m cross 1, and order of D has to be P cross m, right? All these things are basics, you can do it. So I hope I don't need to do. So the most common case is CISO, single input single output. Mostly this will be the case. Okay, 90% of the time your P will be 1, M will be 1, right? 99, I would say not 99, 95% of the time. 95% of the time your P will be 1, M will be 1. So you don't need to worry. So you can represent your variables like this. You can I have taken few examples, you can see. So that's how you represent the state space. Now how do I find out the solution? Solution meaning what is the y value, output, right? Solution of my state space equation. What is my y of t? That is basically my solution. So case 1, like there are multiple kinds of solution, because previously we never considered initial value, because transfer function we will not be able to calculate. Why? So let's take an example, right? Let's take this example that uh, my y of t is equals to 3 into input. Let's say directly I'm differentiating the input dx x of t by dt, correct? Now if let's say this x has a initial value, so if I take the inverse Laplace, this will be y of s, not inverse Laplace, sorry, Laplace transform 3x of s minus x of 0, because x has the initial condition now. Okay, let's say initially the value was 1. Okay, let's say x of 0 is 1, at t equal to 0 it is 1. So what is the transfer function? Transfer function is y of s upon x of s. So here this will be y of s equals to 3 x of s minus 3. Can I calculate y of s upon x of s? You cannot. That is the beauty, right? If you have initial conditions, this becomes a non-linear equation. Non-linear equation. If it's a non-linear equation, you will not be able to solve it. So that's why we never use transfer function method in these kind of cases whenever I have some initial conditions, right? So we first of all will calculate the solution whenever the input is 0. Basically u of t, the input is 0, but the state variables have some initial energy between them. So due to that, what is the response or output? So this kind of response is called as zero input response, ZIR. When my input is 0, I am not providing any input. Like here I have a capacitor, here I have a resistor. So I can either provide input here this side, step input, or this capacitor can have a voltage, initial voltage across it, right? Let's say 2 volt. So I am not providing an input, this is shorted. So what will be the response with no input? So that's why it is called as zero input response, also called as natural response. So if I don't disturb the system, what will be the natural response? So this is also called as a natural response, okay? Zero input response. So this response is due to the initial value, okay? And forced response is called as the response due to the input. I'm providing input. This is called as zero state response. Basically the state variables, initial values of all the state variables are 0. That's why it is called as zero state response, right? So this is the example, same example I have taken, right? So this is the natural response, and if I'm providing it some step input, this is the forced response, okay? So if you measure the output, output will vary. So these are the solutions. This already we have discussed, like Laplace transform already we have discussed. So what will be the solution if I have this case, right, where my input is 0? So if I take the, if my input is 0, right, so my x dot of t will be equals to a into xt, and y dot of yt will be equals to c into xt, right? So what is my xt? So what I can do is I can take the Laplace transform here. This will be x of s, because my initial conditions are not 0, right? So minus x of 0 equals to a into x of s, correct? So from this I can directly say what is my x of s. X of s will be equals to x of s into s minus, now remember all these are matrix, right? All these are matrix actually, okay? So if I'm taking common x of s, that means this will be not 1, this will be I. Here also actually if I'm taking common, this will be si, right? Don't forget s into I. So this will be there actually, s into I minus I, okay? All these are matrix, and that will be equals to a itself is a matrix into x of 0. X of 0 is just a constant number. So I can say what is my x of s. X of s is equals to a into x of 0 upon, like I can take the inverse, this is just a matrix, right? Just a matrix. So not I can take the inverse on both sides. This will be if I take x, yeah, a into x of 0 into si. Hold on a second. Yeah, a into sorry, this is a, right? This a, what I'm doing, this is a matrix, a will be there, sorry, this will be simply one x of 0 only. Oh, this will be x of 0, sorry, si minus a inverse. Okay, that will be your x of s. If I take the Laplace transform here, this will be my y of s, this will be equals to c into x of s. Simply I can put my x of s here, so my y of s is equals to c x of 0 into x of s into this value si minus a inverse, right? So this is my natural response. So I think there is a is there any question? So this is my this is my x of s, and yeah, this is my natural response, right? So basically x of t is this. Okay, now there is a very interesting thing. If I take the Laplace inverse of this, right, if I want to calculate what is my x of t, the Laplace inverse of this will be actually e raised to power at. How? So of course we will not come into the proof. There is a proof, I think I have also proven it somewhere, but we will not go into the proof. Simple thing is, right, if I have simply s minus, so this is a, right, uh yeah, s minus a inverse, right? So I'm talking about the case when my matrix is 1 cross 1, for the basic case 1 cross 1, right, single element. So si minus a into x of 0, and this is my x, capital X of s, right? So this is a 1 cross 1 matrix, so simply this will be x of 0 upon s minus a. So what is the Laplace inverse of this? It is simply e raised to power at into x of 0, that's all, right? So for 1 cross 1, this is the proof. Okay, for higher order I have proven it in my full course, but of course we don't have time, so we will not discuss about this. So actually this matrix, right, uh, this matrix is called as the state transition matrix because it defines how my state is transitioning with respect to the initial conditions, correct? Output also, obviously we will calculate the output, no worries, of course we will calculate the output. Why we will not, right? We will calculate the output. Output will come out to be, so what will be y of t? Y of t is simply equals to c into x of t, right? Y of t is c into x of t. Y of t is c into x of t. So this is my x of t, correct? Y of t would be simply c into e raised to power at into x of t. So this is my y of t. Okay, so that's why this is called as the state transition matrix. I hope you have finally understood why this matrix, right? This is actually a matrix. How is this a matrix? So you will feel like how this is a matrix. So if you expand your e raised to power at, right, it will be what? 1. In matrix format, 1 is represented as I. 1 plus a plus a square by 2 factorial plus a cube by 3 factorial and so on, right? So this is a matrix actually. All these are matrix, right? You can do a square by 2. So this will be the value of this matrix. Okay, e raised to power 80. So that's why I hope you understood, right? This is a matrix. Of course, we'll solve many questions in this. Further, we'll understand. Before that, there are few properties of a matrix. So the trace of any matrix A, right? In this case, system matrix will be actually the sum of the eigenvalues of that same matrix, and actually in our case, it is the poles. So basically, sum of the elements. Let's say this is my A matrix. -1, -2, 0, 3. So sum of trace of my matrix, right? Trace means sum of the leading diagonal elements. This, right, will be equals to sum of all my eigenvalues, and this will be equals to sum of all my poles. Determinant will be equals to the product of my eigenvalues or product of my poles. These are the properties of A. Okay, these are properties of eigenvalue and eigenvector. You must remember it, right? Okay, so yeah, if I have a matrix A and if its eigenvalues are this, if I am adding A plus Ki, then its eigenvalue also will be incremented by K. Okay, if one of the eigenvalue is 0, then the matrix is said to be singular because the determinant comes out to be 0. That's why. So these are few properties of eigenvector, eigenvalue that you must know, and it's good to figure out. Great. Okay, now yeah, that's all basically, and this is my diagonal. So this is a diagonal matrix that I think we have discussed in the R-PYQ video. So what happens if I have a diagonal matrix, right? Diagonal matrix is nothing but the matrix formed using the eigenvalues. That's all. Okay, so I can write a diagonal matrix in terms of this V inverse AP, where V is a modal matrix. How, like, we are not discussing about how to calculate, but we can write a diagonal matrix like this. Diagonal matrix is just a matrix that includes all the eigenvalues of this matrix A. So eigenvalues of this and this will be same actually. Okay, so these are few properties that you must keep in mind. So yeah, let's solve this question basically. Okay, let's solve this question. So here they have given, for the given state equation, uh, this is my state equation. They are asking me what will be x1 of 0, x2 of 0, like x1 of 0 and x2 of 0 initial conditions are given. What will be the state matrix, state vector at t equals to 2? So we can solve it, right? We can easily solve it. So first of all, if you ever tend to forget the equation, always write it. So x dot equals to a into x plus b into u, y equals to c into x plus d into u. Now the thing over here is, what I can do is, the inputs are assumed to be, so they are asking me what will be the state variable matrix. So I have to, they have not given me any information about the input. Actually they should have mentioned that for 0 input, actually they should have mentioned this. So input is 0, so basically my x dot of t will be equals to ax and my y will be equals to cx. So basically my x of s into s minus x of 0 will be equals to a into x, capital X of s. So basically your, you can solve it, right? Your x of s will be equals to si minus a inverse into x of 0. That's all. Correct? So how will I solve it? So what you can do is, you can, there are many ways to solve it. I'm thinking just how can you solve it? That is what I'm thinking. Okay. Okay. Si minus a. So yeah, si minus a inverse, right? So what is si minus a inverse? So what is si minus a? S I. So s into I is 0, 1, right? It is a 2 cross 2. So a will be of order 2 cross 2 minus a. A is what? A is this value, right? 2 0 1 3. Okay, and I have to take the inverse, of course. Don't forget the inverse, right? So this will be, this will be equals to s minus 2 0 minus 1 s minus 3, and I have to take the inverse. Now there is a shortcut for inverse of 2 cross 2 matrix. You swap the main diagonal elements and you change the sign of the off diagonal elements. Also you have to divide by the determinant. What is the determinant? S minus 2, s minus 3, and then of course you will do this simplification. This I have taught in my engineering mathematics linear algebra as well. So s minus 2 1 0, correct. Okay, now this, if I rewrite, this will be 1 by s minus 2 and 0. Like I can take this inside, right? I am taking this inside actually. So 1 by s minus 2 into s minus 3 and 1 by s minus 3 basically. So what you will do, right? So this is your si minus e inverse. So your x of s is equals to si minus a inverse, this matrix, right? Whatever, like let me write this a b c d, okay, into x of 0. What is x of 0? It is a column matrix, right? It is minus 1 1. So it is minus 1 1. Okay. So if it is minus 1 1, so basically your, okay, this will be very difficult for us to solve. This will be a minus a, so a, b minus a and d minus c, correct? Where my a is basically this value, a is this value, b is this value 0, c is this value and d is this value, right? Now you will take the Laplace inverse. Can you calculate the, because now you will take the Laplace inverse, because if I take the Laplace inverse of this equation, right, what will I get? On the left hand side I will have x of t, on the right hand side whatever the expression that will be the expression. So there is one way to solve it directly in the time domain, that is very lengthy, right? We will ignore that, we will discuss in frequency domain. Okay, so first I will take the Laplace transform, I will solve it, I will find out this matrix. Okay, Si minus A inverse, Si minus A inverse will be this. Next, either you can find out this directly, you can take the Laplace inverse here, right, and this will be a resolvent matrix, and with a resolvent matrix, like I hope you can take the Laplace inverse, right? You can take the Laplace inverse and convert this into time domain. All these are exponentials. First of all, this is a unstable system. Okay, so now you, what you will do, like either you can do that, or first you can multiply, then you can take the inverse, or you can convert this into time domain, then you can multiply. Both are perfectly fine. It depends on whether you want to reduce your calculations or not. So your x of t is this finally. Okay, u of t, because it exists only after t greater than 0. It is not the input, right? This is not the input, not input. It is step signal. Okay, step. So they have asked me to find the value of x of 2. X of 2, if I put here 2, this will be minus e raised to power 4 and e raised to power 4. That's it. That is your 0 input response. That is your that is your, not response actually. This is the state variable value. Now what is the response? Right? This was the state variable value. What was the response? Response is c into x of t. Okay. So here have they given us c? They have not given. So they have given us c, right? C is 1 0. Okay. So simply 1 0. So what will be y of 2? Y of 2 would be equals to 1 0 into my x of t, right? That is x of 2, that is e raised to power 4, e raised to power 4. This will be equals to minus of e raised to power 4. So your response, 0 state response, sorry, 0 input response is minus e raised to power 4. That is your answer. That's how simple it is, right? So that is the full flow with which they can ask. Like they can ask a small part, whatever I have taught you till this point, they can ask a very small portion of it. Okay. Now what if the initial conditions are not at t equals to 0? Then how will you solve it? Then you have to think about it, right? Then your inputs will not be basically, then your inputs will not be in the so how will you solve? So that we'll discuss. Okay, if your basically initial conditions are not at t equal to 0, then how will you solve? We'll discuss. So first let us discuss the property of state transition matrix. So we know that phi of t is called as the state transition matrix, that is in time domain it is e raised to power 80, which is itself a matrix only. Okay, as you can see, this is a matrix only, right? So that is what my state transition matrix is equals to. Okay, great. Now if I write phi of 0, right, that basically means t equal to 0. And what is e raised to power 0? It is simply 1, right? And in matrix 1 means identity matrix. So phi of 0 actually is identity matrix, and the order of state transition matrix is same as the system matrix, that is n cross n. So this is one of the property, very important property, right? Very important property. You have to remember all these things. Okay, there is a big proof, not going to that. Now what is phi dash of 0? Right, again similar proof is there. If I differentiate, right, with respect to t, this will be a into e raised to power 80, and if I put t equals to 0, this will be simply a, right? So phi dash of 0 actually is my system matrix. So this is called as the system matrix. That's all. Okay, great to know, great to understand. Okay, now here, if I raise my 5 to the power of k, if I am raising it to the power of k, this will be e raised to power 80 raised to the power of k. So this will become e raised to power akt, e raised to power akt. So if I take these two terms together, this is simply ak into t, e raised to power ak into t. So I can assume this to be a variable m, right? So this is e raised to power mt. So basically this is nothing but phi of mt, that's all. Okay, because here initially I had my phi of t was what? My phi of t was 80. Okay, sorry, not phi, sorry. So this is phi e raised to power akt, right? Because I'm just taking the power. So what I can do, I can take k and t together. Okay, so I know phi of t is equals to e raised to power 80, correct? So phi of this I can assume to be m. So phi of mt would be, so sorry, phi of m would be e raised to power am, where m is my kt. So phi of kt is equals to e raised to power kt. So that's why this relation is followed. Again, very like not that important. Mostly we will use this property and this property. Okay, but this is also a very important property and good to know. There are of course proof, we don't want to go to that proof, but here this is the property that we will use if my initial conditions are not at t equal to 0. Okay, let us prove this property. So basically this means phi of t1 minus t0 into phi of t0 minus t2 will be simply equals to phi of t1 minus t2. What does it mean? So if I break it down, right, this will be what? E raised to power a of t1 minus t0. This will be e raised to power a of t0 minus t2, right? So ultimately your t0 and t0 will be cancelled. This will be e raised to power of a of t1 minus t2. This is equals to my phi of t1 minus t2. That is what I have done over here as well, right? So this will be useful actually. We will use it, okay? And this property is like it tells that state transition process is bilateral. So we will use it here now. So if I say x of t is equals to phi of t into x of 0. So if I delay my time by t0 units, right? If I am delaying by t0 units, here I have t0. I'm delaying it by t0 units. So if let's say I had a step here, right? If I had to write delayed step, how will you write it? It will be u of t minus t0. If I had a step at t equal to 0, if it is a delayed step, how will you write it? It will be u of t minus t0. That's why here I have written a delayed state transition matrix. Why? Because the input state variable was also delayed. Initial state was not at t equals to 0, it was at t equals to t0. That's why this is a delayed state transition matrix. So your response, right, will be this. This you have to, if you want to remember it, understand it, and it conceptually as well. Okay, so if your initial state is not applied at t equal to 0, this is how you will solve it. Okay, this is how you will simply solve it. Yeah, that's basically it basically. So yep, I think there's a bit of proof here. We don't want to go into the proof, but that's how you'll solve it. Okay, so yeah, let's say this is the equation, right? We have to find out our x1 of 0, x2 of 0 and x1 of 2, x2 of 2 if we know this value. Okay, so initial values are not given to us, they have given me this value. How will I compute the initial values basically, right? Okay, so if either your initial state is unknown to you, right, and the state is given at a certain point that is not, that is like at t equal to 1, how will you calculate the initial state, how will you calculate the response? So it's not that difficult, right? Pretty simple. So first of all, I know I will use my equation, right? x1 dot is equals to a into x plus, the input is not there. Okay, input is not there. So basically my x of s minus s into x of s minus x of 0 will be equals to a into x of s. So basically, right, your x of s will be equals to phi of s. This is also called as resolvent matrix in Laplace domain. In time domain also it is called phi of t. That's it. this will be into x of 0, right? Now x of 0 is not known to me, correct? So it does not matter actually. It does not matter. Without it being known, then also you can solve it. So how will I solve it? So you can use properties, or without properties also you can solve it. Without properties also. So here, right, what is phi of s? It is si minus a inverse, and trust me, this will be used a lot of places. So this, right, this should be your bread and butter. Okay, this should be a chalk and cheese. So si minus a, so s minus a, this is 0, this is minus 1, this is minus 2, s plus 3. So this will be equals to s plus 3, s, signs will change, I will divide by the determinant, 1 by s into s plus 3 minus 2. So this will be equals to uh, so this, right, is s square plus 3s minus 2. Can I write this like this? Okay, s, okay, what will be the location of poles? Minus b plus minus b square minus 4ac. Okay, that is weird. So I'm getting weird location of poles. Yeah, I just made a silly error, like here, right? Actually forgot, like here I have minus 2, so I'm subtracting this will become plus 2. That's what I was thinking. This will be plus 2, so this will be minus. So if this is plus 2, right, this will be plus actually. That's what I was thinking. This should be simple. Why is this difficult? So s plus 1 into s plus 2, this is my location of poles basically, correct? So this would be 1 divided by s into yeah, s plus 1 into s plus 2. So okay, this would be s plus 3 by s plus 1 into s plus 2, 1 upon s plus 1 into s plus 2. So you have to be very good in matrix, and this would be minus 2 upon s plus 1 into s plus 2, and this would be s upon s upon s plus 1 upon s plus 2. So yeah, now we are done, so we can finally take the Laplace inverse, right? But taking the Laplace inverse, will it help me? Okay, x of 0 is also there, right? Don't forget x of 0 is also there. Don't forget that thing, right? Okay. So if I take the Laplace inverse, this is my resolvent matrix phi of s, correct? The Laplace inverse of this, right, would be, so let me first put it in the partial. Let me take another page, that will be better for us. Let me keep it down. Like I've already solved, actually, okay, let's use the solution only. So I've already solved it. Okay, so ultimately, right, your phi of t will come out to be what is your phi of t? Phi of t will come out to be this will be a phi of t. Okay, so let us use this phi of t. Actually, I want to show something, so let us use this phi of t, because like that, like you can do partial fraction, right? You can do partial fraction, you can solve it, you're expert. So this is my phi of t. Okay, Now what will I do is, I know that x of 0 into this phi of t will be equals to my x of t, correct? So let me put here t equals to 1, because I know the value of x of 1, right? So if phi of 1, what is phi of 1? It is simply 2 raised to power minus e minus e raised to power minus 2 e raised to power minus 1 minus e raised to power minus 2, 2 into e raised to power minus 2 minus 2 into e raised to power minus 1, 2 into e raised to power minus 2 minus e raised to power minus 1 into x of 0. I know, I don't know what is x of 0. You can obviously take the inverse, then multiply. That is also up to you. Actually, that is interesting. Actually, we could have not taken the inverse. Okay. No, but you could have. You did not. Yeah, you wouldn't have got the expression for x of t, right? Yeah, that is also another thing. Let me just do one thing. Just hold on. So x of s into si minus a is equals to x of 0, correct? Ah, we can directly take the Laplace inverse here only, no? That's all. That will be so much easier for us, correct? Okay, if I directly take the Laplace inverse here, this is si minus a. If I directly take the Laplace inverse here, that will be, yeah, because this is in product, right? So there is some s term. No, we cannot do it. We cannot do it. No, we cannot do it. So x of 0 into x of 1. Okay, and x of 1 is what? X of 1 is given to us, that is equals to 1 comma 2. So there are two ways, right? There are two things. Either you can directly take the inverse of this, right? This is just a matrix. You can take the inverse and your x of 0 would be this, like this. Let me name this matrix as some m matrix. So m inverse into 1 comma 2. Okay, like that you can find out. And yeah, if you know x of 0, then ultimately you can find out any value x of t at t equals to 2 as well. You can do, but we can use the property, like this is one of the way to solve it, and basic way as well if you don't remember the property, but you can use properties. Okay, so this, right, I have told you, this I have told you, right? X of t is equals to phi of t into x of 0. X of t will be equals to phi of t minus t naught into x of t naught. That is one thing. Another thing is, if let's say x of t is equals to uh, phi of t into x of 0, so what I can do is I can write this as an inverse. So x of 0 would be equals to phi inverse into, like, basically 1 by phi of t into x of 0. So this is simply phi raised to the power of minus 1 into x of 0, and we know if I am raising it to the power of minus 1, right, this, right, can go inside third property. So this will be phi of minus t into x of 0, sorry, into x of t, sorry, into x of t. Okay, that is what my x of 0 is equals to. So just put here t equals to 1 and your answer is there. Okay, that's how easy it is, right? That's why you can use this property. This property is very useful. So you have, if you would not have used this property, you would have to calculate the inverse. That will be very complex, correct? So what you can do is, you can say that your x of 0 will be equals to phi inverse into x of t, which is basically phi of minus t into x of t. So put the value of t equals to 1. If I put the value of t equals to 1, this will be phi of minus 1 into x of 1. What is phi of minus 1? Phi of minus 1 would be, this would be 2 raised to the power e minus 2 raised to the power e square. This will be e minus e square. This will be 2 e square minus 2 e 2e square minus e into x of 1. X of 1 is already given to me, right? X of 1 is this 1 comma 2. So this is how easy it is, right? You don't need to compute this inverse. That will be very tedious for you. So that is the user property. So ultimately, what property you have to remember? So these things, it's okay if you don't want to remember, that's fine. First property, the most important one. Most important one. This will be used. We will see. Second property, again very very important. Third property also again very very important. And this final property, right? This is again very very important property. Okay. So this thing also you have to remember. These are the four things that you have to remember. Okay, in state transition matrix. So that was about the state transition matrix. This is also called as the resolvent matrix if it is given in the S domain. Now let us discuss about the complete solution, right? When input is also considered, input is non-zero. If input is non-zero, then right, your x dot will be converted into this in Laplace transform. So what you can do, again you can take x of s to be common, right? If I take x of s to be common, or okay, what they have assumed. So because what they can do, okay, let me do this. So x of s, if I take this as common, right, here this will be s, again si minus a, and this will be equals to x of 0 plus b of us. Just give me 1 second. Okay, so now my x of s would be equals to x of 0 si minus a inverse into x of 0 plus si minus a inverse into b into u of s. So basically, right, your solution will be addition of the, this is what, if I take this, take the Laplace inverse, your x of t will be equals to, the solution will be equals to the 0 input response plus the 0 state response. Okay, that is what your overall solution would be. So that is what is written over here. Okay, so yeah, this, right, this is actually not the, this is very simple to solve. Why? Because here, right, if I take the Laplace inverse, this is just a constant. So x of 0, we have seen that it is just a constant. Okay, it is not a function of time. X of 0 is the value of x at t equal to 0. It is just a constant number. But this, right, is u of s. So I'm multiplying, this is also a frequency term, this is also a frequency term. Basically, if there is some multiplication, let's say I have some r of s into y of s. Okay, so the Laplace inverse of this will be convolution in time. This you will learn later on, right? This you will learn in signals. So this, right, solve, taking the Laplace inverse here is very difficult. So what we do is we first solve this in the frequency domain, then we take the Laplace inverse. I know you have not understood this thing. What do I mean by it, right? So do I have an example? Okay. Here, how? So I don't, it seems like I don't have an example, unfortunately. These are ABCD, that is fine. Yeah, I have this A and B, right? So this A and B are there, and let's say I have a U of S. U of S is unit step. So let me solve it for the previous case only, where I had been given the A. B was not there. Okay, B was not there. Okay, A is here, right? So let me take this example. Okay, then I will explain what do I mean by it. Okay, this is here. Great. Yeah. So let me paste this and let me just take this example. So here, what will be, let's say, if your U of S is basically a single input, basically 1 by S, right? It is a unit step. U of t is basically your input is a step function. It is input. So your input is unit step. Okay. So what will be your U of S? It will be 1 by S. Got it? Great. and let's say you have some initial state variable, it is 2 cross 1, 1 comma minus 1. Okay, so what will be your equation? So your x dot will be equals to a into x plus b into u. All of these are functions of time. So I'll convert this in frequency domain. So this will be x into x of s equals to a into x of s. Also don't forget the initial condition, minus x of 0 plus b into u of s. Okay, so here, right, you can simply take the Laplace transform. Why? Because this b is just a constant, it is not a function of frequency or time, it is not a function of time. Okay, and this a is also a constant number. You see, a and b are all constant, so all these are good, these are great. But what if your b was a function of time? Let's say your b, right, instead of this it was t comma e raised to power t. Then can you take this simple Laplace transform here? You cannot. Why? This b, right, is just a constant. So 3 into u of t, what is the Laplace transform? It is 3 into u of s. So this does not change. So this does not change. But if let's say this is not a constant, this is 3t into, let's say, u of t, then what will be the Laplace transform? The Laplace transform, right, it is not that easy. Individually, if you find out the Laplace transform, it will not be the multiplication. So I can show you, right? So what is the Laplace transform of 3t? It is 3 by s square. What is the Laplace transform of u of t? It is 1 by s. So if I multiply these two things, it will be 3 by s cube. That is wrong, right? What is the Laplace transform of 3t into ut? It is 3 by s square only. Correct? 3 by s square only. So that is a problem. Basically, if I am multiplying in time domain, there will be convolution in the frequency domain. So that you will learn, like in signals. So that's why if it is a function of time, then it becomes a problem. Then I cannot convert. If it is a constant, then there is no problem. So as this was constant, I was laughing. Okay, there was no problem. But if one day they will give this as function of time, then you have to be very, very careful. Then how will you solve? How will you solve? Just like I have solved here. What did I do? I did not solve them separately. I made them together and then find out the Laplace transform. So here also, if it is a function of time, first you will see your input, you will multiply. So your input is u of t, right? So you will multiply t et into u of t. So this whole thing, right, b into u will be converted into tut into e raised to power t ut. Now you take the Laplace transform. This will be 1 by s square, 1 by s plus 1. So if you have enjoyed this, understood this, hit a like and comment below. Okay, if you have understood the concept of Laplace transform and we are not even studying signals. Okay, so yeah, this point is very, very important. Okay, but till now, till today, till this date, they have not asked a question like this wherever these are functions of time. But if it is a function of time, then right, things will be very hectic. Okay, just be careful. So yeah, as these are constant, so I can easily take the Laplace transform, no problem, right? So this is my x of s. Now I can write my x of s as a function of, so I can take this all this common and then I can take the inverse. This will be si minus a inverse into x of s plus b into si minus a inverse into u of s. Now previously what we did, this was not there, so we simply took the Laplace inverse, right, and this was my x of t, that was equals to phi of t into x of t, x of 0, sorry, this is not x of s, sorry, this is x of 0, right, sorry, x of 0. So it was very simple. But this is not simple. B is constant, but this is not, this is a function of frequency, right? This was a constant, so this was not a problem. But this is a function of frequency, and this is also a function of frequency. So there are multiplications. So I cannot simply take the Laplace inverse. How can you, so how will I solve it? So first I will multiply these two together and convert them as a single term like this, right? I converted them as a single term, and then I will take the Laplace inverse. So what is my SI minus A inverse in this case? So SI minus A inverse would be SI minus A inverse. So minus 2, this will be plus 2, this will be S plus 2, okay, inverse. So this will be 1 by S into S plus 2 plus 4 this plus 4, and this will be swapped S plus 2 S, this will be 2 minus 2, okay, that's all. So okay, now what you'll do, I have U of S as well, right? What is U of S? U of S is, so you have to multiply B as well, right? So what is B? B is 0 comma 1. So don't forget B. B is there. SI minus A inverse into B is also there, right? Now this is just a constant. This can come outside. Okay. B is also there. B is 0 comma 1. Okay. So your equation will be simplified, and ultimately you have to multiply U of S as well. So I will multiply all these things. U of S is what? U of T is unit step. So U of S would be simply 1 by S. That's all. Okay. So yeah, so here, okay, if the order of B is 2 cross 1, so yeah, that is fine, that is fine, yep, that is fine. So let me first multiply these two things. So if I multiply, this will be a row into column, right? So this will be 0 into this, 0 into this. So first row will be 0 anyways, and 1 into this, hold on a second, 0 into this, that's it. Okay, so this is 2 cross 1, 2 cross 2. How will I solve it? No, this is not possible. 2 cross 1, 2 cross 2. How will I solve it? Hold on a second. Okay, sorry. One minor mistake. If I am doing SI minus A inverse, right? So I am post multiplying it. Okay. Yep. So this is like previously it was constant, so there was no issues. But here, right, this will be SI minus A inverse. Hold on a second. No, sorry, I'm pre-multiplying it, right? Yeah. So okay, let me write it properly. Like what I'm doing, there is a concept of pre-multiplication and post-multiplication. So if I take this on the left hand side, this on the right hand side, this will be, if I take x of s to be common, correct? So okay, you can either pre-multiply or post-multiply. It's totally up to you. So let me keep it as pre-multiplication. That would be best. So this will be si minus a. This will be cos x of 0 plus b into u of s. So if I pre-multiply si minus a inverse on both sides, this will be I. This will be si minus a into x naught. So this, right, will be pre-multiplied. So be careful. This is all matrix, right? So actually order matters here because I am doing multiplication. So order matters. So this will be actually si minus inverse. Previously, right, all these formulas, whatever I have written. Okay, this is actually correct, right? Phi of s into bu. So this is actually correct. I have written here correct only. Okay. So yeah. So this will be si minus a inverse into b. So first, right, order matters actually here. Order matters. Otherwise, matrix multiplication will not be valid. So this, right, will be here. Si minus a inverse will be here, and then b will be there, then u will be there, correct? So directly I can simply multiply this, right? So okay, b represents m into b represents n into m, correct? So what n is the number of state variables and m is the number of inputs. Why, how can I say it is m into m? Because u would be like, it is b into u, right? And of course the first element, first number of rows will be defined by number of rows of here, that is n. Only I can decide the number of columns, that will be decided by the input. So here it is 2 cross 1, So number of inputs is 1, that is fine. So 2 cross 1 into simply a single variable, it is simply 0. So I can convert this. This will be simply, hold on a second. I'm multiplying simply a single element with this matrix. So this will be 1 by s into this, right? So simply this will be 0, 1 by s, that's all. Now I can complete this multiplication, right? What will be this multiplication? This will be 0 into this, that is 0, 2 into this. So this will be 2 by s, okay, upon this will be again 0 into this is what? This is s, right? S into 1 by s, that is simply 1. Okay, of course there is this term. So this is s square plus 2s plus 4, right? S square plus 2s plus 4 is nothing but s plus 2 whole square. Okay, now like this is the result of phi of s, si minus a inverse into b into u of s. Okay, now you are ready. Now you take the Laplace inverse. Okay, you put this inside, right, and then you take the Laplace inverse. Now you can easily calculate. So that is what I was explaining. So that is how you can calculate the complete, like x of 0, x of t in terms of x of 0 already you have solved. Now it will be some function into x of 0, there will be something, and plus also input is considered now. Consider properly input, a function of input is also considered now. So that's how you will solve basically. I hope that is that part is clear. So yeah, now these are all great to know, but mostly questions will be asked from this transfer function, right? So what they will do is they will ask you to calculate the transfer function. How can you calculate the transfer function? Transfer function will be calculated whenever your initial state is 0. Of course we discussed, right? Initial condition are 0, so it is basically the 0 state response. Okay, and for simply L-type systems. So transfer function will be very simple. What will be the transfer function? Transfer function is y of s upon x of s, correct? So that will be equals to, so here, right, if I solve this, this will be x of s, s into x of s minus x of 0, but x of 0 is 0, no initial condition. So it is directly equals to a into x of s plus b into u of s. Okay, so your x of s is equals to si minus a inverse into b into u of s. That is what my x of s is equals to. What is transfer function? In this case, my input is not x, actually, sorry, my input is u of s, right? That is a transfer function. So I can replace my x of s in this equation. So y of s, so that is what I have done here. If you see, my transfer function is this. Okay, if you solve this, I have came till this point, x of s is this, then I will replace in the y of s the value of x of s, and your transfer function will be the ratio of y upon u, right? If I take u common, so this will be basically this. Do you have to remember it? I guess you don't have to, because anyways you remember the state equation, you can derive it in 10 seconds. It will take you 10 seconds to derive the transfer function. If you ever forget, but you will not forget because you will use this hundreds or thousands of times. Now this is my transfer function. Okay. Most of the cases your this D matrix will be 0. 99% of the cases. Okay. In 99% of the cases, your D matrix will be 0. So your transfer function will be only this. And mostly they will ask this only. Okay. Thousands of times this formula has been used, so mostly they will ask this only, but sometimes D will not be 0. So you must know the proper proper equation as well, so you can solve it, right? Like you just have to do matrix multiplication. So these are few. So pause the video, try to find out the transfer function for this system, for this system, for this system. Like it will take you a bit of time, because finding out, you have to do si minus a, then you have to take the inverse, then you have to multiply with b, and you have to multiply with c in front, right? Make sure you are writing it in proper order, because in matrix multiplication the order matters. Okay, now one small thing I will say, whenever you are solving state space transfer function, just this, right? Sometimes calculating this is very tedious, right? Si minus a inverse, so you can assume a b c d, right? And then further solve it. You can multiply this with b, right? Then you can multiply this with c. So your equation will be b plus d. So actually you don't need to calculate all the elements of si minus e inverse. You just need to calculate the b element and d element, right? So this is one simplification that you can do. Also, please remember how to find out the inverse of a third order equation. But my expectation is they will never give you a third order equation. Maximum they will give you second order, because finding out the inverse of a third order equation will be very difficult, right? That will take you huge amount of time. So mostly they will not give you the third order equation. Okay. So yeah, so this is one property, very very important property, that eigenvalues of A system matrix will be equals to poles of A. There is a proof, but we don't need to go into the proof. So basically this equation, right, magnitude, determinant, not magnitude, sorry, determinant Si minus A, this is actually the characteristics equation. Okay, determinant Si minus A is the characteristic equation. How? So basically, right, your transfer function is what? Your transfer function T of S is C into Si minus A inverse into B. So if I assume everything to be 1 cross 1, right? If everything is 1 cross 1, this will be simply C B by Si minus A. So what is this? This is the pole, right? This is the numerator, denominator. So if I make this equal to 0, that will yield me the characteristics equation. So of course we have to take the determinant, right? So we for a matrix we will take the determinant and make it equal to 0. That will be called as the characteristics equation. That's why it is called as system matrix. Of course there is proof, we are not going into the proof. Okay, now there are a few things, like I've already explained, right, how to apply state space equation. So if you have given LC, you can simply write the KVL KCL equations and you can convert this into state space equation, right? But they will mention you exactly what variables are they taking as state variables. Okay, so yeah, let's try to do this actually. So if they will mention you, I think there is example. Where is example? Yeah, this is example, right? Yeah, this is example. So here write the state space representation for the following circuit. These are the values, these are the initial conditions, and find the time domain expression for Vc of t and IL of t. Now as I have told you that state space representation is not unique, so it can change, but ultimately your final result, right, Vc of t and IL of t, for both students, me and any other student, it should come out to be same. If you have solved it correctly, it will come out to be same. So let's solve it basically. So here, right, let me write the KVL. So I have to write my input is Vi, my output is Vo. Also, my state variables are Vc of t and IL of t. Okay, they should have mentioned actually, but these are my state variables. So what is the state equation? It is some x dot plus a into x plus b into u. Okay, so what is Vc dot? Vc dot is dVc by dt. It is simply equals to Ic by t, capacitor current by t. Okay, but that is actually not my state variable. So I cannot write Vc. I have to write Vc dot in terms of my state variables, that is Vc and IL, correct? And plus of course the input. If I have input, I will write it in terms of input. So what is IC? This capacitor current is same as the inductor current. It is a series circuit. So I can say Vc dot, this is not actually C, right? So Vc dot actually is equals to IL by C. So yeah, I got one of the state equations. I got the first state equation. Vc dot equals to IL. So we generally write this in small letters. State variables are written in small letters. Okay, and it is understood that this is bracket of t, this is bracket of t. I'm not writing bracket of t because it will be very untidy, but I hope you understand the fact these are all functions of time. Okay, Vc dot IL, I got one state equation, so I don't have any input, that is fine. We don't have input, no problem. What about the next state equation? So how can I write IL dot? What is IL dot? IL dot is L DIL, sorry, DIL by dt, and DIL by dt is simply equals to VL by L, correct? VL by L, but VL is not my state variable, VC is, right? So I can write a KVL here. If I write KVL minus of Vi plus IL, because IL is my state variable, so I'll write in terms of IL. I'll not write I'll write in terms of IL. IL into R plus VL. VL is not my state variable, so I want to replace VL here, right? That is the reason why I'm writing here VL plus VC. VC is also my state variable. This is equals to 0. So my VL is equals to Vi minus ILR minus VC. So this will be my IL dot is equals to VI by L minus IL R by L minus VC by L. Okay, yeah. So now finally I am able to write my IL in terms of my state variable IL into minus R by L. So this is my equation 1. So like first of all you have to define the order of state variables. So first VC will come, then IL will come. Okay, these are my state variables. So yeah, so first I will write VC, then I will write IL. Okay, so IL will be here and this will be VC into minus 1 by L plus IL into minus R by L plus VI into 1 by L. So are you able to form the equation? Are you able to form the state equation? It's pretty simple, right? Pretty simple, that you have to simply write here. So what is my state equation? So state equation would be first VC is there, then IL, right? So VC dot IL dot is equals to what? VC dot is equals to what? VC dot is equals to IL by C, that's all, right? So here I have my, this will be a 2 cross 2 matrix because I have two state variables. I have here VC and this is not capital IL, small I, right? So actually I have to write dot twice. So IL, so it is VC is equals to IL into 1 by C, and I have 0 into VC plus 0 into input VI, right? So this will be actually 0, this will be 1 by C, and I don't have any input, right? So plus 0 into input is 0, that is VI, that is also 0. Now what about IL dot? So IL dot is equals to minus 1 by L of VC and minus R by L of IL. Okay, this should be small IL, right? 0, this will be, and it is a function of input as well, that is equals to 1 by L. Okay, so that's that, correct? So yep, now we have to solve, just give me 1 second, yeah, we have to solve it. So this is my state equation, right? What about my output equation? So my output, what is my VO? VO is this, right? So VO is directly equals to my VC, right? It is not even a function of input. So D is 0. So VO is directly VC, right? So VO is directly equals to VC. So, and it is 0 into IL. So I can write VO to be equals to 1 comma 0 into my state matrix, sorry, state vector VC into IL. Sorry, this will be actually, this will be a row matrix, right? 1 0 VC into IL. So this matrix multiplication is proper. So the order you can find out using intuition, right? Using basic common sense. Plus 0 into U, it is not a function of input. So now I hope this is my A matrix, this is my B matrix, this is my C matrix. I hope we can calculate the complete solution. So let us calculate the complete solution actually. That will be good for us, right? So they have given me the values. The values are, so okay, if input is 0, so input is 0, right? If input is 0, then this thing is automatically gone. So basically my x dot is equals to, what is my A matrix? So A matrix is 0, 1 by C, 1 by C would be uh, 2, right? 1 by C would be 2 farad, that is 2 only, minus 1 by L, minus 1, L is 1, right? Minus 1, minus 1, minus 1 by L, minus R by L. R is also 3, 3 by 1, minus 3 by 1, that is minus 3. Okay, so this is my uh, matrix basically. Now into X, and U is like input is 0, right? Input is 0. So they are asking me to find out the expression for VC of T and IC of T. Okay, so this will be basically uh, okay, this is my A, SI minus A inverse, right? So what is my SI minus A inverse? This would be minus 2, 1. Into okay, so this would be, so what is X of 0? X of 0, right, is like VC of 0 and IL of 0, that is 1 comma 0, right? So we don't need to solve everything actually. So this will be 1 into 0, that is S plus 3 only, and this will be minus 1, that's all. That is what we have to solve, right? So this will be S square plus 3S plus 2, that is S plus 1 into S plus 2. So yeah, I hope you can solve it now. So like this is my x of s basically. So if I take the Laplace inverse, I will get the expression for x of 0, x of t, because they are asking me x of t only, right? Yeah, x of expression for VC of t and IL of t. So yeah, this will be, if I just use partial fraction, s equals to minus 1, this will be 2 by 1. So 2 by s plus 1, s equals to minus 2, this will be 1 by minus 1, so minus 1 by s plus 2. Yeah, that's all. So 2s plus 4 minus s, so s minus 1, yeah, it is correct, and upon minus 1 upon, so again if I use the partial fraction, this will be when s is equals to minus 1, this will be minus 1 upon plus 1, that is minus 1 by s plus 1. S equals to minus 2, this will be actually minus minus plus 1 by s plus 2, that's all. So ss will be cancelled, this will be, yes, this is correct. So if I solve this, right, this will be 2 into e raised to power minus t, if I take the Laplace inverse, minus e raised to power e raised to power minus 2t into e of t. This is what was the first element? What was the first element? What was the first element? VC, right? This was my first element, that is my order. What was the first element? So this is equals to my voltage, VC of t. And what about the current? Current would be e raised to power minus 2t minus e raised to power t into u of t. Okay, this is my current expression, IL of t. Okay, so I think the similar thing we have solved here as well. Like you will see that ultimately here, right, I have assumed the order to be different. So here the order was first current and voltage, but ultimately, right, if we solve the final solution of voltage, I think, okay, we have not, unfortunately we have not solved it. That is interesting. Why have I not solved it? Okay, I should have solved it, but ultimately it will come out to be same. But the second part is where my input is not 0 now, but the initial states all are 0, nothing is mentioned. By default you will assume initial states to be 0. So input is a sinusoid, what will be your output? So if your states, all states are 0, then this is just like a LTI system. Okay, if it is a LTI system, simply you find out the transfer function and you put s equal to j omega and you can solve, right? So let us like first of all you will calculate si minus a inverse, right? Then you will multiply this with b and c, okay, and then this is my transfer function, right? And then after this, if you know the transfer function, I hope you can know how to calculate the output voltage. The same thing I have done here, right? I have calculated my si minus a inverse, that is my transfer function, and then simply you put the value of the transfer function at s equal to j omega, magnitude and the angle, okay, and you will be able to calculate your output. So I hope you can understand what is the sinusoidal steady state response. So the next topic is controllability and observability. In between, I have taught a lot of things in my full course regarding similarity transformation, how to decompose a transfer function, right? How to draw the state diagram. But all those things actually not that important for gate point of view, because they will not ask you. Okay, in gate they will mainly focus on controllability and observability. Like there are many forms, so mainly there are these four forms of transfer function, right? Your state space like system matrix can be of these four forms, but we don't need to uh, give too much importance to this, because mostly they will not ask you from this. Mostly what they will ask is from the controllability. What do I mean by controllability? Let's say this is my example, right? Okay, now if I say this is a RC circuit, and if my input is 0 and my capacitor voltage is 0.5, okay, capacitor voltage is 0.5, then uh, what will happen? What will happen? And case 2, my input is a step function and capacitor voltage initially is also 0.5. Both cases initial voltage is there. In this case there was no input, here there is input. So what is the meaning of controllability? If we can control the future state of the system with the help of input, then the system is said to be controllable. If we can't control the future state of the system with the help of input, then it is called to be uncontrollable. So here, right, uh, in case 1, okay, so in case 1, what is the what is the voltage across the capacitor? When input is not there, it is 0.5 e raised to power minus t, right? If input is 0, it will be 0.5 e raised to power minus t. If my input is there, it is a unit step, then the voltage equation is this. So is the future state changed of my voltage across the capacitor? Yes. So I say this system is said to be controllable. Okay, this system is said to be controllable with state variable. Okay, because I see that the future state, I am able to influence the state variable, right, value with input. If input was not present, and if input was present, the voltages I am getting different voltages, future state is different, so that means I am able to influence, that means this system will be controllable. Now what is the mathematical rule that we have to follow for the system to be controllable, right? It is not very simple. Like if you say all the eigenvalues are are negative, basically all eigenvalues negative, meaning all the poles are negative, that means all the poles are lying on the left hand side, then system can be controllable, right? But it is not the necessary and sufficient condition for the system to be controllable. There can be other conditions as well. Okay, so like there are few things, like we have done many calculations, but ultimately, right, the thing that we'll go to is uh, here. So the we will use Kalman's test for controllability. Okay, where is it? So there is a simple formula for Kalman's test of controllability. Yeah, this one. Okay, Kalman's test. Yeah. So we will solve for controllability using Kalman's test. We will not do all these things. We'll solve using Kalman's test. So Kalman's test, right? We have to check for controllability if, okay, this is my transfer function. Actually, no, this we will not do it. No, we will not solve it. Where is it? Yeah, yeah. So okay, observability, will come to observability. Let me first solve a question. Is there any example? Yeah, this is my Kalman's. Okay, this is my Kalman's test for observability. What is my Kalman's test for controllability? I'm not able to see it. Okay, that is interesting. Where is my Kalman's test for controllability? Uh, hmm. Check if the system can be made stable. Yeah, this is my Kalman's test, right? So there is few more physical significance of controllability that I will explain. But first of all, let's understand how can I compute the whether a system is stable or not. So we will calculate the this matrix QC. Okay, this is called as the controllability matrix. QC is called as the controllability matrix, and we will calculate the determinant of QC. And if it is not equal to 0, we say the system is said to be controllable. That's it. Okay. So exam, this will be useful. So you have to remember. And this is my controllability matrix. You will say, what is this? I don't understand. I do agree. You don't understand. So for that, I am here. So let's do an example, right? So this is an example. We have to check if the system can be made stable. What do they mean by made stable? I will explain. Let us first of all check whether the system is controllable or not. Okay. So for that we can solve it. We can solve it. So let's solve. So what is my A matrix? My A matrix is 1 0 0 3. B matrix is 0 1. And for controllability, you just need A and B matrix. That's all. For checking controllability, you just need A and B matrix. Okay. So what is your controllability matrix? It is B into AB into A square B and so on. Okay, and this will keep on happening till what point? Till, of course, my order of my system matrix, that is 2 cross 2. So if my system matrix is 2 cross 2, I'll only choose the first two elements. Okay, so let us calculate. So this will be A. So B is simply 0 comma 1. So the first column will be 0 1 of my controllability matrix. The second column will be A into B. A into B is also a column matrix. So basically these are all my columns. So what is A? A is 1 0 0 3 into B, that is 0 1. So there might be a doubt in your mind, is it B into A or A into B, right? So if I perform B into A, this will be 0 1 1 0 0 3, correct? So this is 2 cross 1 and 2 cross 2. So this matrix multiplication is not possible. So it will never be B into A, it will always be A into B. That's how you can remember the formula. So if it is A into B, so from this A raised to power 0, I multiplied A. So everywhere I will keep on multiplying A, right? That's how you can remember the formula of controllability matrix. Okay. I hope you have understood this point. Now, so it will be A into B. So what is A into B? A into B. So for controllability matrix, you only need A and B because you only need the input information and the state matrix. Okay. For observability, you will need A and C because we want to observe the output. So I will of course explain you the significance of controllability and observability. Let's first know how to calculate these things, right? So controllability, this will be A into B. So this will be 1 into 0, that is 0, 0 into 0, that is 0 only, right? So 0 into 0, that is 0, 3 into 1, that is 3. So this second column will be 3, right? So now if I calculate the determinant of my controllability matrix, is it stable? No. QC, determinant of QC is 0, right? So the rank is less. If the rank is less, basically we say if it is not a full rank matrix, right? Rank of QC is less than n basically. If it is not a full rank matrix, then we say simply our system is not controllable. Okay. and this is same as saying the same thing, that basically the determinant is 0. Okay, if it is not a full rank matrix, determinant will be 0. Now if it is not controllable, it means I will not be able to make the system stable. If let's say the state variables, if one of the states variable is unstable, with the help of input I will not be able to make the system stable. That is what controllability means. I think there are a few key points in controllability. Where is it? Where is it? Where is it? Where is it? Here. So all the state variables, if all the state variables are reachable from the input. So basically I have the input, right? There is some state diagram. We don't want to get into the state diagram right now. I have an input and I have some state variables, x of s and state variables, right? And this is my output. So this is my system, correct? So if all my inputs are able to reach the all the state variables, right? If I'm able to measure all the state variables, if I'm able to take feedback from the state variables, if all the state variables and the input all are interconnected together, that means even if one of the states are unstable, basically even if my system matrix is unstable, with the help of input I will be able to make them stable. I will be able to stabilize it. Then it is called as controllable, because I am able to control the state of the system with input. That's why it is called as controllable matrix. Sorry, that's why it is called as controllable system. And this matrix is called as the controllable matrix. Okay. So if I am able to measure all my state variables, and if I am able to measure all my state variables, even if my state variables are unstable, let's say x1 of t is some e raised to power t, right? It is an unstable signal. But if I provide some input and it is able to reach my state variable, I can do something, right? I can make it, I can stabilize it, I can shift the pole on the left hand side, right? How can I shift the pole on the left hand side? So this is basically 1 by s minus 1. So I can add a 0 of s minus 1 and I can add a pole of s plus 1. I can multiply this, right? So this pole will be gone and my system will be stabilized. So that is the thing, I can stabilize. So this is what controllability means. Controllability basically means I can control all my state variables. Great, understood? Okay, so we can stabilize the system. So there is one very basic question, I think this one, yeah. So stabilize the following representation using positive and negative values of feedback. Shift the poles to -1. So okay, this is my system, right? Okay, stabilize the following system. This is the only question, right? That is what they've asked. Okay, shift the poles to -1. So here, right, this is just a 1 cross 1 matrix. So very simple. It is just a 1 cross 1 system. Seems like very difficult, but it is very simple. Everything is 1 cross 1. Okay. So here, what is my A? A is simply 1. It is a 1 cross 1 element. My B is simply 1. My C is also 1. Okay. So I have to stabilize this system. So what is my transfer function? T of S. It will be Si minus A inverse into B into C. D is 0, right? D is 0. So C is simply 1, S is simply S into I. It is a 1 cross 1 matrix, right? Its order is 1 cross 1, correct? So this will be 1 only, minus A is also 1, inverse into B is also 1, right? So I see that the transfer function is 1 by S minus 1. So it is not stable, correct? It is not stable. How can I make it stable? What shall I do to make it stable? So basically, like there is like they should provide this, they will provide you this diagram, don't worry, they will provide you this diagram. So initially, right, this was your diagram. So they are telling you to provide a feedback, choose some value of this k such that this system is stable. Okay, so if this block, so they have to give this diagram actually, otherwise you will not be able to solve it, right? So you have to make the system stable, and you have to move the pole to -1. How can I move the pole to -1? For that, what do I have to do? So for the modified block diagram, okay, what will be the state equations? Trust me, like they will give you all these diagrams, don't worry, like this diagram was not there, Now I'm giving you this was the state equation initially, and I saw that the pole is at s equal to 1, but they want to have a feedback so that I can shift with the pole to s equal to -1. Currently the pole is at s equal to 1. So what can you do? Simply you can say now your new input r of t is equals to this x, this is my state variable, right? X they have told this is my state variable, into k minus, so r of t minus k into x, k into x equals to u, correct? K into x into u is equals to u. Basically this u variable, u is my input, right? So sorry, my new input is r of t only, right? New variable is r of t only. So yeah, this I don't care, this will be u, basically this value, right? I'll multiply this with b, and b is 1 simply, right? B is 1. So this will be 1, this will be multiplied with 1, and here also I will add x, right? So this will be plus x, a is also 1, and this will be equals to my x dot basically. Okay, this is my equals to my x dot. And what is my y? Y is simply same, y is simply c into x, that is simply x only. Okay, so my new input is r of t, sorry, it will be x dot will be equals to x, I can take common, this will be 1 minus k into x plus r of t. Okay, so so what is my a here? My a has changed, it is 1 minus k. My b is, my input has changed, right? It is r of t, so this will be 1. My c is 1 again. So what is my transfer function t of s? So it will be a si minus a inverse, right? Si minus a inverse, so this will be si minus a, so this will be 1 plus k inverse into b into a, that is 1 only. So it is equal to s minus 1 plus k. So basically, right, your k needs to be 2. If it is equals to 2, then your pole will be shifted to s equals to 1, right? If I'm not mistaken, this has to be, yeah, k has to be, yeah, k has to be 2. Okay, if I'm not mistaken, this is negative here. Hold on a second. This is equals to x dot minus of x. Yeah, 1 minus k. Correct. Yes, it is correct. So, so basically, right, if my value of k, if I'm taking the feedback from the state variable and feeding it, right, to the input, I'm able to control the state. Previously, it was an unstable system. I made it stable. So, controllability helps us to make a system stable. Previously, this system was unstable. With the help of feedback, I made it stable. If the system was not controllable, I would not have been able to take the feedback and measure the output. So that is what controllability tells me. Controllability tells me whether I can take the feedback or not, whether I can measure the state variables or not. If I'm able to measure the state variables and feed it right to the input, I can somehow make the system stable. So that is the significance of controllability. Similarly, there is a concept of observability. Okay, observability basically means that whether my output can observe the state variables. Previously, whether my input can take feedback from the state variables, right? Whether my input can take feedback from the state variables, and observability means observe whether my output can observe the state variables. Output will, of course, it is output, right? I will take the output. Output will not be able to do anything, but whether my output can observe all the state variables. That is what observability means. Okay, so yeah, there is a test again, Kalman's test for observability, right? So which is equals to, again you have to unfortunately remember this formula, which is equals to, like, the actually the matrix is this, right? CA n minus 1. This is the original matrix, observability matrix. Okay, but we remember it like this. So your observability matrix Q naught is C transpose A transpose into C transpose, and like this, right? This is very difficult to understand. So maybe we'll have a example. Yeah, this is example, right? So we have to check for controllability and observability. So this is my transfer function. Will you be able to comment about controllability or observability? The simple answer is no, because you have not been given any state space representation. A, B, C matrix, these are not given to you. So you will not be able to define the state space equations, and if the state space equations are not given to you, you will not be able to comment about controllability and observability. So you will not be able to comment about it. Okay, but we should have some examples. If I have any example, let me just okay, we don't have any examples. Great. So yeah, we can take this only. So let me take the previous example only, right? We had AB. Okay, we had previously we had only AB. Okay, so let us take an example, very basic example. Let's say it is a 2 cross 2 matrix, 2 1 2 3. Okay, or 1 yeah, 1 3, and your C is basically, it will be a row matrix, right? 1 comma 0. Okay, so how will you calculate the observability matrix? First of all, it's a 2 cross 2 system, so your observability matrix also will be 2 cross 2. Basically, if your determinant of observability matrix is 0, then it is said to be not observable. If it is not 0, it is said to be observable. Okay, so let us compute this, right? So first, what will be there? Previously, what was there? Previously, for controllability matrix, if I have C here, right, it was controllability. So if it is C, I cannot have C here, it will be B. That's how you can remember. If I have C here, I cannot have C here, I have to write B. That's it. And this is the first column. Then I will have A into B. B into A is not possible, so only A into B is the only possible. Then I will have A square into B. So your observability matrix will just be the opposite. Already B is taken, so it will be C, and one thing was there, transpose. That's how you can remember it. So this will be C transpose. Then I will have A transpose into C transpose. Again, if you try to do, right, if you try to do uh, C transpose into A transpose, right? What is C transpose? It will be a column matrix, and A transpose would be a 2 cross 2 matrix. So you are trying to multiply a 2 cross 1 with 2 cross 2. Again, invalid. So definitely it has to be it has to be A transpose into C transpose only. Again, I will stop in the second column because order is 2. So what is C transpose? It is 1 comma 0. What is A transpose into C transpose? So A transpose is 2 1 1 3. Okay, hold on. Row will be changed to columns. Okay, hold on a second. Yeah, actually this A transpose is equals to here, right? Because the off diagonal elements are same, so it is A transpose is equals to A only. That is interesting. Row will be changed to columns. Row will be changed to columns. Yeah, A transpose is equals to A. So into C transpose, it is simply 1 0, correct? So this will be 2, this will be 1. So this will be 2 1. What is the determinant? It is simply 1, which is not equal to 0. That means my system for this particular case will be observable. That's how you can calculate the observability condition and the controllability condition. Now there are one more thing, duality property we don't need to study. You can ignore the duality property. Okay, no need to study duality. There is one thing known as stabilizable system. When my system is stabilizable, if my state space representation has few states which are unstable. So few states, like let's say I have x1, x2, x3, and let's say out of x1, x2, x3, x1 and x2 are unstable states, right? Like if I write the time domain expression, x1 of t would be e raised to power t, x2 of t would be e raised to power 2t. These are unstable state, but controllable. It's not like if my controllability matrix is 0, that means one of the states is not controllable. I'm not able to take feedback from one of the states. Okay, if that is the case, then it may happen that few states are controllable. Let's say x1 and x2 are the states from which I can take the feedback. These two states are controllable, but x3 is not controllable, right? X3 is not controllable. Then I can say it is partially controllable system. Or if x3 itself is a stable state, let's say the value of x3 of t is e raised to power minus 3t, which is stable, correct? So I can control x1 and x2 and I can make them stable. So overall the system is stable. That's why it is called as stabilizable system. Okay. If the states, if few states which are unstable are controllable, and if my state space representation has few states which are stable but not controllable, then it is called as a stabilizable system. Okay, although it is not fully controllable system, but it is stable because I can make the unstable states stable, because I can partially control the state variables. But I will not be able to control all the states like x3, but x3 is already stable, so it's fine. So that's why it is called as a stabilizable system. Then next is the last definition, that is detectable system. What is detectable system? So if my state space representation has few states which are unstable, but I can observe those states, right? And if my state space representation has few states that are stable like x3, here x1 and x2 are unstable, but I can observe them. But here I will not be able to observe x3, but x3 is already stable, right? So I don't need to observe it, right? I will observe the unstable things like which are moving, right? You like wherever some action is happening, right? Action movie. So you like to observe unstable things, right? You don't love stable things. So we are able to observe the unstable states, but we're not able to observe the stable states, and that is fine. That state is already stable. So then my system is called as detectable. Okay, because of course I will not be able to fully observe all the states. Few states are not observable, so my qo determinant of qo matrix is 0, but still we can comment that my system will be detectable. So with this we are done with the state space representation. Okay, now we will solve few gate PYQs. Let's begin with solving gate PYQs of state space analysis. So this is the first question. For the given circuit, which one of the following is the correct state? We have been given this differential equation and this circuit is given to us, right? Basically we have to derive the state equations for this circuit. So what do I see? That I have V and I which I am differentiating. That means my voltage and current are my state, like the voltage and current are my state variables. What is the current? Current is the current through the inductor, voltage is the voltage across the inductor, and it makes sense, right? Because capacitor stores in the form of voltage energy, and current, and your inductor stores in the form of uh, 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 like current, right? Inductor stores in the form of energy in the form of current. Okay, so yeah, uh, like now we can do it actually. So I can write few equations. So, and I see I1 and I2 as my input, right? These are my inputs, I1 and I2. So if I write a equation here, or it's better, let me first write a equation here. So I2 is equals to, what is the voltage here? V, right? So I2 equals to V by R plus C dVc by dt, because the current through the capacitor will be IC, that will be C dVc by dt, 0.25 into dV by dt, or I can write simply V dot. Also don't forget, here also I have an incoming current, right? So these two are incoming current, these two are my outgoing current. So actually this will be I2 plus I, that's all. I2 plus I. Okay, so what do I need to write? I need to write my V dot, right? V dot in terms of all the other variables. So my V dot would be first I have V, that is minus 4V, then plus 4I, then plus 4I2. It is not a function of I1 at all. So I see that yes, in the first row if I compare, I have minus 4, correct, plus 4, correct. It is not a function of I1, that is correct. It is a function of I2, that is 4. So this first row is same. Let me compare with the other rows. Now here I have a 4i1, right? That is not correct. Here again this row and this row are same. Here again this row and this row is opposite. So either this can be a possible answer or this can be a possible answer, right? Now uh, let us now solve for the second state variable, that is this, right? So for this actually what can I do? So my I1 and I2 are inputs. So what is the voltage here, right? How do I find calculate the voltage here? That will be a bit difficult. So this current is I1 here, this current is I. So this current will be some, okay, what will be this current? This current will be I1 minus I. Okay, this current will be I1 minus I, that's all right. Now what I can do is I can simply apply a KVL in this loop, correct? I can apply a KVL in this loop. What is a KVL? 2 into this, right? So remember this is the direction of current, correct? So this will be plus minus. So minus I1 minus I into 2, then plus direction of current is this, right? So it will be plus minus VL, that is L dIL by dt, that is L at is 0.5 into IL dot, then plus simply V, the voltage across the capacitor is simply V, that is equals to 0. So I can say that my so I have to write my I in terms of IL dot is nothing but I dot, right? IL dot is nothing but I dot. So my I in terms of other variables, I dot in terms of other variables. So this is I dot. I dot will be equals to, this will be, if I multiply by 2, this will be minus, okay, minus 2V minus 4I and plus 4I1. That's all right. So minus 2 minus 4 plus 4, yes, minus 2 minus 4, this is plus 4 and this is also plus 4. No, it is not a function of I2, right? If I multiply this last row, here I am observing that my I dot is function of I2 as well, but that is incorrect. It is only a function of I1. So option A will be correct. So it is not that difficult basically. You just have to apply KVL, KCL and write the state variables, derivative of the state variables in terms of all the other variables, input and their own state variable. That's all. You just have to form the matrix equation. That's all. Okay. So I'm just doing it in a fast manner because there is no concept, like of course there is a concept involved, but it's not that difficult, right? Simply write down your state variables, derivative of your state variables in terms of the other variables, whatever they have given. That's all. How can you understand? From the options. From the options I can understand, okay, here I'm taking the derivative and here the variable is present itself, right? So that means V and I both are state variables, and I1 and I2 I'm not taking the derivative, that means I1 and I2 are my input. That's all. Let's solve the next question. Question 2. Consider the following state variable. X1 dot equals to x2 dot, uh, x1 dot equals to this and x2 dot equals to this. State variable equations. The initial conditions are this, at t equals to 1. Second, the value of x21 will be, okay. So okay, so the initial conditions are also given to us. So what we can do, we can easily calculate the state variable matrix, correct? Or you can directly solve using basics, using Laplace, that also you can do, but we can solve using state variable matrix. I know that only we are seeing the response due to state, that is the natural response, it is not the forced response. So my natural response is supposed to be phi of t into x of 0, correct? This is the matrix basically in the matrix format. So what is your phi of t? Phi of t is Laplace inverse of si minus a, sorry, Laplace inverse of si minus a. So what is my si minus a? So Yeah, what is my E matrix here? If I write my E matrix x dot, it will be equals to A is equals to, this will be 0 1, this will be minus 6 minus 5. Huh. So I hope like x1 x2 dot, this will be x1 x2, and that's all. So this is my x1 x2 dot, x1 x2, and this is my state equation, right? This is my E matrix. So from this matrix I can, like, of course we can derive it from basics as well individually, what is x1 and x2, uh, but let's solve it using our method only, because mostly we will use this. So this will be equals to a Laplace inverse of si minus a inverse. So this will be s into I, s minus 1 6 s plus s plus 5. So inverse of this will be 1 by s into s plus 5 plus 6. This will be s plus 6 s 1 minus 6. Okay, so this is my uh, resolvent matrix. So I can calculate my state transition matrix by taking the inverse, Laplace inverse of this. So what I need to multiply x of 0. So I will not calculate this, right? First I will multiply x of 0 with this. Okay, so if I multiply x of 0, because x of 0, right, one of the row is 0 actually. First row is 0, it is 0 1, right? X of 1 is 0 and x of 2 is 1. So if I multiply with that, right, my calculation will be much simpler. Okay, s plus 5 1 minus 6, and then it is 5. Okay, so this will be equals to, yeah, this will be 1, then this will be minus 6, this is 0 5, that's all. It's 2 cross 2 into 2 cross 1, so it will be 2 cross 1. Yeah, so now it becomes much simpler, right? Your matrix becomes much simpler. So this will be s square 5s plus 6, that is basically s plus 3 into s plus s plus 2. So now you can easily write this. So this is your x1. Now I can take the Laplace inverse of this, correct? Before that, let me write this properly. S equals to minus 2. This will be 1 by s plus 2, s equals to minus 3 s plus 3, 1 5. Now I hope you can take the Laplace inverse of this. This will be e raised to power minus 2t minus e raised to power minus 3t, and the bottom would be e raised to power minus 2t, 5 into e raised to power minus 2t minus e raised to power minus 3t. That's all, right? This is your x1 of t, I have just taken the Laplace inverse, that's all. X1 of t, x2 of t, and we have to calculate x2 of 1. So x2 of 1 would be 5 e raised to power minus 2 minus e raised to power minus 3. So okay, this will be negative. Let me just quickly check. S equals to minus 2, s equals to minus 3, everything is correct. This, if we multiply, this signs will just change. Okay, this signs will just change, that's all, and this will get swapped. Oh sorry, I guess I'm doing something wrong here. Cofactor of this is s plus 5, cofactor of this is s. Hold on a second now. S plus 5, s6, if I take the transpose, it is correct only. It seems like I'm doing something, some sort of silly error. Minus 6 minus 5 0 1, it is 1. So multiply this, 0 times 1, this will be 0, this will be 1, this will be 0, this will be 5. I'm so sorry. I just figured out that this is not 5. This is S, right? This will happen in exam as well. So write down, mistake copy. Don't mistake S for 5. Please make sure you don't repeat this mistake. Don't write S for 5. So this will be actually S. I'm extremely sorry. This is S. So if I have S here, correct? If I have S here, right? This is so whatever is the Laplace transform here, and if I'm multiplying S, right, that means I have to differentiate this one, correct? Multiplication in S domain means differentiation in time domain. So if I differentiate this function, this will come out to be minus 2, and minus 3 into minus will come out to be plus 3. That's all. So this will be minus 2 plus 3. Everything is same, just it was minus 2 and plus 3, just a small minor, not a minor actually, it's a big mistake, but that's fine. So yeah, this into minus 2, then plus this raised to over 3 into 3. Yeah, it comes out to be 0.12212. That is what we are expecting, but I was not getting the same answer. So of course we are making some calculation mistake. So in your exam as well, you can make some calculation mistake. So just be very careful regarding this. Let's solve the next question. So this system is shown, and it is asking us that current IL of t in the inductor, voltage and VAC of t across the capacitor are taken as state variables, both assumed to be initially they are 0. Then it is completely controllable, observable. What is it? Correct. So it's very simple, right? It's very simple. So just first of all, let us form the state equations. So I see my VO is the output voltage and input is the source current. So let me first of all write the state equations, then I will form the output equation. So yeah, we can write, what can we do? So this voltage is VC, right? So this current would be what? VC by T. So VC by 1 ohm, that is VC only, correct? So here current flowing is VC, right? VC by 1 is VC. This is the amount of current flowing through here. And what is the current incoming? This is IL current that is incoming, right? So some current would be outgoing here as well, or maybe I can write some current is incoming here as well in this, because IS current is incoming from here. What is the value of this current? The value of this current would be IS minus IL. IS minus IL, right? IS current is incoming, IL current is outgoing, so this is the IS minus IL. That's all. That is the thing that we require. That's all. Okay. So, yep. So what I can do here is let me make it okay. Yeah, let me write the equations actually. So okay, what next can I do? what next can I do? This is ILs minus IL. So first of all, let me write out the output equation. It is the simplest one. So VO is equals to simply VC of t. V of t equals to VC of t. So that is my output equation. That's all. I don't have any input, right? My output is directly connected across the capacitor voltage, right? So yeah, I can directly say that I can directly see the uh, input, correct? Okay. Now out of this, right, what is my C matrix? So C has to be a, so I can assume my state matrix, right, X to be VC IL, correct? So C would be, this will be C into VC into VCIL, right? So in the C element, right, the first element would be 1, second element would be 0 because it is not a function of IL. So 1 comma 0. So that is my C matrix. My D matrix is 0. So anyways, whenever we discuss about state controllability, observability, nowhere I have mentioned D in the formula, right? So all of the places we have assumed that D to be 0. Now what about A and B? That is interesting. So how can I write my input as a function of output and state variables? Okay, that is interesting. Okay, we can write, can I write, yeah. So what is the current that is going into the capacitor? That is C dVc by dt, right? I is equals to C dVc by dt, that is C into Vc dot, that is equals to that, right? This is the total outgoing current and these are the incoming currents, right? So incoming current will be equals to outgoing currents. So outgoing current is C Vc dot plus Vc in this resistor equals to incoming current IL plus this current. What is this current? It is Is minus IL. That's all. Is minus IL. It is simpler actually because whatever current will come, right? What is it? Is. The same current should come out of this, right? Correct. That is the property that we have learned in networks. So actually, this will be cancelled. Only Is will be left out. So basically, my Vc dot and C is 1 farad. Vc dot will be equals to minus Vc plus Is. That's all. That is what my Vc dot is equals to. What about my IL dot? Okay, for IL dot, what we can do? For IL dot, we can actually calculate the key wheel in this loop. Okay, so VL is what? VL is this into Is minus IL. VL is Is minus IL into 1 ohm basically because they are connected in parallel. So VL is nothing but L dIL by dt and L is 1. So it will be IL dot will be equals to minus OS. So yep, IL dot will be equals to minus IL plus Is. So yeah, now we can actually form the state variable, right? That is Vc dot into IL dot will be equals to minus 1, this will be 0, this will be 0 minus 1 into your state variable, okay, Vc into IL. I don't feel this is like okay, we will see, is this controllable, observable or what, plus this will be Is, this is also plus Is, this is also plus Is, that is 1 1 into Is. So this is my B matrix, this is my A matrix and this is my what did it go, this is my C matrix, right? So for controllability, what do we check? For controllability, if you remember, we write QC, right? If I write QC, then of course C will be involved. So not C will be, B will be, C is already used here, so C will not be there, B will be involved, right? Because we're checking the controllability with respect to the input, with respect to the input. So first I will have B, correct? Then I will have not A transpose, sorry, A into B, right? Because then only the matrix multiplication will be valid, otherwise matrix multiplication is not valid, and I have to go till the second point only because it is a 2 cross 2 matrix, right? You can try B cross A, but it will not work because B has a dimension 2 cross 1 and A has a dimension of 2 cross 2. So its number of columns is not equals to number of rows. So matrix multiplication is not valid. So you have to write A cross B only. So this will be B is supposed to be 1 1 into AB. AB will be minus 1 into 1, that is minus 1, and this is 0, this is minus 1 into 1 minus 1. Okay, so here I see, of course it is not a full rank matrix because determinant of QC is simply 0, right? So it is not controllable. What about the observability? Let us check the observability. So if I check the observability QB, here first of all I will write, we will have to write C transpose because C itself is a row matrix, right? So I have to write C transpose. C transpose. Now again you cannot do C transpose into A transpose, right? You have to do A transpose into C transpose. Only this matrix multiplication is valid, correct? The other things are definitely not valid. I hope that point is clear by you. Okay, so yeah, that's how, like I've already told you how to remember these things, right? So yeah, let's solve this. So if I solve this, right, A transpose into C, C transpose is what it is, 1 0, and A transpose would be minus 1 0 into minus 1 0. Okay, it is, if I do minus, yeah, it is same only. A transpose is same as A, so minus 1 into C transpose, minus 1 into 1, that is 1 minus 1, sorry, and this into 0 would be 0, that row will be completely 0. Again we're observing, again determinant of QB is equal to 0, so it is neither controllable nor observable. Okay, so option A would be correct in this case. Sorry, not A, sorry, neither state controllable nor observable. Option D, option D will be the correct answer for this question. Let's solve the next question. We have been given a state space representation for the first order equation where x state variable u is the control input. Why is this? Let u be equals to minus kx, okay, using some controller, and k is the controller gain. Then to place the closed loop pole at minus 2, what shall be the value of k? Currently, what is the location of closed loop pole? Do you know? So I know my x dot is equals to a into x into u. So in this case, it is a first order equation. So a will be 1 cross 1. A is a 1 cross 1. It is simply an element. What is the value of a? That is minus 1, right? What will be the location of my poles? It will be Si minus A inverse, right? Si, I is 1 cross 1, right? So it is simply S into 1 minus A. A is minus 1 inverse. So it is equals to 1 by S plus 1. Currently, this is my transfer function. And of course, sorry, not my transfer function, sorry. Like I have to multiply C also and B also, that is there, but don't worry. C and B, right? But don't worry for now. For now, you just worry about this, that I see the pole location here is S equal to minus 1. C and B will not provide any pole, right? Pole are determined by the eigenvalues of A, that is minus 1. Currently, the pole location is minus 1, but I want to place it at minus 2, further away from the origin. So, what do I need to do? Simply just change the equation, right? X dot will be equals to minus k plus minus k into x, because u is minus kx. So x dot is equals to minus 1 plus k into x. So right now my a becomes minus 1 plus k, and your uh, si minus a, right? like basically your location of pole will be negative of this, right, minus of lambda, like, so it will be 1 plus k. So I have to move my pole location, sorry, this will be minus 1 plus k, right, that is my lambda basically. So I have to move my pole location at minus 2, right, lambda should be minus 2, so k would be equals to 1, that's all. That is your answer, right? So of course there is this thing, like I have solved you, like what happens, like actually what is happening, we're providing a feedback with the control gain in the block diagram, but that is not of any use to us. Ultimately solve it using the equations and you're done. K is equals to 1, you're done with the answer. Move on to the next question. So k equals to 1 is the answer for this question. Let's move on to the next one. Like here we have done multiple things regarding output controllability, but we don't have to worry about it, so we can ignore it. So because I feel they will not ask regarding output controllability, they will basically ask controllability and observability normal. So the state equation of a second order system, so it's a second order system, that means there are two state variables, correct, there are two state variables. So if there are two state variables, then they have also told us that there are, like, after these two state variables there are two eigenvalues, lambda 1 and lambda 2, distinct, they are distinct. So basically your eigenvectors are independent. So for alpha 1 alpha 2 become constants, the solution x of t of the equation would be where x of 0 is the initial condition. So I know they are only discussing about the natural response, right? They are not discussing about the forced response because no input has been given to us. So I know the solution x of t is actually equals to phi of t into x of 0, correct, phi of t into x of 0, right. So now what we can do is we can actually calculate few values. So what is my x of 0? X of 0, right, will be simply combination of my, because x of 0 is, they have told me that lambda 1 and lambda 2 are distinct, two distinct eigenvectors of A. So x of 0 would be basically some lambda 1 into v1, sorry, e raised to power, sorry, some constant c1 into v1 plus some another constant c2 into v2. Basically it will be combination of the two eigenvectors, constant c1 plus c2. This has to be valid, right, because A has two linearly independent eigenvectors. So I can write my x in terms of v1 and v2. Now if v1 and v2 are my eigenvectors, then I can say that A into lambda I will be equals to lambda I into vi, correct. Now eigenvector of A is vi. So what is the eigenvector of e raised to power a t, right? Eigenvector of e raised to power a t, right, will be simply, sorry, eigenvector will not change, eigenvector remains same. What will change? Eigenvalues will change. It will be e raised to power lambda I t, that's all. I hope you remember, right? If I'm taking the exponential, the eigenvector remains the same, eigenvalue changes. This we have discussed in the linear algebra. So we will just do this, correct. So basically, right, what is phi of t? Phi of t is e raised to power a t. How can you remember it? Simply, what is phi of t? It is the inverse Laplace si minus a. So it will be simply inverse Laplace of this, correct. So if I assume it to be 1 cross 1, it will be inverse of s minus a, Laplace inverse of s minus a. That is nothing but yeah, that's all right. So this will be e raised to power at, that's all. So that is what we will do, right. So my x of 0 is this c1 into v1 into c2. Now what is my phi of t? Phi of t is this, right, e raised to power at. So phi of t into, yeah, e raised to power at into lambda, lambda will be this only, right. So this is, sorry, what I'm doing, this is the eigen, I have to multiply the eigenvector, right, vi eigenvector will not change, this will change, sorry, so what am I doing, okay. So yeah, now we will replace our uh, v1 and v2 from here, right? So yeah, that is what we can do. So c1 into v1, right? Okay, so what is that? So what is my x of t? It will be c1 like e raised to power at into c1 v1 plus c2 v2. So it is equals to c1 into e raised to power at v1 plus c2 into e raised to power at v2. Okay, now what we can say is, what is e raised to power 80 into v1? So e raised to power 80, if I put here I equals to 1, e raised to power 80 into v1, that will be e raised to power lambda 1 t into v1. So this is nothing but c1 into e raised to power lambda 1 t into v1. Similarly, this will be c2 into e raised to power lambda 2 into v2. So now it becomes very simple. So this is just a, like c1 c2 are just constant, so I can write them c I summation I is 1 to 2 e raised to power lambda I vi. So which is present in, I guess, in option A, right? Option A. So instead of C they have written alpha, so I guess there should not be much of a difference. Both of them are telling us the same thing. So option A will be the correct answer for this question. Let's move on to the next one. Consider the state space description of the LTI system with matrices as shown. For the input sin omega t, omega greater than 0, the value of omega for which the steady state output of the system will be 0. Okay, for which the steady state output of the system will be 0. Okay, so for the input sin omega t, omega greater than 0, okay, steady state output will be 0 for the input this. So basically, right, when the output will be 0 for a particular input, what we have to do, we have to calculate the transfer function. Okay, we have to calculate the transfer function, and after calculating the transfer function, if I put s equal to j omega, and for that magnitude it goes to 0, whenever that magnitude will be 0, that means simply there will, even though there is some finite input, I will have no output. Because what happens, what do we do with the input sinusoid? We multiply the magnitude of my transfer function at that particular frequency, and of course add the phase of the transfer function, correct? So yeah, that's all. So that is what I can calculate. So remember here my d is not 0. So first time I guess they have given that d is not 0. So how do you remember the transfer function? One thing you can do, if you don't remember, right, like I know it is c into si minus a inverse into b, but what about d? I remember it without d. Don't worry, if you don't remember for d, right, we can derive it. So what are my equations? X dot equals to x a into x plus u, y equals to c into x plus d into u. Sorry, this will be b into u. So from here I can write my u of s will be equals to, hold on a second, so s into x of s, remember transfer function, no initial conditions, a into x of s plus b into u of s, right? So from here I can directly write what is my x of s. X of s is equals to b by si minus a, right, into u of s. So I can replace it over here, right? This is nothing but b into, so actually this, right, is placed here. So don't you mess up with the matrix multiplication, because that will be important for you. Now I will multiply by si minus a inverse on both sides. So x of s will be equals to si minus a inverse into b into u of s. Now what will be my y of s? Y of s will be c into x. X is this si minus A inverse into B into U of S plus D into U of S. So basically your transfer function Y of S upon U of S is C into Si minus A inverse into B plus D into U of S. Okay, so yeah, so uh, yep. So now we can, yeah, this U of S will be go there. So now you can directly say what is your expression for the transfer function. What is the expression for the transfer function? So like you can either write it directly or derive it. So we have derived it. So now we will solve basically. So what is your C? C is 3 minus 2, right? Now Si minus A inverse, right? Let me not write this. Let me write ABCD for now into B. B is 0, 1. It will simplify our calculations just a bit, not by a greater amount, just a bit. Plus D. D is nothing but 1. D is simply 1. Okay, this is my transfer function. So this will be A into 0 plus B, that is B only, into 1, and C into 0 plus D, that is D only. So this plus 1, this will be equals to 3b minus 2d plus 1. This is my transfer function. For B and D, of course I will calculate what is my B and D. So Si minus A inverse is my ABCD. Okay, so Si minus A inverse. So what is A? Is 0, 1, minus 1, minus 2. So this will be 0, 1, minus 1, minus 2. Yeah, this will be my Si minus A, and I have to take the inverse of this. So I have to swap the main diagonal elements and just change the sign of off diagonal elements. This calculating, this will be S into S plus 2 plus 1. Okay, so this will be equals to, if I solve this, I just need to calculate B and D, that's all. I just need to calculate B and D. So this is S square plus 2S plus 1. This is nothing, S plus 1 whole square, right? This is nothing but S plus 1 whole square. Okay, so I have here, I just need to calculate B and D, that's all, right? So what is B? B would be basically this element and this element, correct? That is my B and D. So this would be 1 divided by S plus 1 whole square, and it will be S divided by S plus 1 whole square. Now I know what is S plus 1 whole square. So what is the Laplace? Okay, I don't even need to calculate the Laplace inverse, right? All I need is just this value, just the transfer function, that's all, right? I don't even need to calculate the inverse, Laplace inverse. So this is my B and this is my D. So it is 3 into B, 3B S plus 1 minus 2 into D, 2 into S divided by S plus 1 whole square. Then I have plus of 1, right? So it will be basically 3 minus 2S plus 1 upon plus S plus 1 whole square upon S plus 1 whole square, that's all. So simply what you can do is you can put s equal to j omega. Omega is supposed to be omega only. Okay, so they are asking you what is the value of omega. So basically for what value of omega, this is my transfer function, this will go to 0. Basically I have to put t of j omega, right? If I put here j omega is equal to j omega, let me put s equal to j omega, this will be 3 minus 2 j omega. Transfer function, either you can write magnitude equal to 0 or your overall transfer function is totally 0. That also would work here. So 3, yeah, 3 minus 2s 2 j omega plus j omega plus 1. Actually what I can do is I can keep this separately, that will be easier for me, right? This plus 1, I will tell you just in a second why. There will be less amount of calculations. J omega plus 1 whole square, right, plus 1. So this would be, what I can do is if I square on both sides, this will be 3 minus 2 j omega upon minus omega square plus 1 plus 2 j omega plus 1. This would be okay, if I put here omega square 1 minus omega square 3 minus 2 j omega, okay, this would be 3 minus, I can use the what can I use? I can use bit of rationalization. So this will be 1 minus omega square minus 2 j omega, and this will be totally real, right? Okay, so I have to make the imaginary part, I have to make, actually basically make the real and imaginary parts, both of them to be 0, right? Okay, so this is becoming bit lengthy. Okay, sorry, actually this, okay, sorry, this would have been even simpler actually. Let me keep the denominator as is. Actually if I add a 1 here, right, if I add 1, it will be simplified actually. So if I add 1, this will be s square plus 2s plus 1. So 2s and minus 2s will be cancelled. S square plus 1. So this will be s square plus 4 basically, right? And this is whole square. So this will be minus omega square plus 4 upon this. Okay. So the overall, this is totally real, right? So of course this has to be 0, right? So basically your omega square has to be 4. But basically your minus omega square plus 4 has to be equals to 0. So your omega is equals to 2, right? Because your transfer function must be 0, because the gain has to be 0. That's why this term has to be 0. That's why your omega will be simply 2. That's all. Omega will be 2 radian per second. That is your answer. Okay. It was a bit lengthy, I do agree. But I tried to reduce the calculations as much as possible. Let's solve the next question. Consider the state space representation of a system. Okay, this is the state space representation of a system where x is the state vector, u is the input, a is the system matrix, and b is the input matrix. Okay, x is the state vector, use, and these are the like the standard things. Consider the system matrix A from the following options such that the system has a pole at the origin. So they are telling me that the system has a pole at the origin. That basically means I have to find out, either you can calculate the location of the lambda eigenvalues, because eigenvalues of system matrix discusses about the poles, right, of the system. So how can I calculate? So we know whenever we have a pole at origin, that means one of the eigenvalue will be lambda will be, one of the lambda will be 0. That means your product of eigenvalues will be 0. That means your determinant of A will be 0. So in the first case, I see determinant is coming out to be non-zero. It is non-zero, right, in the first case. In the second case, determinant is actually coming out to be 0. Okay, it is 0. In the Third case, if I see minus 3 and this is minus 3, it is coming out to be non-zero. In the final case as well, it is coming out to be non-zero. So of course, only one of them is the possible answer, because if one of the eigenvalues is 0, then that means the product of all the eigenvalues will be 0. That means determinant has to be 0. It has to be. That means option B will be my correct answer. That's how you can solve this question in a quick manner. Let's solve the next question. So consider a system S represented by this in the state space. Which of the following state space representation given below has slash have the same transfer function as that of S? Which of the following? Okay, it has the same transfer function, right? So unfortunately there is no other option, because I was asked like during 2024 that is there any option to calculate this transfer function like with any shortcut, right? So one thing is you just identify the eigenvalues and you match the eigenvalues, but that also will take some time. Okay, calculating the eigenvalues also will take some time. If the eigenvalues are same, then also the pole look, then also the transfer function can be different, because eigenvalue can only discusses regarding the pole of the transfer function, but my transfer function consists of both numerator and denominator. So for the transfer function to be same, both the numerator and denominator must be same. So we have no other option but to calculate the transfer function of each of the options. So in the first case, what is the transfer function? So I hope you remember the formula of transfer function Si minus A inverse into B. So in the first case, it would be C is 1 2. This would be Si minus A, right? So S minus A 2 S plus 3 into B. So B is okay. Let me first of all obviously calculate the transfer function here, right? So it is C into Si minus A inverse, that is S2 minus 1 S plus 3 inverse, don't forget here of inverse, into B, right? 1 0. So actually okay, let me write this ABCD. If I write ABCD, right, this would be A upon C, that's all. So basically if I convert this matrix into ABCD format, that will be easier for me, correct? Yep. So yeah, this will be 2 minus 5. 2a minus 5c. Okay, so this will be my answer, basically transfer function. So what is A and C that I have to calculate? So just I just reduce my calculations, that's all. Okay, so what is the inverse of this? S plus 3s minus 2 1. Okay, so yeah, that's all. And of course don't forget to divide by the S plus 3 into S plus 2. So yep. Now uh, what we will do is we will actually we will calculate these values, right? Okay. uh, so this will be s square plus 3s plus 2, that is s plus 2 into s plus 1. So quite, this is like quite lengthy. This question is like super lengthy. Okay. Okay, so hmm, if I calculate this, s plus 2 into s plus 1, remember this is also s, right? Don't forget this is s. Okay, otherwise again I will do some mess up, right? Okay. Okay. 2 into, so your answer is minus 2a by 5. Okay, this should not be the case, right? Hold on a second. So what am I doing? What am I doing? Your transfer function is 2a minus 5c. That's all. Correct. Your transfer function is 2a minus 5c. So if I calculate this value, so 2 into a, right? So a would be your minus 2. So minus 4 upon whatever this value is, s plus 3. So that is s square, basically s plus 2 into s plus 1, and minus 5 into c. 5 into c, minus 5 into c, minus 5 into c, right? So c is s, so minus 5s. Okay, so this comes out to be minus 5 into s, but I believe maybe I'm doing some sort of mistake. Okay, let me just you can just fast forward it. I will just calculate this in a quick manner. It seems like I'm making some sort of mistake. Okay, I'll do this in a good manner actually, otherwise I'll just mess it up. Okay, so what is the transfer function? It is c into si minus a inverse into b. That's all. There is no d here, d is 0. So transfer function, let me write this c as 2 comma minus 5. Psi minus a inverse. Okay, let me write this as a b c d for now, and b is 1 comma 0. That's all. Just give me 1 second. Yeah, now this would be 2 minus 5 a, and this will be c. So your final transfer function would be 2a minus 5c. That's all, right? So I just need to calculate this abcd, that is nothing but my si minus a inverse. So it would be s minus a, that is plus 2, this will be minus 1, this will be s plus 3 actually. Great. And inverse, so this would be 1 by s into s plus 3 plus 2, s plus 3, swap the main diagonal elements, change the sign of the off diagonal elements. So from this you can directly say what is your a. So your a would be, your a would be s plus 3 upon s plus 2 into s plus 1. Okay, and your c would be equals to minus 5. So c, right, c is basically, okay, okay, c, I was wrong here. C was actually this, right? 1 plus s plus 2 into s plus, yeah, that is where I was making the mistake. That's why we should do things a bit slowly. So this is my c basically. So now yeah, my answer would be 2a minus 5c, right? 2a would be 2s plus 6 minus 5c would be 5. Okay, signs are all, signs and all are fine. Yep, signs and everything is fine. So if I subtract this, right, uh, give me a second. So yeah, so your final transfer function comes out to be this upon s plus 2. So just let me just properly write it, s square plus 3s plus 2. So your final transfer function comes out to be 2s plus 1. There is actually no shortcut that I know of, certainly, that which you can solve. So again we have to go for option A and calculate the transfer function for option A. So these kind of questions you should solve at the end, because this question is very lengthy. Okay, these kind of questions you should solve at the end. So what is the transfer function for option A? So this would be dx upon dt, that is equals to uh, so the what is my a, b, so b is this 0 comma 1, right? C into si minus a inverse into b, right? So again I will have a b c d, this will be my c, right? Again if I solve, this would be equals to b and d, right, into 1 comma 2. So here the solution would be b plus 2d. This will be a solution for the transfer function. So again now let me calculate the b and d elements, right? So it will be si minus a inverse, so s I minus a inverse, this would be 1 by s into s plus 3, s plus 3 plus 2. Then this would be, I can swap the main diagonal elements and I can change the sign of the off diagonal elements. So it seems it is b plus d, right? So this time b and d are this, b into 2d. So it is 1 plus 2s upon the same denominator. So denominator and the numerator are same. So option A matches. Okay, so option A, the transfer function is same. So option A is one of the correct answers. Have they asked which of the following has have? Okay, so there can be multiple actually, unfortunately. So we have to solve for option B as well, right? Again I have to copy and paste it for option B. So this would be dx upon dt, correct, dx upon dt. So we can solve it. Again, c 0 to, this will be a b c d, this will be mm, c a b c d into b, b is 1 comma 0, so this would be a into this 0. So basically only copying the first column, this would be a and c, this would be 0 into 2, that is 2c, right? So 2c is my answer in this case, and I see that the this a matrix is same as the previous a matrix, right? And if I've already calculated, right, I've already calculated, that is a shortcut basically. For this I've already calculated the inverse, I think. Yeah, this a matrix is same here, it is not same here, so something will be different. But what do I see is, for this, right, my elements, I just need to calculate the, I just need to find out the c element, right? What is c? C is minus 2. So your answer actually is minus 4 upon, denominator is same, denominator will not change, s square plus 3s plus 2, which does not match. So definitely option B is incorrect. Let us calculate for option C. So in option C we see that the A matrix has completely changed. So unfortunately we have to again calculate, but what do you observe? This and this are same, right? So ultimately again our work will be divided. So actually you just need to calculate 2 transfer functions. You don't need to calculate 3 transfer functions. So they will always give you some option, right, of flexibility. You will feel that question is written in the, no. If you are smart enough, you will be able to decode exactly which things you need to calculate, and rest automatically will take care of itself. So this will be equals to dx upon dt minus 1 0 2 0 2 minus 2. Okay, right? So yeah, minus 1 minus 2 minus 1 3. So yeah, this would be, if I solve it again, c is 1 comma 1. Actually this, right, unfortunately we will not be able to do something because here elements are not 0. Okay, that is a disadvantage. Elements are not 0, but I think this calculation of this will be much easier. So your final answer, right, this will be minus a, this will be very difficult. Okay, but let us do it anyways. So 1 comma 1, so 1 cross 2, this will be a into minus a plus 3b, this will be minus c plus 3d, and ultimately your answer will come out to be minus a plus 3b plus 3, sorry, minus c plus 3d. Okay, so yep, so now this would be si minus a inverse. So s plus 1 0 s plus 2, inverse of this is very easy. It is very simple, right? Because it is a diagonal matrix, and inverse of a diagonal matrix is nothing but just the inverse of each element. That's it. Okay, that's how simple it is. Inverse of diagonal matrix is very simple to calculate. This will be s plus 1, this will be 0, this will be 0, this will be 1 by s plus 2. That's all. So yeah, things are easy actually, because your element element b and c are 0. So this is 0. So ultimately your answer will come out to be minus a, that is minus s plus 1 plus 3 into d, that is 1 plus s plus 2. So this would be equals to minus s minus 2 plus 3s plus 3 upon s square plus 3s plus 2. So this would be equals to 2s plus 1 upon 3s plus 2. Okay, so is it same here? 2s plus 1, s square plus 3s plus 2. Yes, it is same. Yes, it is same, right? Because our original transfer function was this only. So luckily it is same. Similarly, you can calculate for the final one as well. You are lucky because in the final one your A matrix is same, just your B and C are changing. So it will be very simpler for you. Let me just put it here. I think some airplane is going above, so let's just pause for a second. Yeah, so you see that A matrix is same, right? Just as the previous case. So A matrix is same. What is changing? Your C matrix and your B matrix. So this would be equals to minus 1 0 0 minus 2 into 1 1. This would be equals to, sorry, this would be ABCD, correct? Because here I have SI minus A inverse. So this would be 1 2. This would be A plus B. This would be C plus D. Okay, so 1 plus 1 plus 2D, right? So it is A plus B plus 2C plus 2D. Right, now we can solve this. If I solve this here, this would be so what is my ABCD again? ABCD is same, right? ABCD is same as the previous case. So in the previous case, C and B were 0. So C and B are 0. So ultimately it comes out to be A plus 2D, and A is 1 by S plus 1 and D is 1 by S plus 2. So it will be 1 by S plus 1 plus 2 by S plus 2. So this would be equals to S plus 2 plus 2S plus 2, right? S plus 2 plus 2S plus 2, that is S square plus 3S plus 2. So actually it is something else, right? It is not equal. So D is incorrect. So option A and C will be correct here. Both of them are matching. So actually, yeah, I do agree. It is lengthy, but at least you only have to calculate 3 transfer functions. This one, and this one. Okay. And this as well, if you observe it carefully, it is like transpose, right? So there will be some similarities, but don't need to go into that. Just you have to calculate 3 transfer functions, not 5, because 4 for these and 1 for this. No, you can simplify this thing. Let's go into the next question, this one, right? So consider a system x1 of t, x2 of t, x3 of t are 3 internal state signals, and u of t is the input signal. The differential equations governing it is this: the signals x1 t, x2 of t are bounded. So basically, right, the signals x1 t, x2 t, x3 t are bounded for all bounded inputs. There exists a bounded input such that at least one of the signals x1 t, x2 of t, x3 of t is unbounded. There exist. Okay, so how will you solve this? So what you can do, you can so they are discussing about the x1, they are discussing about the state variables and regarding the inputs. So let me write just the state, because they have only given me the state equation, they have not given me the output equation. So just let me write the state equations, right? So what is the first state equation? X1 dot is equals to 2 into x1 plus u, that's all, right? Now for any bounded input, my x1 will be stable. Basically, it will be bounded, right? How can I understand it? Simply what you can do, you can calculate the response x1 of s upon u of s. So for any bounded input, my x1 of s also will be bounded. That means the poles of this transfer function should all lie on the left hand side of j omega axis of the s plane. So let us calculate that. So of course we are talking about transfer functions. So initial conditions will be assumed to be 0. So if I see here, this will be s into x1 of s, that is equals to 2 into x1 of s plus u of s, correct? So this will be x1 of s into s minus 2 equals to u of s. So I can see this transfer function is equals to 1 upon s minus 2. So one of the pole is lying on the right hand side. So even for bounded input, output will be unbounded. So actually x1 of t, this statement is first of all incorrect. The signals x1 of t, x2 of 3, x3 of t are all bounded for all bounded inputs. This statement is absolutely incorrect, not correct, right? Because I can see, of course, for a bounded input here, right? Because the poles are lying on the right hand side, so output will go unbounded. Unbounded. Basically, x1 can go unbounded. What about the let me calculate for all of them. So for this one, right, what will happen? Similarly, if we solve for this one, x2 dot will be equals to minus 2x2 plus u. So actually here, your x2 of s upon u of s, if you calculate, of course, your initial conditions are 0. Here, the pole comes out to be on the left hand side. So actually, for bounded input, right, if u of s is bounded, then x2 of s also will be bounded. So for bounded input, x2 of s also will be bounded, right? So there exists a bounded input such that at least one of the signals is unbounded. This statement seems correct, right? Because I see that at least one x1 is unbounded. For a bounded input, x1 goes unbounded, but x2 is bounded, right? So at least one of them is unbounded. This statement seems correct. There exists input such that the signals x1 to x2 of d, x3 of t are unbounded. There exists input signal. No, because if my input is bounded, right, x2 of t will always be bounded because all the poles are on the left hand side. So this statement is incorrect. The signals x1 of t, x2 of t and x3 of t are unbounded for all bounded inputs. Again incorrect, because x2 of t is bounded for a bounded input. It is not unbounded. x1 of t is definitely unbounded for a bounded input because the poles are on the right hand side of my s plane. So option B is correct, but let's of course derive it for the third one as well, x3 of t, right? If I say for x3 of 3, it is simply 0, right? So x3 of s is equals to, so simply your x3 dot of t is equals to 0 into x3, that is 0 only, plus u of t, correct? Now if I calculate the Laplace transform of this will be s into x3 of s equals to u of s. So x3 of s will be equals to u of s upon s. So basically your transfer function is 1 upon s. In this case, right, your system is marginally stable or it is unstable, because if you have a pole at the origin, right, if you have a single pole at the origin, it is not marginally stable, it is unstable. Simply, if you have a pole at the origin, it is unstable. Okay, if you have a pole at the origin, it is unstable. How can you verify it? Simply what you do, if you provide your input u of s to be unit step, so it will be 1 by s. So your x3 of s is actually 1 by s square, which is simply nothing but t, correct? So basically, right, tut in the time domain. So for a bounded input, for a step input, my output is going to unbounded. It is t into ut, correct? So that's all. That is the thing, right? So yeah, statement B will be correct in this question. Let's solve it for the next question. Consider the state space model. Consider the state space model. X dot of t equals to a into xt plus b into rt. Yt equals to c into xt and abc are given. The sum of the magnitudes of the poles is. So they are not asking me the sum of the poles. The sum of the poles will be simply sum of the eigenvalues, which is nothing but the trace, correct? That's very simple. But here they are asking me the sum of the magnitude of the pole locations. For that, I just simply need to calculate the poles, right? What will be my pole location? Pole location would be si minus a inverse, right? That's all. And the denominator of that, right? That's all. Or you can simply write the characteristic equation, that is lambda square minus trace of a, that is 3 lambda, plus determinant of a, that is 2, equals to 0. From this I can calculate the lambda. Lambda is 1 comma 2, right? Yes, 1 comma 2. So this would be basically lambda is 1 comma 2. So this would be basically so what is the sum of the magnitude of the poles? Hold on a second. Lambda comes out to be, so this lambda is minus 1 comma minus 2, right? Minus 1 comma minus 2. Don't make this mistake. Yeah, minus 1 comma minus 2. That's all. It to be negative, right? Because the sum of the uh, eigenvalues would be equals to trace of a, that is minus 3. Okay, like you can solve this equation. I hope I don't need to explain here much. So lambda is minus 1 comma minus 2. So ultimately your sum of magnitudes of pole will be magnitude of lambda 1 plus magnitude of lambda 2. So that is equals to magnitude of minus 1 plus magnitude of minus 2. That would be equals to 1 plus 2, that is equals to 3. That's all. So 3 is your answer for this question. Okay, with that we are finished with state space. Now we will move on to controllers and compensators. Let's begin with controllers and compensators. So basically there are two things. One is controller, another one is compensators, and there are very small things, right? Few things you have to keep in mind, that's it. Don't study it as a new chapter, just study it as a topic, that's all, as a new topic. So what is controller? Don't worry, we will use basics only. Mostly we will use basics. 1-2 things I will tell you to remember, that's all. What is a controller? Controller is a device uh, connected in the forward path of a plant to improve the transient and steady state performance of the system as per requirement. Okay, so it is a device that will be connected here that will improve the overall steady state performance of the output. So basically we receive some error signal at the input side, right? And then we do something with the error signal. You want the temperature of your room to be at 24 degrees, outside the temperature is 26 degrees, right? So there is an error of 2 degrees, right? How fast you want to move to your true value, desired value, that will depend on the controller. So your steady state response depends on the controller. Simply it is nothing but a block with a transfer function. It will have some transfer function, like let's say it will be kp, which is known as proportional controller. It will be some ki by s, which is known as a integral controller, right? And then it can be known as kd into s, right, which is known as a derivative controller. So it differentiates the error signal. If it integrates the error signal, it will be called as a pi controller, right? Generally we don't just use I, we use pi. So kp plus ki by s, or kp plus kd into s. Okay, so pd controller, pi controller, it is nothing but simply it does the derivative of the input error signal, or it will take the integration of the error signal, or it will write the proportionality constant of the error signal. So these are the things basically, right? That's all. That is what my controller is. Ultimately your controller will be a function of s, and you need to solve the whole transfer function or loop, you have to find out the loop gain. You might have to find out few parameters like frequency domain parameters. We'll discuss about those, right? What is your bandwidth? What is your resonant frequency, right? I have discussed regarding this, I think, in the uh, polar plot, right? What is my resonant frequency? Okay, I think I have not. Okay, I think I have discussed this, right? Yeah, what is my in the polar plot, in the frequency response, I have discussed regarding this, right? How to calculate all these things, how to calculate the peak resonant, how to calculate the cutoff frequency, all these things I have discussed, right? So here we will just revise those formulas and we will use this. So I hope you remember the time domain parameters of in the frequency domain, right? Division of time domain and frequency domain parameters. So these are my frequency domain parameters. Now, do you remember what happens at this particular frequency? At this particular frequency, we receive resonance. Resonance meaning our gain of the transfer function is infinity. Resonant, this is the resonant condition, right? So, in resonance condition, the gain becomes infinity if my zeta is 0, right? If there is no damping present, it will become infinity. If there is some damping, then of course we will get some peak, because this will be the maximum amplitude of my transfer function at resonance. We know at resonance we get the maximum power, maximum current, maximum voltage, something like that, right? Not for all the cases. If it's a series circuit, at resonance across the capacitor or the inductor, we'll get the maximum voltage. If it is parallel resonance RLC, then we'll get the maximum current, right? We'll get something maximum, correct? So basically the amplitude of my transfer function will be highest. Of course, zeta has to be non-zero. If zeta is 0, then the function will blow up, that we have discussed in the frequency response already. Okay. So yeah, this was the thing. These were few parameters. So basically what they will do, they will give you some controller, right? And they will tell you that for a PI controller, what will be the resonant frequency? Or let's say previously the resonant frequency was this. Now the resonant frequency has become 4. What will be the parameters Kp and Ki for this particular condition? Right? Simply you have to solve the question. That's it, right? Nothing new. So a few things that we want to revise. That when does resonance occur? Resonance occurs only if my system is underdamped and my zeta lies between 0 to 1 by root 2. Otherwise this formula of resonance won't be valid. Okay, otherwise this under root will be negative, correct? Now there is a formula for peak resonant formula, right? Peak resonant, okay, that is the gain of the transfer function, right? The amplitude of the sorry, this is not the gain, sorry, it is the amplitude of the response to a sinusoidal input, right, which will be maximum. So MR will be equals to KCL upon sine 2 theta, right? I hope you remember what is sine 2 theta. Sine 2 theta is simply nothing but sine theta 2 sine theta cos theta, correct? And I know what is my cos theta, it is zeta. What is sine theta? Sine theta is 1 minus zeta square under root. So it is simply 2 into zeta into 1 minus zeta square under root into KCL. So generally people tell you to remember this formula, but if you don't want to remember this formula, just remember this one. This should be enough, right? So this I'm just revising because we have already learned this in the second order frequency response, correct? Cutoff frequency. The frequency at which the magnitude response will be 1 by root 2 times of the DC value. This again is a very big formula. Unfortunately, there is no other option but for you to remember. Like you can remember it like this. It is very similar to my resonant frequency, right? Resonant frequency was omega r was equals to omega n 1 minus zeta square, 2 zeta square, correct? So in cutoff frequency, what we do is we write omega n, then we square this, right? We simply square this. So if I square this, it will be 1 minus 2 zeta square, right, plus then under root, again I will square the inside function, right? Inside function squared plus 1. That's all. Like it will, of course it will be very similar to my resonant frequency, but there will be few differences. Simply I will square it. So let's move on to few other parameters like cutoff rate. What is the cutoff rate? It is basically the derivative of the magnitude of my transfer function with respect to omega at omega equals to omega c. So you will calculate the omega c here. You will differentiate your transfer function magnitude. So let's say the magnitude of my transfer function is a very simple equation, just for the sake of it, right? Omega square, let's say 4 minus omega square upon 2 minus omega square, something like this, right? So you will differentiate, right? This is my, let's say, function of omega. So you will differentiate this with respect to omega, right? And then after that you will put omega equals to omega c. So that will give you the cutoff rate. Now let's come to the time domain parameters. How to remember the time domain parameters? I have already told you, right? All the parameters, whatever we have remembered, can be used, because they will tell you if the controller was not present, then the rise time was 2 seconds. But after including the controller, the performance improved. So rise time reduced. It became 1 second. So what is the parameter? Let's say Kp, Ki, all those parameters, right? So yeah, that's all basically. That's why you have to remember. How to remember the rise time? So if I have Tr here, right, then there cannot be, with R I cannot have omega n, I will have D. Basically there are two kinds of time, right? One is rise time and another one is the, if you remember, there was a what did it go, rise time was there, decay time. Yeah, two times over there, right? Decay time and rise time. So if I have D here, right, I cannot have omega D here, right? In the bottom I cannot have D, so I will have omega n. That's all. If I have omega n and zeta are very closely related, like zeta into omega n, right? So here I will have zeta. That's all. Zeta plus, I think it was 1 plus 0.7 zeta. I think that formula is also here. Where is the decay time? Yeah, so not what I'm doing, not the decay time, so delay time, right? Delay time, not the decay time. It is the delay time, right? What was the decay time? Decay time basically means have they shown, yeah, when the response, right, decays, that is my decay time. But that is not a parameter actually. The decay ratio is an important parameter, because when do we get the first peak? We get the first peak at pi by omega d. It is not that difficult to remember, right? Very easy to remember. What is the second peak? Second peak will be after every 2 pi, because it repeats with a period of 2 pi, and second peak obviously will be lower than the first peak, so it will be 3 pi upon omega d. Okay, right? Yep. So yeah, that's the thing basically. So here 3 pi upon omega d. Now yeah, that is the second peak, right? This is the first peak, and obviously the, if I see the decay ratio, decay ratio right, decay time, basically the first undershoot, right, would be 2 pi upon omega d. These are the few formulas, like first undershoot will be happening here, that is 2 pi upon omega d. You can calculate the period and all those things. Basically number of oscillations before settling, right? What will be the number of oscillations before settling? So this is my settling time, correct? T set. So how many oscillations will happen? How can I calculate that? So it will be, what are the period of oscillation? So each oscillations take how much time? It is T naught. What is T naught? T naught is 2 pi upon omega d. Well, omega d is the damped frequency of oscillation. So each oscillations takes T naught amount of time, and I am settling in T set, right? So it will be T, number of oscillations will be T set upon T naught. That's all. Number of oscillations would be T set upon T naught. Okay, that is my number of oscillations. That's all, right? Yeah, that's how we calculate these things. Maximum of peak overshoot, this formula also we have gone through very well. It comes out to be e raised to power minus cot theta. If it is not in percentage, if it is represented in percentage, it will be 100 percentage. Correct? Yeah, that's all. So yeah, if zeta, so there is many relations that you must keep in mind, right? So if your zeta increases, or let's say zeta reduces, right? If your zeta reduces, what happens to your theta? So my theta is here, right? So if your zeta reduces, right, zeta is equals to cos of theta. Zeta reducing meaning theta will increase. Zeta reducing meaning theta will increase. Correct? So if theta increases, what will happen? If theta increases, what will happen to cot of theta? It is actually pretty difficult to understand. So let me break it down. It will be cos theta upon sin theta. So if basically zeta reduces, your cos theta will reduce, right? Theta will increase, but your cos theta will reduce and your sin theta will increase. So actually your e raised to power cot theta will overall reduce, right? Cot theta will overall reduce. So it is e raised to power minus pi cot theta. So this term actually reduces, right? And I have a negative symbol. Previously it was e raised to power minus 0. Let's say pi. Now it has become e raised to power minus 0.5 pi, which will be larger. Obviously this one will be larger. So if zeta reduces, right, your maximum peak overshoot will increase. That's why they follow a inverse relation. Similarly for rise time also, you can actually calculate all these things. You can understand the relations. You can write your rise time, right, and then from that you can understand like what is happening. This is not pi upon omega d. Here there will be pi minus theta. So your normal period of oscillation is pi upon omega d. Sorry, not pi upon omega d, 2 pi upon omega d. Your peak time is pi upon omega d. So your rise time, of course, will be something lower than your peak time, because peak happens here, right, and rise happens when it goes from 10% to 90%, right? So that's how you can remember that your rise time will be something less than your peak time, and my peak time was actually pi upon omega d. So your rise time will be simply pi minus theta upon omega d. That's all. Okay, pi minus theta upon omega d. So that's it. Okay, so yeah, that's it. Basically these are the formulas for settling time. For underdamped, overdamped, you can simply find out the location of one of the pole that is nearest to the origin and just multiply, take the inverse of that and multiply it with 4. That's it, right? Okay. So yeah, these are few things basically. So there are many things like what will happen if I add closed loop poles to the OLTF. So these things are there, but for us, right, these are not that important, because ultimately you will solve the questions and you'll understand what is happening, right? So even though if you don't know all this, right, still that's fine, that's enough, right? We'll directly move on. Like this is a summary. So what your task would be to derive it. That is your task, because not super important for exam point of view. This table is not super important for exam point of view, but understanding how am I coming to this result, that is important, right? So let's say if I had initially a OLTF like this. Yeah, this was my OLTF, right? Then I added a pole that is further away from the origin. What will happen? How the parameters will change? Rise time, decay time, resonant frequency, all those things. And if I add a pole that is nearer to the origin, right, what will happen? So those things are there basically. And yep, so these things I have derived here, but for you, I mean, the summary table is not super important, but for you it's understanding that exactly how things vary. If I add a pole, open loop pole more nearer to the origin, open loop pole, remember we're changing the open loop poles, not the closed loop poles. Okay, so it's not that simple as it seems like, because we're adding open loop poles. So yeah, you can see the parameters, what will happen. Okay, not super important, but understanding how, what is varying, what is changing, because this kind of derivation will be helpful in your main exam. Now yeah, that's all basically. There are many types of controllers. The first one being the very basic on off controller, right? On off controller basically means it will be turned on if the error signal is negative, it will be turned off if the error signal is positive. Simply you can think of it as a AC, right? There can be like either on off means there can be two levels, right? Off or on, or like there can be two gains, that is also possible. Let's take the simplest case where my K2 is 0, K1 is non-zero. So in the AC input, right, you want your temperature to be 24 degrees, but sorry, yeah, you currently you want 24 degrees, so that is what you are providing input to the controller side, and your output, that is the atmospheric temperature, is 26. So actually the difference is -2. So controller sees a negative, right? So it will, if the controller sees the input to be negative, it will make the value uh, turn on the AC. So the AC is turned on. Basically, it is providing energy to the AC. So it is turning on the switch, right? That's why it is positive. It is turning on the switch. So switch is on. Now as soon as I will reach my 24 degree that is desired, or let's say if the AC was turned on for a while, temperature may have reduced very much, 23, right? Now what is the error signal? It is positive, right? So now if the error signal is positive, it will turn it off. It will basically turn it off. That's all. Correct? It will basically turn it off. That's all. Right? So yeah, that's it basically. So we got this. Now this is the basic principle of a on off controller. That's all. Now here, instead of on and off, there can be two levels. So if my error signal is negative, then it can provide a gain of K1. If my error signal is positive, it will provide a gain of K2. Simply, the simplest example is when my K1 is 1 and K2 is 0. K2 0 meaning it will just turn it off, and K1 1 meaning it will just turn it on. It will directly connect it, right? It is just like a switch. That's all. Okay, that's all. So yeah, now uh, there is the next kind of controller, which is KP, right? So basically uh, it will amplify the input error signal. So your Kc of t, output of the controller would be Kp into E of t, right? In Laplace domain it will be something else, and this is a very basic example. So let's say I have this plant transfer function Gp of s, right? So what is the, if you see what is the CLTF, if the controller is not involved, it is 4 upon s square plus 4s plus 4. So I can calculate my zeta. So what is my omega n? Omega n is 2. It is a, I think it is, I feel it is a critical damped system already, right? Critical damped. So let's say I want to reduce the settling time. Correct? I want to reduce the settling time. What is the settling time currently? It is 4 upon zeta omega n, that is 4 upon 2, that is 2 seconds. So if I connect a controller, the settling time will be greatly improved, reduced. So now that OLTF, right, modified OLTF will be 4 into Kp upon s square plus 4s plus 4s plus 4 Kp. That's all, right? So now it's not that simple. Okay, so let me take a simple if I can think of any simple case. Yeah, let me take Kp to be equals to 3 by 4. So if my Kp is 3 by 4, right, then this would be s plus 3 into s plus 1, right? Now what is, like, it is a overdamped system, so what is the pole that is nearer to the origin? It is 1, right? So now, okay, your settling time actually has increased. Sorry, we should choose the pole that is okay. We have to move further away from the origin, right? Okay, yeah, okay, sorry, actually, if I make it over dam, it will become more slower. Already it's like, if it is critical dam, right, then we don't have any other option. Okay, unfortunately, what I will do is I will not keep it 4, I will keep it 3 upon s plus 4s. That will be easier for us, right? So this will be 3 now. This will be 3 upon s square plus 4s plus 3 zeta will not be 1 anymore. So zeta will be something greater than 1. It is a overdamped system, okay, because your poles are negative and real and unequal. So zeta in this case is greater than 1. But if I do this transformation, it is 3 kp, right? And if I choose my kp to be 4 upon 3, so just I have to take the example as we move along. So here, if it is 4 by 3, right, what will happen? Your system will become critically damped. Then your zeta will be simply 1. And if your zeta is 1, then this will be the fastest response. So like, I'm just giving you an example, how can the system parameters be varied with a proportional controller. That's it. Okay, so there are many examples, like the steady state error will be totally gone. So of course there are derivations, I'm not going into that, but if you see the steady state error, right, for a type 0 system, right, it will not be gone, but it will be totally minimized. We can minimize the steady state error. There is a derivation, but we don't need to go into that, but just understand how to calculate the error that I have taught you in the time response. That's enough. Okay, now, yeah, so can reduce the steady state error further, yeah, with the help of controller. Then there is PI controller. What is PI controller? It will obviously, the output of the controller will be proportional to the error, plus it will be the integration of the error signal. There are many advantages if you convert this into a Laplace domain. If you calculate the things, you will see what will happen is the error, right, will be totally made to 0 for a type 0 system. For a type 0 system, the error will be totally gone, eliminated. With proportional controller, the error was not made to 0, it was only reduced. We can reduce it, right? So what happens if previously my error was 1, right? The error will be totally made to 0. But in proportional controller, if my error was 1, now the error can be half, it can be 1 by 4, it can be 1 by 8, but I cannot totally minimize it in proportional controller. But in proportional integral controller, I can minimize it. There is a mathematical proof. Of course, I will not go into the proof right now because that is not the purpose. But you can obviously prove it. You can pause the video, you can try and prove it. Error will totally be gone. So I see a proportional controller in Laplace domain, it is Kp plus Ki by S, right? Because integration is 1 by S in the Laplace domain. So it is simply Kp into S plus Ki upon S. Kp into S plus Ki upon S. That's all, right? So I can see we have a 0 at what location? 0 at minus Ki by Kp. We have a 0 at minus Ki by Kp, right? Open loop, this is the open loop 0, right? So this proportional controller adds a open loop 0. So these things are important things to keep in mind. Proportional integral controller. So do my proportional controller add anything? No, my proportional controller does not add anything. It does not add a pole, it does not add a 0. So it is a very simple structure. But as soon as I will move to complex structure, although there are advantages, right, the error, steady state error totally becomes 0, but of course structure also becomes very complex. So I get an open loop 0, and of course I get an open loop pole at the origin, right? Open loop pole at the origin. So yeah, now what happens, sometimes we plot the variation of Kp and Ki as a function of S or something, right? So basically, what are the valid values of Kp and Kp and Ki? Why? Kp is the proportional gain, Ki is the basically this integral gain, right? Ki is the integral gain, Kp is the proportional gain. Now Kp and Ki, what you have to understand, that for some values of Kp and Ki, right, the closed loop system can go out of stability because these are all open loop poles and zeros. And I know my characteristics equation is equals to 1 plus because I have added these things, it will be ki upon s into g of s, right, into the OLTF, correct, because these are added in the input path, forward path. So what will happen due to this, right, the locations of the closed loop poles will change. Now due to these variations of kp and ki, for some values on kp and ky, the location of the poles can go to the right hand side of S plane. That is a problem. So this, right, ki, kp, this discusses the valid values of kp and ki for which the system will be stable. It is called as controller parameter space. That's all. Okay, I hope that part is clear. Now in integral control, there is a bit of problem. What is the problem? The problem is wind up phenomena. What happens? Wind up phenomena affects refers to the situation for a large change between the set point and the output system when it occurs for a long time. The integral term accumulates a significant value and specific problem in the excess overshooting to the actuator. So what will happen basically? Let's say the error signal, right? Initially, the temperature outside is 40 degrees, and you want the temperature to be 15 degrees. So there is an error of how much? Minus 25 degrees. If it was proportional controller, basically your actuator output is the output from this point, right? So this is my controller, then this gives input to the, there is actuator or plant, anything, right? Then this gives me output. So depending on the magnitude of the input, right, controller will work. So here, if it was a proportional controller, let's say the gain of the proportional controller is 2, then this will be minus 50, and I don't care about the unit, right? It will be some unit. So input is minus 50. Basically, we provide the magnitude or voltage signal. Input is 50. Okay, somewhat 50. Like if you see like minus 50, of course, it does not mean anything. We provide some analog signal, whether voltage or current, whatever, right? So input is very large, right, for a proportional controller. What if this was integral? If it was integral, right, the input would be 25 degree integration minus 25 integration dt 0 to t, and obviously ki is there, right? Ki, let's say, again is 2. Now here the problem is, there's a problem. Of course you will say, sir, as I'm providing some input to the actuator or the plant transfer function, so of course AC, if AC is turned on, if AC is in sending me the error like signal that you turn on, so of course the temperature will reduce. So error signal also will reduce. It will be something 20, minus 24, minus 23. That is correct. But for a second, just trust me that for a second, if you assume it to be constant, if it is constant, then your error signal is minus 50 into t. So as the time increases, right, the controller output increases, the voltage level goes very high. When t is 1, it will be 50 volts, right? So let's say when it is minus 50 degree, right, then the controller provides the input to the actuator or the plant transfer function as 50 volts. But here it is constant, it will always be 50 volts, and it will only reduce because the error signal also will reduce. It will go from 25 to 24 and so on. So this also will reduce because it is proportional. But in this case, yes, it is proportional, but here I have t term, right? So as t increases, right, time increases, this will keep on happening, right? This error signal, it will either remain constant, it will reduce, but not to a very large value. So there can be wind up phenomena if there is suddenly very large amount of error, right? Suddenly the controller will provide a very high value. There is high voltage, and if I provide high voltage, the controller may get saturated. The controller may get saturated. That's all. Okay. So yeah, that is the thing basically. I hope you have understood this point. Yeah. Now, steady state error, you can discuss all those things. We have already discussed. It will make it totally zero. Proportional derivative controller, again similar things are there. We will, like, of course, we will, the output will be, output of the controller would be the proportional to the error signal, also the derivative of the error signal. That's all. Correct. So derivative controller anticipates the future response. I have discussed what do we mean by derivative, right? It is f of x plus h minus f of x by h. So of course it will anticipate. So these things are there. Anticipatory, reduces overshoot. Okay, that's all. So these are the properties of a proportional controller. What happens? Key points. You can just see what is happening. So again here, right, what do I get as a pole and 0? So here proportional controller, because it is derivative, it will be kp into e of s. plus S into KD into E of S, correct? So this will be E of S Kp plus S into KD, right? So I see that we don't get any pole, we get a 0, open loop 0 at minus KD upon Kp. Okay, so I'm just writing in rough here, minus S equals to minus KD upon Kp, right? So yeah, so that is a that is not a problem as say that, just like this will be like a improper transfer function. That's why I've written here improper transfer function, because I don't have any 0, I have a pole. So whenever it is an improper transfer function, that means it is a non-causal system, right? That's why we predict the future. This you will be taught in signals and system. That's it. Okay. Okay, this statement actually is incorrect. Attenuates high frequency attenuates high frequency noise. It is incorrect, right? Because it is a it is also called as a lag compensator, that we will lead compensator, that we will realize later on. But if I write what is my transfer function, right? My transfer function is this. This is my transfer function, right? If I replace S with j omega, replace your S with j omega, correct? Just give me 1 second. If I replace S with j omega, what will I see? What will I see? That this will be, magnitude of this will be Kp plus Kd whole square omega square whole under root, correct? This is the magnitude, and at high frequency magnitude will be very high, at zero frequency magnitude will be low. So this statement actually is wrong. It will be, it amplifies high frequency noise. Like if I have a noise that is high frequency, right? High frequency meaning, let's say 1 megahertz signal, 1 gigahertz signal, right? If its amplitude is 0.01 volt, right? It's very small, it's just a noise. But you can observe, if the transfer function, right, the magnitude is very high, so ultimately at a particular frequency, at 1 gigahertz, maybe the gain is 100, so this will be multiplied by 100, so this will become 1, which is very high. So that is a problem for us, right? That is a problem. So of course we don't use just PD controller, we don't use just PI controller, there are many things. So that is one disadvantage of PD controller. Another one is, it is a non-causal system, right? In real life we cannot develop a non-causal system, because of course it differentiates, and we know for differentiating we predict the future, right? Of course we cannot predict the future of the error function, so that is not possible. That's why it is called as a non-causal system. Okay, already I have discussed how it amplifies the high frequency noise. So yeah, there are a few more things that we do, but we don't need to get into that. So maybe like ultimately what is getting used in industry is the PID controller, which obviously includes everything whatever we have discussed, right? Advantages also, and there are few disadvantages as well. That is, the complexity will increase, okay, and few disadvantages of other things also may come into picture, right? But the disadvantages of PD controller and the disadvantages of PI controller, both of them will be very high if I use them by themselves. But if I use PID controller, the disadvantage, that is the amplification of high frequency noise, right, will not be that high, will not be that high. Okay. Similarly for PI controller, there was my controller was getting saturated due to problem of wind up. So that wind up problem also will be reduced here. But of course complexity will be increased, because there are a lot of components and it's not that simple to include everything. Now there is a basic term known as proportional band. You just have to remember about this term. In gate, I don't believe they will ask you from this, but you never know. Previously, I think in very old question they have asked regarding this, but I don't feel latest questions they will ask, but still they can ask. A proportional band of a PI controller is 50%. What does proportional band mean? Proportional band, if they have mentioned in percentage, it is nothing but 100 upon kp, the proportional gain of the PI controller, right? So of the proportional part, right? Okay, 100 upon kp is the gain of the proportional part of the controller. That's it, correct? So if they have given you 50%, so 100 upon kp, the proportional band is 50%, right? So kp would be equals to 2%. Kp will be 2, not 2%, 2, because already this is also 50%, this is also in percentage, right? So kp will be 2. So that's one way to find out. One more term is reset time. What is reset time? Reset time is basically uh this ratio, okay, kp upon ki, because if you derive the transfer function, okay, this will be, if I properly write the transfer function, this will be kp into s plus ki. And if I write this in time constant format, meaning this will be 1 plus s tau by 1 plus s tau 2, something like this, right? This is called as the time constant format. That's why it is reset time. So if I write this in time constant format, so it should be, if I take ki common, this will be kp upon ki s plus 1 upon s. So this is actually called as the reset time, because this is also tau, unit is seconds, so this is also tau, right? So this you can understand using the time constant format, and this is not that difficult for you to remember. Although I hardly believe they will ask you, they will directly give the values of kp and ki, but sometimes they don't directly give you the values of kp and ki, they indirectly give you. So they will give you the reset time, and they will give you the uh, proportional they will give you the proportional band. That's all, right? So these are the things. Now we will move on to compensators. Okay, reset time is this, and yeah, that's all. And your proportional band is that. Compensators are approximations of controllers. So of course you will never be able to get a proper PI controller. A proper PI controller means I will have a pole exactly at s equal to 0, right? That what do you know a ideal do you know an example of the circuit? It is an ideal integrator. So ideal integrator is the example of a of a pole exactly at s equal to 0, right? But this had many problems. If you have studied analog electronics, you will remember this particular circuit had many problems. So we built a practical integrator which had a resistance in parallel with the capacitor. So the same will happen here. We will not be able to build ideal controllers, so the approximations of controllers are actually called as compensators. Similarly, ideal differentiators also very difficult to design. That's why the approximations of compensators are actually called as, approximation of controllers are actually called as compensators. Now we have mainly four kinds of compensator: lead compensator, lag compensator, lead lag, and lag lead. So we will understand one by one. Once if you understand one, right, other three you can easily remember the other three. Okay. So basically lead lag basically means we're compensating the phase. So let's say the input, right? If I'm providing some sinusoidal input, if I have a block diagram, then the output will be basically multiplied by the magnitude of the transfer function at that particular frequency, and phase also will be added. So this phase, right, if it is increasing the phase of the input, my control block, then this compensator is called as lead compensator, because it is increasing. Lead means positive angle in the anti-clockwise direction. That's why it is called as lead compensator. If it is decreasing the angle, right, if this angle is negative, then it is called as lag compensator. That's all. You don't need to understand anything else. That's all. Okay, this is the crux, right? So here's the same thing I have explained, right? If my angle is greater than 0, it will be called as lead compensator. If my angle is less than 0, it will be called as lag compensator. Now there are a few properties about lead compensator, right? So the basic standard transfer function of a lead compensator is this. Okay, now we need to provide a phase lead, right? We need to provide a phase lead. So if I have both a 0 and pole, so 0 provides like with the help of 0 the angle can be increased, right? With the help of pole the angle can be reduced. What do I want? I want my angle to be increased, right? Because I am providing lead, so overall angle must be increased, because 0 provides a plus something of angle 0 and pole provides a negative angle, correct, due to pole. So of course I want plus to be dominating, so it has to be a 0 dominating system. That's why 0 will lie more nearer to the origin, so lead compensators are called as 0 dominating. Okay, so yeah, that's all. Basically that is what you have to understand, 0 dominating, right? 0 provides more angle, that's why it is 0 is more nearer to the origin, because the angle provided due to 0 will be higher. That's why, like, you can compute, right? What is the angle provided here? This would be, let's assume a location. Let's say this is -1, this is -2. Okay, pole location, 0 location. Let's say at any standard frequency, right? What is the angle provided by the 0? It will be omega upon 1, right? What is the angle provided by the pole? It is tan inverse omega upon 2. Okay, tan inverse omega upon 1 and tan inverse omega upon 2. So which one is providing more angle, right? This is like tan inverse, higher the value, higher will be the angle. So this is providing me higher angle, right, than this. That's why it is 0 dominating. I hope you have understood. So lead compensating means 0 dominating system. That is the most important part that you have to understand. Okay, this is the standard transfer function. If you want to remember, you can remember, but there are few things, other things as well you have to remember, that I will explain later on. This alpha is an important parameter that I will discuss. Okay, so what are the corner frequency? You can draw the Bode plot. I hope I don't need to explain. Now this part is very important. At what frequency my phase will be maximum? This has been asked in the exam multiple times, and I am guessing this will be asked again. Now there is of course a derivation, right? You can calculate the phase expression, then you can differentiate with respect to omega, and then you can calculate that at this particular omega frequency it is maximum. But it's better if you remember it. What do we need to remember? And this will be utilized in lag compensator as well. Basically, the frequency at which the phase will be maximum will be the GM of corner frequencies. GM meaning geometric mean, right? So basically, whatever are my corner frequencies here, what is the corner frequency? One corner frequency is at 1 by tau, other corner frequency is at 1 by alpha tau, right? Whatever are my corner frequencies, you just multiply those two and then take the square root, then take the under root, right? You multiply those two and then take the under root, and you will get your uh, frequency at which your compensator will provide maximum phase. That's all. Now what is the value of the maximum phase? Simply you put this value of the frequency at this expression, tan inverse omega tau minus tan inverse omega alpha tau. You can do that, right? You know the transfer function. Can you calculate the phase? If I give you omega I have already computed. You can, right? You can calculate. This will be tan inverse omega m upon 1 by tau, and this will be minus of tan inverse omega m upon 1 by alpha tau. You can calculate it. So there is a simplification. Basically, if we calculate that, if you put the values here, right, the expression comes out to be this, some sine inverse something, right? Now I don't recommend you to remember it, right? You just need to remember this one, right? If you know the frequency at which maximum phase occurs, you can simply put that frequency in the phase expression like here and calculate. Now remembering too many things is not of any use, right? So just remember this one, and this expression, if you want to remember, you can remember, but this can be easily calculated in the exam hall. You don't need to, like, it's not no hard fast rule that you have to remember it, but this one is the most important one. This you must remember, and it is very easy to remember. That's all. So this is the most important part from the lead compensator. Now lead compensator is a causal approximation actually of PD controller. Causal approximation meaning because it is a causal system, right? Now PD controller is not a causal system. So in PD controller, what we assume, like if I assume my pole to be very far away from my 0, correct, then it becomes a causal approximation, right? If my pole is very far away from 0, then it becomes a causal approximation of my uh, PD controller. My lead compensator is a causal approximation of my PD controller. Okay, so yeah, these are few points. You can go through this. I'm not going through them. Not that important. Like lead compensator will help in increasing the phase. Now these things, right, there are a few things like how to find out the alpha of a controller, but I will say don't need to remember this alpha and all those things. Like in the standard transfer function of a lead compensator, this alpha expression was there. No need to remember it, right? No need to remember it. You can always derive it. Okay, so what is happening in high frequency, low frequency, those things you can draw the pole zero diagram and you can plot the Bode plot. Now we will come to the lag compensator. As the name suggests, lag compensator will provide a lag, overall lag, right? So this time it will be a zero dominating. Because it is a lag compensator, sorry, not zero dominating, it will be a pole dominating system. Because the pole will provide more phase shift, right? That's why I will get a negative angle, of course. So it will be a pole dominating system. Similarly, again, corner frequencies, you can see this is the standard transfer function. If you want to remember, great. Don't want to remember, no issues. Okay. Again, if you like, this will be a approximation of PI controller. Like will be a approximation of PI controller, and it behaves as a low pass filter if you see, because it attenuates the high frequency noise, right? High frequency gain is much lower compared to the low frequency gain. That's why it will be like behave as a low pass filter. So these are the things, bandwidth, how bandwidth is reduced. You can put on the parameters and see, right? Bandwidth is reducing basically the working range where the gain is greater than 1 by root 2, and stability is also sometimes reduced because the phase margin will be reduced because it is providing a phase lag, right? Phase margin is a parameter, right? And if it is reducing the overall phase of my OLTF, that means the phase margin is reducing, and if phase margin is reducing, that means my system is going more towards instability. That's why stability is reduced here in this case. That is the reason why stability is reduced. Okay, not completely stability, it becomes unstable, but it is reduced. Great. That is one thing, low high frequency noise. That's all. How now we have lag lead compensator. That means first I will provide lag, then lead. So it provides both lag and lead, but mostly it will be a pole dominating system. So if I draw the pole zero diagram, right, first I will get a lag compensator, then I will get a lead compensator, right? What is the diagram of a pole zero diagram of a lag compensator? I will get a pole first, then I will get a zero, right? Because lag compensator provides more negative phase, that's why pole will be there, right? So this is my lag compensator, and just beside it, I will write my lead compensator. That's why the name lag lead, basically it includes everything. That's the thing. That's the only thing. Like you can see the filter, what kind of filter it is. It is like it is likely a band stop filter, right? Band stop filter. So then we have lead lag compensator. In lead lag compensator, similarly, first I will get a lead compensator, then I will get a lag compensator. That's all. It will be again two zeros will be outside, two poles will be inside for a lead lag compensator, and here two poles will be outside and two zeros will be inside. Great, great, right? Yeah, that's all. And this will be like a band pass filter. Okay, these are the things. Yeah, now pause the video, and whatever knowledge we have gained, right, you have to identify the type of compensation used from the locations of poles and zero. It's up to you. Pause the video, whatever I've discussed right till now, try to identify it. So sometimes this kind of question also has been asked, whether it is a lag lead compensator, lead lag compensator or not. Correct. So I see in the case A, in the case A, I have a pole and pole at -1 and 0 at -10. So basically it is a pole dominating system, right? Pole first, then 0. Single pole and single zero. So of course it will be a lag compensator, right? This will be a lag compensator. What about for the B, part B? Part B, I see that I have like two poles and two zeros. So it will be either lag lead compensator or lead lag. So I see first I have pole, then I have zero, then I have pole, and then I have zero. Okay. So first I have pole. First I have a pole, correct? -1. Then I have a 0, -2. Then I have a pole, -3. Then I have again 0. So have we studied anything? So it feels like first I am getting lag, right? This is lag compensator. So you'll say this is like lag lead compensator, lag lead compensator, which is wrong, which is wrong, right? This is not a basically lag lead compensator, because this is not a compensator, not a compensator, not a compensator, right? It is nothing basically. Let's do it for the case C, right? Case C, 0 pole, 0 pole, right? So again you see, right, is it, so I have zeros, and like this is again not a compensator, right? This pole zero diagram is not proper. This is also not a compensator, not a compensator, right? Here again I see 0 pole, and 0 is nearer to the origin, so you will say it is a lead compensator, and again you will be wrong. The first thing that forgot to tell you, that for any control system to be a compensator, it must be stable. It is not stable. My poles are lying on the right hand side, right? So whatever compensators I insert inside the system, all those must be stable. Basically, the poles must be lying on the left hand side for that particular controller only, for that compensator transfer function. So here poles are lying on the right hand side, so it is not stable. Both pole 0 must lie on the left hand side. Great. For part E, again I see this is a lead compensator, correct? Because 0 is more nearer to the origin, so it will be a lead compensator. For part F, I see I have two zeros outside, right, and two poles inside. So again it is a lead lag compensator. Okay, lead lag compensator. Okay, lead lag compensator. That's all. So yeah, that's all basically. Yep. So yeah, here's the answer. There is a summary. So this is the most important summary for compensators, right? What kind of filter they are, what is the pole zero diagram. Of course we have already discussed what is the uh, like the frequency at which maximum phase occurs. That is these are the most three important parts. That's all. You don't need to study anything for controllers and compensators. You are sorted. So now let's start with the PYQs of controllers and compensators. So this is the first question which I see. A phase lead network has a transfer function, this, right? G of s, the angular frequency at which the maximum phase shift for the network occurs. They are asking me what is the angular phase shift for which the maximum phase shift occurs. So it's very simple. Just find out the GM of the uh, corner frequencies. What is the corner frequency here? Remember, right? Corner frequency, how to calculate corner frequency? S upon omega z upon 1 plus s upon omega p. So omega z is inverse of 0.2 and omega p is inverse of 0.05. So this is actually equals to 5 radian per second, and this is equals to uh, uh, 1 by 2, 1 by 20, 20 radian per second, right? So your frequency at which maximum phase shift will occur, omega m, will be under root of omega z omega p. So it is 5 under root of 5 into 20, that is under root of 100, that is 10 radian per second. So 10 radian per second would be your answer. So I have told you only to remember this thing, and from that only mostly they will ask the question. Otherwise it will be a conceptual question which no formula will work. You have to solve. So this is a conceptual question. The unity feedback system that uses proportional integral control is shown. The stability of the overall system is controlled by tuning PI controller parameters Kp and Ki. The maximum value of Ki that can be chosen so as to keep the overall system stable, or in worst case marginally stable. So basically they are asking me the edge condition, right? That when the system will be on the verge of instability, right? So let us write the characteristics equation. It will be 1 plus gs. So it is basically gs is this, correct? Gs is this into this, so it is kp into s upon S into 2, just give me 1 second, 2 into S cube plus 4s square plus 5s plus 2, right? Yep, that is it basically. So yeah, this, right, equals to 0, correct? So here, right, if I properly write it, this will be okay. This is becoming a fourth order system. Okay, that is quite interesting. Fourth order system, right? So this is not a third order system, so we have to plot the route table for this. So yeah, let me first of all properly write this. This will be s raised to power 4 plus 4s cube plus 5s square plus 2s plus 2 kps plus 2 ki equal to 0. So this will be s raised to power 4 plus 4s cube plus 5s square plus s into 2 plus 2 kp, sorry for the noise on the background, plus 2 ki, that is equals to 0, right? So we have to form the route table here. So if we form the route table, they are asking me the maximum value of ki. Okay, the minimum value, of course, of ki has to be positive because all the coefficients must be positive, otherwise this won't be a Hurwitz polynomial. So minimum value I know, they are asking me the maximum value. Okay, so s raised to power 4, s cube, s square, s raised to power 1, s raised to power 0, correct? So first I will write 1 5 2 plus 1 5 1 5, then 2, then I will write 4, then 2 plus 2 kp, then 0. That's all. Sorry, this will be, hold on a second, this will be 1 5 2 into ki, 2 into ki will be there, right? Yeah. So now I can form the route table. So this will be 4 into 5 minus this divided by 4 only. So this will be 5 minus 1 plus kp divided by 2, that's all. Great. And as I have 0 over here, right, this 2 ki will be directly copied over here. Okay, in the second, actually I have not given enough space here, right? I'm very privileged that I can move things around, but you are not, so make sure you give more space. So 2 ki will be directly transferred over here and this will be 0. Great. Okay, this calculation will be very difficult. Okay, here only main thing will happen, right? So this will be 5 into this kp. So kp, okay, this kp, right, kp, this cannot be, this also has to be positive, right? This also has to be positive. So 5 minus 1 plus kp by 2 has to be positive. That means 10 has to be greater than 1 plus kp and kp has to be less than 9. Now let me assume that this is x. Okay, this question is actually pretty good. Let me assume this is x. What is x? X is this multiplied by this minus this multiplied by this, correct? So let me write these values. So here it will be 5 minus 1 plus kp divided by 2 into, I can take 2 common, 1 plus kp again minus 4 into 2 ki, that is 8 ki, right? Divide by something, I divide by this value only, correct? But I don't care. Why I don't care? Because here what will be copied? Here 0 will be copied, right? 0 will be copied. Here also 0 will be copied. Now of course they have told me at max my system can be marginally stable. For my system to be marginally stable, right, this has to be 0, or for, yeah, this has to be 0, right, this has to be 0 if my system is marginally stable. So I will assume that case. I will assume my system is marginally stable. I will assume my system is marginally stable, right? You could have assumed this one as well, right? You could have assumed this to be 0 as well. But actually we don't get a row of 0 whenever I have even power, right? We get a row of 0 in the odd power only. So that the above equation gives me the auxiliary equation. So this, actually I was wrong here, right? I was wrong, unfortunately. This is incorrect, right? Because in the Raoult-Hurwitz criterion, we have learned that we will never get a row of 0 in even power. We will always get it in odd power, because the row above the row of 0 is actually the auxiliary equation. An auxiliary equation always happens with odd power, sorry, even power. Auxiliary equation always happens with even power. So hence this is wrong. This part is wrong. Okay, this part is wrong. Okay, great. Now this has to, like, at max this can be 0, right? So that my system is marginally stable. So what is my Ki in terms of Kp? So my Ki, right, because it is equal to 0, right, whatever I am dividing, it does not matter, right, because I multiply that on the other side, that will vanish. So that's why I'm not writing divided by this value, not writing it, because I'm equating this equals to 0, that's it. Now my Ki is equals to this value, right, this value divided by 8. So which is, because I have already a 2 here, so this will be 1 by 4 into 5 minus 1 plus Kp upon 2 into 1 plus Kp. Okay, that is my Ki. Now what have they asked? What is the maximum value of Ki? Because there are two variables. Now this, right, actually this you have to plot in the controller space that we have discussed, right, Kp and Ki. So for what maximum value of Ki my system will be marginally stable? How can I calculate it? So I have a function here, let's say y, which is a function of x, and I have to find out the maximum value of y. How do I calculate? I differentiate that dy by dx, I equate it equal to 0, and I find out the value of x, right, and then I put the value of x in this equation, in this particular equation, and that gives me the maximum value of y. That is exactly what we will do. It is not so obvious here. That's why after this step many students will be confused, and I have seen the solution in many PYQ books. They have given some solution, right, and you are not able to understand the solution. Trust me, you see any other PYQ book, there this solution would not have been given to you properly, correct? But here, that's why we are here. That's why PrepFusion is here, to clear all your doubts. So I will differentiate this function with respect to Kp, because Kp is my variable. I don't care whatever is the value of Kp. I need to find out the maximum value of Ki for this particular condition. So dki upon dkp, that will be equals to 1 by 4 is just a constant. Here I have product, right, multiplication. So I will use change rule. First I will differentiate this, then I will differentiate this. So for, if I differentiate this function, right, it will be simply minus 1 by 2, that's all. Minus 1 by 2, and of course this I will keep as it is, constant. 1 plus kp. Hold on a second. Yeah, this is interesting. So then I will differentiate this, that is 1 only, and this will be kept as constant. So 1 by 4 can be outside, this will be kept as constant. So this will be again 1 into 5 minus 1 plus kp by 2. This is equals to 0, right? So this actually is added. This is added, this will be equated to 0. So this is equated to 0. That means this will be equals to 1 plus kp by 2 equals to 5 minus 1 plus kp by 2, that's all correct. So this can go on the other side. So 1 plus kp is actually equals to 5. So Kp is actually equals to 4. So when Kp is 4, right, I will get the maxima condition. Correct? I will get the maxima condition. So when Kp is 4, my Ki will be what? That is the maximum value of Kp. Now that is the maximum value of Ki. Now you will have some doubt, sir. If I equate this equal to 0, we can get a maxima or minima. But here you are only getting a single value of Kp, right? You are not getting two values. And in the question they have asked for maxima, and there are no upper or lower bound on the value of Kp or Kp, right? So you will assume that this condition is for the condition of maxima. You will assume that. I know the students who have studied maths very well, they will have a doubt, sir, how do you know that this is maxima only? How is this not minima? You are correct. For your own sake, of course, you can double differentiate this. And if you can put the value of x there, right? In this case, I will put the value of Kp and I will see that it is negative. So of course, I will get a maxima, correct? But the question here already is asking me maxima and I am getting only a single value of Kp, then it will be maxima only, it will not be minima. Understood? So yeah, Ki, if I put the value 4, right, this will be 1 by 4, 5 minus 1 plus 4 upon 2. This will be 1 plus 4. So this will be equals to 1 by 4, 5. So this is 5 by 2, right? That is 5 by 2 only into 5. Okay. So this will come out to be 25 by 8. So what is 25 by 8? I guess it will be 3.125. Okay. 3.125. This is the maximum value of Ki, maximum value. So this will be actually your answer. What have they asked? Round off to how many decimal places? 3 decimal places. So exactly it is 3.125. Exactly. So this question is actually pretty beautiful because this is a mixture of both Raoult-Hurwitz criterion and controllers and compensators. So in controllers and compensators, they will not just ask from that particular topic. They will mix two questions. That is the beauty. So this question was actually pretty good. You can watch the solution again. Let's solve the next question. This is the next question where we have been given a closed loop transfer function. Planned transfer function is given, right? So the closed loop system is shown and planned transfer function is shown. The compensator is simply gain is 1. For a unit step input, the output response has damped oscillations. The natural frequency of oscillation would be. So simply they are asking me what is the natural frequency of oscillation. Basically they are asking me what is omega n. So I can actually solve it. So overall what is my OLTF, right? OLTF. OLTF is GP into GC. GC is simply 1. That is GP only. So it is 14.4 upon S into 1 plus 0.1 S. Correct? So let me actually properly write it, right? With S, the coefficient of S should always be 1. Okay, if you remember in the standard second order representation, so coefficient of S always must be 1. So this will be, if I multiply by 10 on both sides, right? Multiply by 10 on both sides, this will be 144 upon S into S plus 10, right? So what will be my CLTF? It will be 1 plus 1 OLTF by 1 plus OLTF. So it will be 144. So S square 144. So from this I can directly say what is my omega n, that is 12. So 12 would be your answer for this question. Now what have they asked? What is my sorry, not natural frequency oscillation. They have asked me what is my damped natural frequency oscillation. Very careful, right? They have not asked you what is your natural frequency oscillation. They have asked you what is my damped natural frequency oscillations. So for that I actually need zeta as well. Zeta would be 2 zeta into omega n would be equals to 10. So zeta in this case would be 5 by 12. Okay, so yeah, what will be damped natural frequency of oscillation? D omega d is actually omega n sine theta, right? Cos theta is this. So sine theta, if you know bit about triangles. Okay, no, I don't know anything about triangles because 12, right? 12 is not proper. 13 would have been possible, but 12 is not possible. No, so no, I don't know. I know nothing about the triangles. Okay, so this will be 1 minus zeta square. So you can solve it. This will be 12, 1 minus 25 upon 144, correct? So this will be some weird value. Let me calculate this. Okay, 144 minus 25 upon 144 under root into 12, which is 10.91 radian per second. Okay, so 10.91 radian per second. So yeah, that will be your answer. Okay, damped natural frequency of oscillations. That's all. So yep, now let me solve further. In the given figure, plant gp of s is this, right? And the compensator is this, and the external disturbance is this. Okay, it is desired that the external disturbance is a unit step. Okay, it is desired that when the disturbance is a unit step, so my d of s is a unit step, that is 1 by s. The steady state error should not exceed 0.1. So maximum error due to my unit step ess should not exceed 0.1, right? Maximum. So they have also provided you where is my error signal located. It is located here. So always in these weird kind of block diagrams, they will always mention where is your error signal located. Okay, it is here. The minimum value of k, what shall be the minimum value of k, so that the error is maximum value of error is 0.1. So let me first of all find out the expression of error due to disturbance. So whenever I am calculating the error due to external disturbance, of course I will make my input 0. Input will be simply 0. So if input is 0, what will happen? If input is 0, this will be here I have my d of s, input is 0. So okay, this will be my c of s, correct? And input is 0. So my error signal, right? When my input is 0, my error signal is simply minus of c of s. Error signal is simply minus of c of s. Correct? Error signal is simply minus of c of s. Right? So yeah, that's all basically. So okay, so I need to calculate c of s. How do I calculate c of s? For that, let me first of all compute c of s upon d of s. What will be c of s upon d of s? I can use simple block diagram, right? I don't even need to calculate the direct relation. This is 0, this part is 0, and this is c of s, right? So minus, so this e of s is minus of c of s, correct? Into gc of s. Don't want to write, currently don't want to write gc of s. Let me just write here gc of s into c of s, right? Then this plus this will be equals to what? D of s plus minus of gc of s into c of s, correct? So yeah, that's all. Now yeah, now your c of s would be this multiplied by gp of s, right? Okay, will be a bit difficult. Okay, still I will solve. So gp of s into d of s minus gp of s into gc of s into c of s, right? So ultimately your c of s actually would come out to be equals to gp of s upon 1 plus gp of s into gc of s. I will not write it. Why? I will explain just at the end. D of s, right? So my error signal is what? E of s is equals to minus of gp of s upon 1 of gp of s into gc of s into d of s, correct? Now what will be the expression for steady state error? It will be limit as s tends to 0 s e of s, correct? So I will do the same. So if I put the expression, right, what is d of s? D of s is a step input. So s into 1 by s, right? S into 1 by s. I will be very smart here, okay? To minimize my calculation, that is what I will do. So this will be actually limit as s tends to 0 into 1, okay? Now what is gp of s when s is 0? So gp of s when s is 0, right? It will be simply 2.2. That's all. Minus 2.2. Okay? And they have asked me to limit should not, the steady state error should not exceed more than 0.1. Okay? So yeah, that's all. Okay, for the error signal is this, right? Input is minus of this, error signal is minus of c of s, correct? Okay, that will go there. C of s is this. Hold on a second. Minus of gc of s. So this will be added. This will be subtracted into gp of s. Okay, I'm just thinking like there is a problem of sign. That is what I'm thinking. Why is there a problem of sign? There should not be actually. Negative sign should be automatically vanished. Okay, that is interesting. Negative sign should be gone actually. That is what I am thinking. GC or GP. Okay, let me keep this sign. I don't know what is happening with the sign, but negative sign should be gone. Maybe I'm doing some mistake, some minor mistake. I'm just not able to figure it out. Right. I don't know. Maybe they were discussing about the magnitude. Let me solve it. So this will be 1 plus GP of 0 is 2.2 and GC of 0, right? What is GC of 0? It is K only, right? It is K. Okay, it is K. Correct. It is K. This shall be like maximum value of this shall be 0.1. Okay, 0.1 units, right? So I'm just thinking something. I guess there is some problem. I'm doing some mistake with the sign. So here C of s comes. This is negative sign. So this is minus C of s. That is fine. Error signal is minus of C of s. Great, great. Now what is my C of s? This is GC into minus. That is fine. This is G of s plus GC into C of s. That is fine. Into GP of s into GP. Okay, that is also fine. Is equals to C of s. Okay, this will go on the other side. I don't know. They should have actually discussed like the magnitude. I guess they're talking about the magnitude. Okay, they should have provided the magnitude. I guess there is some sort of slide error. This should be the magnitude. So if it is the magnitude, right? This will be plus. Okay, I guess there is some sort of error. I'm guessing that. Okay, because from my end I see it is positive. So because otherwise the question will be wrong. So if they are discussing about the magnitude, this will be 1 plus 2.2 k equals 22. So otherwise k value will come out to be negative, right? That is not possible. So I guess they are discussing regarding the magnitude. So kp would be 21 divided by 2.2. So 21 divided by 2.2, that is 9.54. So maximum value of k should be 9.54. Okay, so yeah, so that is the thing basically. So I think this question had some empty as well, because yeah, there is a problem here. I think IT Bombay also did not tell us, like, this was coming out to a negative, k value was coming out to something else. So we have to be careful here, right? So I guess they will make some changes here. Okay, this there were some changes, I do remember. So if they properly would have given the question, then the magnitude, if I would have assumed the magnitude, then this would have came as 9.54. That's all, this will be the answer. Let's move on to the next question, right? Consider a unity feedback system. The PID controller is given to you, as shown in the figure. PID controller, okay. uh, PID controller as shown in the figure. Okay, PID controller, yeah, it's like a, yeah, PID controller. It is only stable for this value of k, for that value of k. So they're basically discussing about the stability. So I can directly use the route. What is route? Route is 1 plus OLTF equal to 0, characteristics equation. So if I see here, my g of s, g of s is 1 by s plus 1 into s plus 3. S plus 1 into s plus 3 into c of s. C of s would be s plus k into, just give me a second, k into s plus 3 minus j s plus 3 plus j upon s. This is equals to 1 plus this, right? Okay, that will be very difficult for me, but that's fine. But this is still a third order system, so it will be not that difficult for me to calculate the stability. Actually here, right, you can multiply these things. Okay, we can multiply these things, right? This will be s plus 3 s minus g, so this will be s plus 3 whole square plus 1 basically, right? Yeah, plus 1. Okay, so this will be s square plus 4s plus 3 into s, 1 upon this into k into s plus 3 whole square plus 1, that is basically s square plus 6s plus 9, that is plus 10. Okay, I'm adding 1 as well. 1 plus this equal to 0. So I can solve it now, not that difficult. This will be s cube plus 4s square. Okay, 4s square plus 3s plus k into s square plus 6ks plus 10k equal to 0. So this will be s cube plus s square k plus 4 plus s 3 plus 6k plus 10k. Okay, so yeah, I can use the internal product and the external product. So k plus, first of all, k has to be greater than 0, right? For stability, k has to be greater than 0. That is one condition. What about the other condition? The internal product must be greater than the external product. So k plus 4 into 3k, 3 plus 6k must be greater than the external product, that is 10 into k. Okay, so let me solve this particular thing. So this shall be equals to, if I take 3 to be common, okay, let me not take 3 common. This will be 3k plus 6k square plus 12 plus 24k is greater than 10k. 6k square plus 14k, okay, 3k is also here, right? So 14k plus 3k, it will be 17k plus 12 is greater than 0. Okay, great. So okay, we have to solve this. So if I uh, calculate the roots of this equation, right? K equals to plus minus, so minus b, that is minus 17, plus minus b square minus 4 is b square is 17 square. 17 square minus 4 is minus 4 into, hold on a second, 4 into 12, 4 into 12 into 6 minus 4 AC, and this plus 17 square. Wow, that is interesting. It is exactly coming out to be 1. Okay, so this is actually 1 upon 2a, 2 into 6. Okay, so there are two roots here. So one root would be minus 18 by 12, that is minus 3 divided by 2. Other root would be minus 16 by 12. So 16 by 12 will be minus 4 by 3. Okay, so there are two roots basically, both are on the left hand side. So k minus 3 by 2 is one of the solutions, and k minus uh, k minus, sorry, k plus, this will be k plus and k plus 4 by 3 basically, right? After k greater than 0, right? If I draw the wavy curve method here, so at k equals to 4, because 4 by 3 is the lowest root, right? Yeah, 4 by 3 is the, sorry, is 4 by, yeah, yeah, not lowest, sorry, 4 by 3 is the highest value of the root, minus 4 by 3, minus 4 by 3, right? And then after that minus 3 by 2 comes. You can break it down, right? You can break down these roots, all these things you can do. So of course after this, right, it is always positive. So k is, the condition was k greater than 0, that was one of the condition, right? So anyways it is always positive, right? So it is always stable, like this condition is always satisfied, this condition is always satisfied. For k greater than 0 it will always be positive, because if I solve the wavy curve method, I see that for this, like, I hope you have watched the video of wavy curve method. I will not explain here the wavy curve method, it has been already explained in the R-PYQ series in the playlist. Okay, that is already there. So of course from the wavy curve method I observe that this is always positive when my k is minus 4 by 3, right? But my k, the lowest value of k, that is 0. So k is anyways greater than 0. So anyways this is always satisfied, always satisfied. That means it is stable for all positive values of k. It is stable for all positive values of k. That is the main condition. Right? That's all. Okay, so option A will be the correct answer. Great question. Let's solve the next question. So again, okay, it is a state space representation. Okay, so this was actually a state space question. By mistake it came here, so I will add in there. So the state space representation of the system, the minimum number of state variables necessary. So I see that this is the transfer function, and I see it is a third order system. So what is the minimum number? Number 3. So number of state variables required will be the number of order, like the order of the system, right? That is 3. So it will be 3. So let me just move this question back in the uh, state space, otherwise this will be a mess up, right? Let me just see where I can fit this in. Let me put this at the end, that will be the best thing. Yeah, let me put this here. What was this? This was 10, this is 11. Let me put it here, otherwise things will be messed up, right? By mistake I think I have put it over here, it is not supposed to be here. Yeah, this should be 6. So in unity feedback system, the planned function is given. The controller is controlled by a lag compensator. You can verify, right, that the location of the pole is at point 1 and location of the 0 is at minus point 1 and minus 10, right? So pole is much nearer to the origin, so it is a pole dominating system. The slope of the asymptotic Bode magnitude plot of the loop gain at omega equals to 3. What will be the slope of the loop gain? Loop gain meaning the product of this and this, because generally how do I connect? I will have a controller, just give me a second. I will have a controller GC, and then I will have the planned transfer function GP, and then I will have this. Okay, correct. So yeah, so that is the thing basically. Uh, so your OLTF, right? OLTF will be product of these two, right? That is what they are asking. What is the loop gain? So first of all, let me calculate what is my OLTF. So OLTF will be product of these two. Now for drawing the asymptotic Bode plot, generally actually we need to convert it in proper time constant format. This is already in the time constant format. Let me convert this also in the time constant format. So for that I need to take 10 common from the numerator and 0.1 common from the denominator, right? This will be 0.1 into s plus 1 upon 10s plus 1, and zero point 0.1 and 10 I have taken common, so this will be 100. Okay, so this multiplied by this OLT, right? That is 0.001 upon s 2s plus 1, 0.01 s plus 1. Yeah, that's all. Yeah, so yeah, so your OLTF will be actually, this will be 0.1 into 0.1 s plus 1. I have a 0 at s equal to 10 actually, right? So let me write this in proper format. This will be s upon omega z, that is 10, and this will be s. So first of all I have a pole at s equal to 0, then I have a pole also at s equals to 0.1, and then I have a pole at s equals to 0.5, right? I'm just taking the inverse of this, right? That's all. Same thing only, right? I'm just writing it in the bottom because this will be easier for me to identify the pole and 0 locations. So this will be s upon 100 plus 1, that's all. So this will be equals to, if I solve this, right? Yeah, if I draw the Bode plot, so first of course there will be some d-secant. What is the d-secant? There is no d-secant, okay? Because I have a, already I'm starting from a pole at s equal to 0. So I have a pole at s equal to 0, so initially the slope would be minus 20 dB per decade, right? Then I will encounter a, and this is anyways 0.1, right? So it will be something lower value, so I'm guessing I will be lying in the bottom. Okay, that's my guess. So then I will encounter at s equal to 0.1, omega equals to 0.1, right? I will encounter another pole. So the slope will be further reduced to, okay, let me actually, this is already very slopey. Let me keep it like it, this. Yeah, that is, no, this is 100, yeah. Yeah. So slope will be reduced further. Another, like I'm encountering a pole here, so overall slope would be minus 40 dB per decade due to the pole. Then again at s equals to 0.5, I'm encountering another pole. 0.5, I'm encountering another pole, right? Slope will reduce further. Slope will reduce further. that is minus 60 dB per decade, and this will go on till the point s equal to 100, right? S equal to 100 is the point where I will encounter a 0. So the slope then will increase by 20. So overall the slope would be 40 minus 40 dB per decade. Overall the slope would be minus 40 dB per decade. But what have they asked actually? They have asked me the slope in dB per decade at omega goes to 3 radian per second in integer, right? So in integer at omega goes to 3 radian per second. So 3 would be lying somewhere here, and in this region the slope is minus 60 dB per decade. So the answer would be minus 60. Minus 60 would be your answer for the question. Okay, let's now solve the next question, right? This was sixth question, this is the seventh question. So the seventh question, the proportional integral derivative controller is employed to stably control a plant with transfer function this. Okay, so now the proportional gain is increased by a factor of 2. The integral gain is increased by a factor of 3. Okay, proportional gain. So I'm employing a PID controller to control this plant transfer function, right? So what is the transfer function for the PID controller? It is Kp plus Kd into S plus Ki by S. This is my PID controller. Now what they are telling me that they are increasing the proportional gain by a factor of 2. So it will be 2 Kp. They are increasing the integral gain by a factor of 3, and they are keeping the derivative gain unchanged. So it is Kd into S, right? Given that the closed loop system continues to remain stable. Okay, closed loop system continues to remain stable with new gains. Okay, with new gains it is still stable. The steady state tracking error, steady state error in tracking the ramp signal would be, okay, what will happen to the steady state error, right? So what was happening to the previous steady state error? So nothing is mentioned. I will assume it to be a unity feedback system. I will assume it to be a unity feedback system, right? That is what I will assume. This is a plant transfer function. Uh, okay. So if I assume it to be a negative unity feedback system, what was the previous steady state error? So previously, right, your steady state error would be R of S minus C of S, right? I hope you remember the block diagram. So here, this is my error signal. Of course, R of S I can take common. This will be 1 minus T of S, right? Simply because C of S is R of S into T of S. Okay. So what is the transfer function? I don't need to. Okay, let us not calculate the transfer function. It will be basically R of S into 1 minus GP into OLT, right? GP into GC of S upon 1 plus GP into GC of S. Correct? Yep, correct. So that's all basically. This is my error function, right? So yeah, previously, so let me put this into perspective. Previously, right, what is the steady state error? It is limit as S tends to 0, S into 1 by square 1 minus. Now the interesting thing is I will not put I can put S equal to 0 over here, right? This will go away. Okay, let me not put S equal to 0. So let me do this, right? Let me do this thing, that this will be equals to Kp into S plus Kd S square. Like you can solve this, there is no problem, you can solve this, right? But I want to simplify my calculations, right? So this will be Kd into S square. In the exam maybe I will solve it properly, right? Maybe maybe I don't trust myself. Plus Ki this upon S, correct? So what will happen if I put S equal to 0, right? This will be anyways vanished. So only ki upon s will be there, correct, if I put s equal to 0. So that is what I will write instead of gc, right? When I put s equal to 0, I will write ki upon s. Okay, that's all. Why? Because I cannot put s equal to 0 here, right? That will make it infinity. So that is a problem. So I will figure it out later. What about gp? In gp, if I put s equal to 0, it will be simply half, right? There is no problem in putting the planned transfer function s equal to 0. It will be simply half. So this will be half upon 1 plus ki by similarly 2s. Great, all life is good. So I'm calculating for ramp signal, right? What was the previous? So what are they asking? What will happen to the steady state error? Yeah. So previously, right, this will be 1 by s is still there, right? I cannot still cancel it. Limit as s tends to 0. This will be if I multiply by 2s on both sides, uh, this will be 1 minus ki upon 2s plus ki. Great. Okay, this will be equals to limit s tends to 0, 1 over s, 2s plus ki minus ki, so it will be 2s upon 2s plus ki. Ki is automatically gone, s is also gone, so it is basically 2 upon ki. If I put s equal to 0, I can put s equal to 0 now because this s has been cancelled. So actually my steady state error only depends on the ki, and it makes sense, right? We discuss in PI controller, it reduces the steady state error. The PI controller reduces the steady state error. The PT controller actually, it does not change the steady state error. It changes the transient behavior. Your PI controller will change the steady state parameters, and your PT controller will change the transient behavior. That's why it differentiates, right? Differentiation meaning it is changing some transient parameters. Integrating meaning it is changing the steady state parameters. So here, right, I'm not okay. I'm increasing my ki to 3 ki. So I'm increasing my controller gain by 3. So the steady state error will be reduced by a factor of 3 because my steady state error is inversely proportional to k, right? So steady state error will be reduced by a factor of 3. So option C will be correct for this question. Pretty simple, straightforward. Of course, you will have doubts out, sir, how are you writing here is equal to 0, you're removing this, then you're solving. Magic. Okay, I'm doing magic. But of course, you can always write this whole expression in this point here, right? Solve it properly, you'll get back to the same result, right? But if you want to be a bit smarter, but don't be too smart, don't be over smart, okay? Otherwise you will make some you will make some mistakes. So don't be over smart, just use little bit of smartness, then you will be able to figure out in the exam hall. If I am bit unsure, right, and if I have enough time, so I will actually write all the values here properly. I will not do any smartness, okay? But just to show you, this can also be done, right? Without writing all the expression cleanly also I can solve it without doing higher calculations, right? This reduce my calculation. That's how you can get gain more marks, okay, just by reducing your calculation. Let's solve the next question. Let me drink a bit of water. Consider a unity gain negative feedback system consisting of plant g of s given below and the proportional integral controller. Okay, so we are using a proportional integral controller, right? Gc of s would be kp plus ki by s. Okay, let the proportional gain and integral gain be 3 and 1. So kp is 3 and ki is simply 1. For a unit step reference input, the final values of the controller output and planned output respectively are. For a unit step reference input, so my input is unit step, the final values of the controller output and the planned output would be. So what is the final values of the controller output? So you see, right, this is my planned transfer function, right? So I am observing that it seems like my system is not stable. This will be 3s plus 1 upon s. Seems like my system is not stable. So they're asking me what is the final controller output, okay, and the planned output, controller output and the planned output. So okay, so let me first of all draw the block diagram. Okay, here I have my input, I have my negative feedback system, GC office, into GP office. Okay, and this is my output C office. They are asking me what is the final controller output and the planned output. Planned output would be same as the control, like the output of the whole block, right? Planned output. Uh, okay, so let me compute these values, right? Let me compute these values. So yep, seems like the system is not stable, right? But actually, if you calculate the transfer function, it will be OLTF upon 1 plus OLTF. So that is GC of s into GP of s. So it is uh, 3s plus 1 into your GP, right? Planned transfer function is 1 by s minus 1. But actually the system will be stable. At first glance, it seems like it is not stable, but system will be stable. Before I told you that controller must all be, all the poles of the controller must all be on the left hand side. That is a separate thing. That is a separate thing. But even if OLTF, right, the poles are on the right hand side, overall system CLTF can be stable. That is a separate thing. This is a separate thing. Both are separate. So 1 plus the same thing over again, OLTF, right? So this would be 3s plus 1 upon hold on a second, yeah, 3s plus 1 upon s square minus s plus 3s plus 1. So this will be equals to 3s plus 1 upon s square plus 2s plus 1. So of course you can observe that all the poles are on the left hand side and not on the right hand side of the CLTF. So of course system will be stable. That was anyways, I already told you, right? That was anyways true. But here like infinity option is there, right? So you can feel like system is unstable. They have given the infinity option just to confuse you, and you should also be careful. Whenever infinity is there, you should be careful. Okay, this is my transfer function. So the what will be the steady state value, right? So input is R of s. So my output C of s, right, will be equals to R of s into T of s, and of course the C of s is nothing but the output of the plant only, right? So the steady state value of plant or the output is s limit as s tends to 0, final value theorem, s into R of s, that is 1 by s, into T of s, that is 3s plus 1 upon s square plus 2s plus 1, which is simply equals to, if I put s equal to 0, this will be 1. That's all. So steady state value of the controller output, right? Sorry, planned output is 1. So 1 is present only in the option D. So option D is correct. Let me verify with the controller output. What will be the steady state value of the controller output? Okay, this, right, will not be that simple. Controller output, right, will be equals to, what I can do, this is C of s. So this will be your C of s upon GP of s. I hope you can understand this, right? I'm just dividing by the block gain, that's all. So what will be the final value of this particular thing, right? C of s upon GP of s. C of s is this value. C of s is basically this value, right? That is my C of s, right? This is my C of s, okay? And GC of s, sorry, GP of s, planned transfer function, is this 1 by s minus 1, right? 1 by s minus 1. So again you might feel like, is final value theorem applicable? We will see. So this is my C of s upon GP of s, right? So actually this is not the pole, this is the zero location. Actually this will go on the top. So this will be 1 by s into 3s plus 1 upon s square plus 2s plus 1 into s minus 1. So actually this is not a problem anymore. This is the denominator, right? That is, again, all the poles are on the left hand side. So there is no problems at all. So I can again use the final value theorem. So again, if I put 0 here, this will be minus 1. That's all. This will be minus 1. So exactly it is matching, right? Minus 1. Yeah. So option D is correct. Let's solve the next question. Okay, this is the ninth question. Okay. The questions of controllers are a bit lengthy because it includes questions from the other chapters as well. Consider a lead compensator. This the frequency with this at which the maximum phase lead is provided is 4 radian per second. Okay, great. I know that the frequency at which maximum phase lead is 4 radian per second. So it will be the GM of both the corner frequencies. At this frequency, the gain amplification provided by the controller, assuming asymptotic Bode plot of K of S is 6 dB. Okay, asymptotic Bode plot of K of S is 6 dB. Uh, okay, at this frequency, the gain amplification of my transfer function is 6 dBs. Okay, in dBs, it is 6 dB. So magnitude of K of j omega at omega equals to omega m is 6 dB, right? So what will be in absolute scale? This is in decibel scale, right? So dB, this would be log 20 log of x would be 6. So it will be 10 raised to power 6 by 20. That's all. 6 by 20. So it will be, I guess, 10 raised to power 0.03, right? So 0.3, 10 raised to power this is 2. Okay. So that would be 2. Right? This would be equals to 2. That's all. That's all. So, yep. So gain would be 2, and maximum, the frequency at which maximum phase occurs is 4, right? This is nothing but the GM of both my corner frequencies. What is the corner frequency? A. What is the corner frequency? Beta A. So GM of both the corner frequencies, A, beta A, that would be equals to A under root beta. Okay, A under root beta, right? So yeah, that is my value. A under root beta is equals to 4. Great, I got one information, right? Another information is given to me, the magnitude, right? So if I put this equals to 4 here, right, this will be 1 plus j4 upon A upon 1 plus again j4 upon beta A, right? And I have to calculate the magnitude of this, and that magnitude is equals to 2. So this will be 1 plus 4 upon A square plus 1 plus 4 upon beta A whole square under root, right? This whole under root is equals to 2. So I can square both sides, right? I can square both sides. If I square both sides, this will be 1 plus 4 A whole square equals to 4 beta A whole square. Okay, great. Okay, do I have any other information here? So this is equals to 4, right? So 4 upon beta A. So this, right? What is my A is A? What is my A? A is under root beta. That will not help me. Let me reduce. What is my beta actually? So my beta. Okay, one information is given to me, right? Alpha into under root beta is 4. So let me do that. Alpha into under root beta. Here I am getting 4. Here alpha into under root beta. Here also I am getting 4. Okay. This I am not getting 4. Incorrect. This, right? It also, it seems it is incorrect. Let me just verify it. 2.25 under root into 2.66. Okay, here I'm getting 4. So this also seems like these three are the possible answers, because they all of them are actually uh, making this condition true. So I have to verify with this condition, right? So A into under root beta, right, is 4. So A is equals to, let me write beta in terms of A. So beta would be equals to 16 upon A square. Okay, beta would be 16 upon A square. Okay, great. So this will be equals to 1 plus 16 upon A square, that is nothing but my beta only, right? Okay, that is equals to 4 upon 1 plus okay, beta is 16 upon A square. So this will be 4 16 upon A square. So A square into A whole square, right? Okay, A will be cancelled. So this will be, A will go there 4. So this will be A by 4. So 1 plus 16 A square equals to 4 1 plus A upon A square, sorry, A upon, yeah, A upon 4. Hold on a second. This is whole square, right? This is not correct, yeah. This part is same only. Sorry, I'm just writing the bracket incorrectly. So A upon 4. Okay, and this of course I will square it. Don't forget, you will square it. Okay, okay. So actually what is happening, this is 1 plus x. Let me satisfy this equation, right? Whichever one is satisfying the equation. So if I put a equals to 1, this will be 1 plus 16 equals to 4 into 1 plus 1 by 4 whole square, that is 1 by 16, right? If a is equals to 1. So of course solving this equation will take me a bit of time, which is definitely not satisfying, right? So this option is automatically gone. So option A is definitely not satisfying. Correct? Option A is definitely not satisfying. Okay, hold on a second. Yeah. So option B, what about option B? Option B, right? If I put A equals to 2, if I put here 2, what will happen? If I put A equals to 2, this will be 1 plus A equals to 2. 1 plus 4 equals to, on the right hand side, what will happen? 4 into 1 plus, if I put A equals to 2, this will be, hold on a second now. This 4 should be there. Huh? Yes, this 4 should be there. That is correct. This will be A by 4 whole square. This will be 1 by 2 whole square, that is 1 by 4. Correct? So yeah, this is matching actually. So on the left hand side I have 5, on the right hand side also you will see I have 5. So 5 is correct. So this seems like this is correct. This is satisfying both the conditions, this one and this one. Of course we can verify with this value. You can put A equals to 2.66. If I put A equals to 2.66, you will see this equation will not be satisfied. That means only this is your possible answer. So option B will be correct. You can verify it. So let's solve, just give me 1 second, right? Yeah, let's solve this question uh, here. So let's try to solve this question, right? Consider a negative feedback system. G of s is given, controller gain is given, the root locus of G of s into C of s is presented in the figure below. The gain of C of j omega at omega equals to 1 is 2. The value of kd would be what? What is the value of kd? Correct? What is the value of kd? Right? Okay. So first thing is, right, I observed that what is the root locus? It is g of s into c of s. So what is g of s into c of s? G of s into c of s. It would be kp into s into ki kd into s square s minus 2 into, so s minus 2 I can directly write here, right? S minus 2 into s minus 3, correct? So that's all basically, right? So this is my g of s into c of s, correct? So this part is done basically. Okay, so yeah, now what I can do is I can see that I am observing a 0 here, but actually I should observe two zeros, but there is only a single 0. How is that possible? So what is happening, maybe the other 0 is on the left hand side, it is not shown in the rule locus, maybe. Okay, but if I'm observing a 0 at s equal to minus 1, what does it mean? If I'm observing a 0 at s equal to minus 1, that basically means if I put s equal to minus 1, that this will be 0, right? If I put s equal to minus 1, this will be 0, right? That is what 0 means. So I will put s equal to minus 1. If I put s equal to minus 1, this will be kp into minus 1 plus ki plus kd square into minus 1 whole square, that is kd only, divided by minus 1 into minus 1 minus 2 into minus 1 minus 3. This has to be 0, right? So it does not matter whatever is my denominator, I'm interested in the numerator. So the numerator is basically ki plus kd, that is equals to my kp. That is one relation. Great, I got one relation. Okay, I got one relation. Anything else can I figure out? So one more thing is there, my crossover points, right? This is my crossover point, this is my crossover point. So crossover point is basically wherever the, at whatever frequency I cross. So what is the imaginary part of my pole? Minus 4, right? So basically at omega equals to 4, I will get a crossover point. Okay, but solving that would be very difficult. Let me try to figure out something else. Some other information is also given, right? This, the gain of c of j omega equals to 2 at omega equals to 1. So what is the magnitude of c of j omega, right? If I put s equals to j omega, right? So this would be kp plus minus j ki upon omega plus j kd into omega, right? So magnitude, right? Let me write this somewhere in the bottom. Magnitude function would be magnitude of this value, right? Magnitude of this value, that will be equals to, this part is real, kp square whole under root plus kd minus ki, so kd upon kd into omega minus ki divided by omega whole square. That's all. Okay, that's all basically. Now this is given to me, the magnitude is given to me as 2, correct? Magnitude is given to me as 2. I'm just thinking of something. If I put j omega equals to 2 here, that should not be the case actually. I don't know if it is talking about the gain or exact value of j omega, I don't know. Okay, at omega equals to 1. So gain of this at omega equals to 1 is 2, right? Okay, what will I do with that information? That is what I'm thinking. Gain of this at omega equals to 1, at omega equals to 1, it is 2. Okay, just thinking something. 2, it is 2. Okay. So kp is actually ki plus kd, right? Kp is ki plus kd, that's all. Kp is ki plus kd. Or one thing is a possibility, one more thing is a possibility, that maybe because I'm not able to observe any 0, right? I believe that KD is 0. But okay, they have asked KD only, right? KD is not 0, but no, that is not a possibility. Actually, this should be properly mentioned, right? I don't think KD will be 0, otherwise they will not ask for KD. They should have mentioned where is the other 0 located. Okay, KD is not 0, right? Otherwise this root locus will not go there, right? There has to be actually there needs to be how many branches there shall be? There shall be 3 branches, correct? So one branch is going here, other branch is going here, right? What is the third branch? That is interesting. So these 2 branches start from here. Okay, one branch stops here only. Okay, it's very interesting. Okay. What is happening? If you see, 2 branches are starting, they're entering here, and they are actually both the branches, right, are going here only. It seems so, because in this open loop 0, 2 branches are incoming. That means this is a repeated 0. S equal to -1 is a repeated 0, and this is an asymptote. That's interesting. Okay, that is interesting. So this is a repeated 0, right? If it is a repeated 0, then this, right, can be written as a factor of s minus s plus 1 into s plus 1, basically, right? This can be written like this: s plus 1 whole square. Okay, s plus 1 whole square. Can I write it as s plus 1 whole square? Can I write it? Will that be valid? Just thinking about that. So actually, okay, first thing is I have repeated poles, right? If I have repeated poles, that means your b square minus 4ac will be 0, right? Discriminant will be 0. That means b square, that is kp square, minus 4ac, that is 4 into a into c. So kp into ki will be equals to 0, right? That is the first thing, because here I see 2 branches are incoming here, right? 2 branches. Okay, so okay, so b square minus 4ac will be 0. Will that help me? That is what I'm okay. I got the value of kp square. Kp square is 4 kd into ki. That's all. I got this value. Kp square I got. Kp square is 4 kd into ki, right? So yeah, that can be helpful actually. So if I square this equation, right? If I square this equation, so this would be ki square plus kd square plus 2 kd ki, that is equals to kp square, and that is equals to kp square is simply equals to 4 kd ki. So this will be equals to 4 kd ki. I don't know whether I'm doing this correctly or not. So these kind of questions you don't solve at the starting, this you solve at the end, right? So this will be ki square. Okay, so kp square is this. So actually this will be ki minus kd, so whole square, right? Because this will go on this side, ki minus kd whole square. Okay, is equals to 0. That means ki is equals to kd. This is the first information that I got. Ki is equals to kd. Great information, right? Great information. Okay, very good information. And of course, if ki is equals to kd, that means kp square is equals to 4 kd ki, and ki is kd, so it will be 4 kd square. So your kp would be, of course, kp has to be positive. Kp would be equals to 2 kd. That's all. Kp would be equals to 2 kd, right? So kp is 2 kd, ki is kd. So now it is very simple for me to solve, right? So I will square on both sides here. Everything is equal. So kp is 2 kd, right? Kp is 2 kd. So I will replace this with 2 kd. That will be 4 kd whole square plus kd is kd only, and omega is 2. Don't forget omega. Sorry, not omega is not 2. Omega is 1, right? Omega is 1. So omega is 1. So this will be also minus kd only. So this will be 0 only, right? And I'm squaring both sides. So this will be 4. So from this it becomes very beautiful, right? Does it become very beautiful? Let me think. Does it become very beautiful? Okay, no, I've already squared it, right? So kp is 2 kd, right? So if I square it, it will be 4 kd whole square. 4 kd square, that is equals to 4. So kd square equals to 1. So kd actually comes out to be 1. Right? Very beautiful question. So answer is this, right? KD is 1. Actually, initially I was not able to figure out like where is the other 0? Where is the other 0? Now I am able to figure out there is one asymptote and there are repeated zeros, right? It is not shown. Actually, they should have shown, but that's the thing that they do, because there are two branches that is incoming in this 0. So it cannot happen that only in a single 0 two branches are incoming, right? Because there will be three branches. One branch is going here, so two branches are coming in here, right? So of course, uh, sorry, I'm sorry. So what is happening is there are total three branches. One is this branch, and the other two branches are this, right? So of course, from all the poles, three branches will leave. Three poles, three branches. So one branch is entering to this 0 on this side, and one of the branch is going on this asymptote, right? So the other branch has to come here, right? Because I see the arrow, So in this 0, there are two arrows incoming towards it. That means two branches are incoming towards it, correct? So that means it is a repeated 0. So that's the beauty. This question is actually pretty beautiful question. Okay, so yeah, answer would be KD equals to 1. I was not able to figure out at the starting. That's why you should solve all these kind of questions at the end, whenever your mind and brain is free. Let's solve the next question, right? This is the next question. A satellite altitude control system is shown below. Okay, I don't care. Function g of s is 1 by s square cascaded with the compensator where k and alpha are the positive real constant. In order for the closed loop system to have poles at -1 plus minus j root 3, right? What shall be the value of alpha? So I want my closed loop poles to be at this location. Okay, I want my closed loop poles to be at this location. So yeah, for that I have to put this pole and then calculate the value of alpha, right? So what is the transfer function? What is the transfer function? Transfer function would be equals to g upon OLTF upon 1 plus OLTF. I will write this directly, right? I will write this directly. That would be equals to just give me 1 second. S square, this will be 1 plus S square, sorry, S plus 4 plus K into S plus alpha. That's all. That's all right. S square is also there, right? Don't forget S square is, oh, sorry, S plus 4 into S square also will be there. That's why you should not do shortcut, but I prefer shortcut. S square. Okay, so this would be a third order system, right? So K into S plus alpha upon S cube plus 4S square plus KS plus alpha, right? So now they're telling me that S equal to minus like -1 plus minus j root 3 is a pole location, right? It is a pole location. If it is a pole location, I will put the value of S right here, and of course, what is my characteristics equation? It is S cube plus 4S square plus KS plus alpha equal to 0, right? So of course, I will put the value of S here, right? So S equal to -1 plus minus j root 3, correct? So this will be -1 plus minus, okay, just I will first of all choose the positive root, j root 3 whole cube plus, okay, this will be very difficult, -1 plus j root 3. I feel, is there any easier way? So it lies in the root locus, right? -1 plus j. So here the system is overdamped. Is it overdamped though? No, it is not. It is like underdamped, right? Okay, so can I use any? No, this is not a second order system, right? It's a third order system, so it's not that simple actually. Cannot simply solve it, right? So we have to solve it using okay. So okay, what do I see that okay, so close to poles are located here. So I have two poles, right? Two poles are located here. So basically this will have, this is a third order system. So out of which two poles are located at this point, right? So of course I can break this, actually, okay, I can do some simplification. So two poles I know location. So what will be the other pole? Other pole has to be a real part, right? It cannot be imaginary pole. If I know that it is a third order system and two poles are imaginary, that means the other pole has to lie on the real axis. It cannot be here, right? Because we know if I have a pole here, I must have a pole here, because if I have a complex pole, they will always lie in pairs, complex conjugate pairs, right? So that is not possible. So I have to, like, one pole must lie here, here, I don't care, but anywhere it must lie on the real axis. So what I can do, I can break this third order system into a second order system, right? Sp into s square plus 2 zeta omega n s, okay, which will be very helpful to me actually. So out of this, right, what is my zeta omega n? So the real part, this is a, like a what do you call, underdamped system, right? Complex conjugate meaning underdamped system, second order. So in this, what is the real part? Real part is -1. That means that uh, zeta omega, this is the minus zeta, if you remember the pole location, right? It was minus zeta omega n plus j omega d. That's what the pole locations of a underdamped system was. So all these things are important. I have told you all these things are important. So minus zeta omega n is this. So how can I form the overall system? It will be 2 zeta omega n, right? 2 into zeta omega n. Zeta omega n is 1, so it will be 2 into s plus omega n whole square. What is omega n? Okay, so omega d is this, right? So what is omega n? So zeta omega n is this, right? So okay, uh, so if I take the ratio, so what is my cos theta? Basically cos theta would be the ratio of the, so here, right, this is -1 and this part is √3, correct? This distance is √3, right? So this is the angle of inclination. So height is √3 and the base is 1, correct? So cos of theta, that is my zeta, will be equals to base upon the hypotenuse, that is actually equals to 2, right? B square a square plus b square 3 under root, yeah, it is equals to 2, that is correct. So cos theta is actually 2, right? Zeta is half, so my omega n would be 2, okay, omega n is 2, so this will be omega n whole square, that is 4. If you are not able to figure out this, right, simply what you do, you can break down this into that, you, I hope that you have understood that you can break it down into a real part and sum of two complex parts. Okay, now what you do, I know that my pole locations are this, so basically this will be my factor. So s of minus pole 1 into s of minus pole 2. So pole 1 is located at -1 minus j √3 and pole 2 is located at -1 minus j √3. So s plus pole 1, like s minus pole 1 into s minus pole 2, right? So if you multiply this, ultimately you will get back to this equation. Okay, so I can show you basically. So s minus of -1 plus j √3 into s minus of -1 minus j √3. If you multiply these two equations, correct, ultimately, right, if you multiply these two, you will get back to this. Just to avoid calculation, I was doing all this. Okay, circus, don't worry if you are not able to figure out. Okay, and of course, if you don't even want to, okay, if you don't even want to do anything, just simply put the value of the pole location in this equation, right, and you will equate the imaginary and the real parts to be 0, and from that you can find out the condition for k and alpha. That also you can do, but of course we are smart guys, so we will simplify our things, right? So now if I replace this, right, now if I expand this, this will be s cube plus 2 s square plus 4s plus s square p plus 2sp plus 4p, right? So this will be s cube plus 2 plus p s square. So from this actually I can directly say what is the value of p, right? Very interesting. The value of p would be 2, because 2 plus p has to be, I have to equate the coefficients, right? So this equation and this equation both are same. So 2 plus p would be 2, 4, sorry. So p would be simply equals to 2. Now next, right, this will be plus 4 2p, 4 plus 2p into s plus 4p equal to 0. Okay, so yeah, so again I already know, right? So they have asked me alpha is equal to simply 4p, so it will be 8, right? Am I correct? Sorry, alpha equals to 4p. Yes, alpha is equals to 4p. Am I correct? It is 4p. Yes, and uh p is half, right? Am I correct? Okay. Hold on a second. Hold on a second. Hold on. Okay, this is k times alpha. Okay, k times alpha. That is what I was thinking, because my answer is not matching. Okay, I have written the answer here. Answer is not matching. It is k times alpha, right? Okay, hold on. K times alpha hai bhaiya. K times alpha hai. So this is actually k times alpha. So k times alpha is 8, and I don't know what is k. K I can find out from this, right? Comparing this and this, the coefficient of s. So that is equals to k equals to 4 plus 2p, and p is supposed to be 2, right? So it will be k is equals to 8. So 8 into alpha is equals to 8. So alpha will be 1. Now it is fine. Alpha is 1. So that is your answer. So this question is actually again lengthy. Controller questions are again lengthy. Okay, that is only problem, because they integrate other topics. So again, right, if you're uncomfortable with this method, right, this is the method 2 actually. If you are not comfortable, what you do? Method 1, just put the value of s equals to -1, any root, put any root here, right? Any root, s equals to -1 plus j root 3, put it here. So basically this will be a complex number. You will get a complex number, and the right hand side is 0. So the imaginary part is also 0 and the real part is also 0. So you'll equate both of them to be 0, and you will find out the conditions for alpha and k, and from that you can solve and you will get the same answer. Okay, that is the homework for you, right? If you're not understanding any of this, there is always a backup option. Great. Let's move on to the next question. So, okay, so this is actually 11th question, right? This was the 10th question. Yeah, this is the 12th question. I think we're almost done, but I think recently they gave a lot of questions from compensators. Actually, it is an important topic, even though people think that this is not an important topic, right? This is an important topic. Okay, so let's solve this. G of s is equals to 1 by 10 s square. Okay, transfer function of a second order system. A controller M of s is connected to the system G of s in the configuration shown below. Okay, great. G of s is 1 by 10 square. Great. There exists no controller of the form ms ki by s, basically integral controller, such that the closed loop system is stable. Okay, and they're then discussing this controller where kp and kd are positive, such that the closed loop system is stable. So basically for a integral controller, this system can never be stable, and for a PD controller also they are telling me this system cannot never be stable. So let me first of all simply find out the CLTF, right? What will be CLTF for in the case 1? In the case 1, right? In the case 1, what is CLTF? So that would be equals to Ki by S into your G of S, that is 10 by 1 by 10 S square, upon 1 plus g of s into m of s, right? So this ki upon, I feel this system is never stable. This is never stable actually. So what will happen here, right? So the characteristics equation, right? If I write the characteristics equation, this will be actually 1 plus g of s, right? Sorry, 1 plus, sorry, this is not the characteristic, this is just directly the transfer function, right? So this will be ki upon 10 s cube plus ki. Okay, so of course I see, right, this system is not never stable. Whatever you do, right, this is not a Hurwitz polynomial, right? Hurwitz polynomial, because the coefficients of s square and s raised to power 1 are missing, right? This is not a Hurwitz polynomial, so this system will be never stable, right? So this statement is actually correct. There exists no controller in the form of this such that the closed loop system is stable. This statement is true. This statement is true actually. What about the second statement? If I had a PD controller, right? If I had a PD controller, everything will be same. Just that what will happen, instead of ki by s, right, it will be a PD controller. So this will be kd into s plus, sorry, yeah, kd into s plus kp. That's all, right? Yes, this also will be this. But this again here, right, again the coefficient of s square seems to be okay. Let me solve this first. Let me not comment. Okay, no, here it is fine. Here it is fine actually. Here it is fine. Okay, because all the coefficients are available. So I see this will be the closed loop transfer function. This would be equals to kd into s plus kp divided by 1 plus, sorry, 10 into s square plus kd into s plus kp. Yeah, this system is stable if all the coefficients are positive. This system will be always stable, right? Always stable. Okay, this will be always stable. So yeah, this statement is actually correct. This statement is not incorrect. This statement is sorry, what they're telling me, that such that the closed system is stable, there exists at least one controller. Yeah, that is all, that is correct, right? There exists at least one controller which can make this stable. Yes, there are not only one, at least not one. If my coefficients kd and kp are positive, we know a second order equation, right? Just the coefficients needs to be positive, that's all. Basically they need to be of same sign for it to be a Hurwitz polynomial. So this is true, at least there is one form that can make the system stable. So this statement is also true. So both my statements are true, that is present in option D. So option D would be correct. Let's solve the next question. A controller d of s is given, okay, and of the form of this, right, is to be designed for the plant this as shown in the figure. The value of the kd that yields a phase margin of this. So basically they are asking me, if I have a controller, what will be the value of the phase margin, right? So pretty simple. If the phase margin is 45, then what will be the value of kd basically. So if I am connecting, what is the modified OLTF, my d of s, right, it will be 1 plus kd into s into 1000 under root 2 upon s plus 10 whole square. Okay, so now of course the angle will change, right? Angle will change, correct? What will happen to the angle? So angle of my OLTF, right, angle of OLTF would be tan inverse s equal to g omega. So it will be kd omega upon 1 minus 90. Of course this will provide 90 degree minus 90, and this will provide, here remember I have two poles, right? So minus 2 into tan inverse omega by 10. That's all. As I have two poles, it will be minus of 2 into tan inverse omega by 10. That's all. So Yeah. So yeah, what is the phase margin formula? Phase margin is 180 plus the angle of OLTF at the particular gain crossover frequency, that is 10, right? So I'll put 180 plus this formula, 180 plus this, right? Angle at omega equals to 10, right? So this will be 10 kd minus 90 minus 2 into tan inverse 10. Tan inverse 10 would be, sorry, tan inverse 1, that is 45, right? That is equals to, phase margin is given, right? Phase margin is 135, I guess. It is 1, sorry, not 135, 45 degrees. So this, right, is 90, this is also 90, so automatically this will be gone. So tan inverse 10 kd is equals to 45, that means it has to be tan inverse 1. That means 10 into kd has to be 1. So kd has to be 0.1, correct? Kd has to be 0.1, and they have asked to calculate in 1 decimal places. So 0.1 will be your answer for the question. Like there are a lot of questions, okay, lot of questions. Okay, so this is the highest, I guess, because it involves all the different topics. So the plant in the feedback is shown, transfer function is shown, controller, the type of the controller C of S that cannot stabilize the system, right? What kind of controller here cannot stabilize the system? So is an R. So it is a MSQ type question. So if I write the characteristics equation, it will be 1 plus g of s into c of s equal to 0. So this would be equals to 1 plus, instead of g of s it is p of s currently. So this would be equals to 1 plus s square minus b square into c of s, right? C of s is yeah, C of s, let's assume that it is a proportional controller. If it's a proportional controller, Kp equal to 0, so there is a problem here, right? There is a problem. So this will be s square minus b square plus a into Kp equal to 0. So what will happen is, you see that the coefficient of s raised to power 1 is missing. So it cannot stabilize the system. You can solve it as well, right? You will get two roots, s equal to plus minus something, right? So one root will be positive, other root will be negative, right? So positive root, of course, pole lying on the right hand side, so it cannot stabilize the system. So this is actually the correct answer, one of the correct answer. What about the integral control? Integral control as well, I believe it will not be able to stabilize it. Let me check. So if it's integral control, right, so this will be 1 plus, I will copy this, into ki by s equal to 0. Okay, so this would be equals to yeah, s cube minus sb square plus aki equal to 0. So of course again s raised to power, right, hold on a second, sb square, yeah, s raised to power 2, the coefficient of s raised to power 2 is missing, right? So again this system is not stable, so it cannot, integral controller cannot stabilize it. So AB is correct. What about proportional integral controller? If it is proportional integral controller, if it is proportional integral controller, this will be Kp into Ki by S, right? So yeah, will this be a problem? I feel, let's see, this will be again a problem, right? Because this, right, will be what, this can be written as Ki plus S into Kp. Okay, this may not be, no, this is a problem, this is a problem, again this is a problem, because what will happen, this will be S cube uh, minus S into B square plus S into A into Kp, then plus A into here. Okay, that is equals to 0, right? So again I see that s square, the coefficient of s square is missing, right? So if the coefficient of s square is missing, so of course not valid, it is not valid, right? S square is missing, it is not valid. So of course, yeah, again it cannot make the system stable. So option C is again correct. What about proportional derivative? So this I feel finally will be able to make it stable, or I don't know. I don't know. So let us see. So here is the g of s into kp equal to 0. So this will be s square minus b square plus a. Okay, this will make it stable. Yes, this will make it stable because all the coefficients are now available, right? Coefficient of s is available, coefficient of s raised to power 0 is also available. So this will actually make it stable because all the coefficients are available. Of course, there is a thing that uh, all these values must be positive. Basically, coefficients of s must be positive, that is there, but still I can at least stabilize it, right? So a proportional derivative controller can actually stabilize it. So my correct answer would be a, b, c. That's all. Let's solve the next question. Correct, 15, I think. Yeah, I think we have one more question after this. That's all. And then we are done. I know I've taken too much time in controllers, but there were more questions, so they're actually asking you questions. And actually from iron, right, there are a lot of questions. That is the thing. From iron there are a lot of questions in controllers. Okay, this question is again is pretty interesting. So the figure shows a closed loop system with planned transfer function as 1 by s square. Okay, and the lead compensator is shown. The compensator is designed to place the dominant pole at s equal to 1.5, this value, right? From which of the following options, choose the phase lead that the compensator needs to contribute. Okay, what is the phase lead that the compensator needs to provide if I want to place my closed loop, if I want to place the dominant closed loop poles at this location? Okay, great. So it is a it has to be a lead compensator, right? If they're talking about phase lead, it is providing phase lead, so it will be of course a lead compensator, right? So I will have a 1 s plus z and s plus p, right? And of course z will be much nearer to the origin. Okay, z will be much nearer to the origin, right? Okay. Okay. This question is again very lengthy, right? Okay, let me think. Okay. Hmm. Can I do something? What is the phase lead provided by the compensator if I want to so basically what are they telling me, that the compensator is designed to place the dominant closed loop poles in this location, right? So closed loop poles are in this location. Okay, what is the phase lead required? Okay, what is the phase lead that the compensator needs to provide? Okay, this question is actually pretty interesting, right? So basically, right, what is my characteristics equation? It is 1 plus cs into g of s equal to 0, right? And the roots of the characteristics equation, right, will satisfy this equation, right? That is why it is called characteristics equation. So they have given me the roots, right? So the poles, dominant poles lie here, right? Correct. So c of s into g of s equals to -1. So what is the angle if I take the angle on both sides, right? So if there are two complex numbers that are multiplied, angles will be added. So angle of c of s plus angle of g of s would be equals to angle of -1. What is angle of -1? It is -180. They need to satisfy. So from here actually I can directly calculate how much is the compensator, how much phase lead is the compensator providing, that is -180 minus angle of g of s. Okay, so what is the angle of g of s at this particular location, at this pole location, because it is satisfying the equation, right? So angle of g of s at this location, what will be it? So if I replace s with s with the value, right, that is minus 1.5 plus j 27 by 2, right, whole square. So what is the angle provided? Angle provided here, right, it will be, remember it is in the denominator, right? So negative sign will be there into 2 because there are two poles. Then remember this part is, okay, there are two options here. Actually, yeah, there are two options. Either you can choose this, choose the imaginary part to be positive, or you can choose it to be negative. There are two options actually. So if I choose it to be positive, right, so actually this, the other part, if you choose it to be negative, that won't be even present in the options. Like the answer that you will get, that is, that will not present in the, that will be not, that option will be not, that option will not be present. Okay, whatever answer you will calculate, that option, that answer will not be present in the options. Okay, sorry, this is a long session, I'm sorry. Okay, minus 1.5 plus root 27, right? Okay, minus 2 into, yeah, so this, right, where is it lying? So it is at negative side and positive, so it is here, somewhere here, right? It is somewhere here. Okay, so what is the angle here? So this is my theta, right? So it will be 180 minus theta. So 180 minus of theta, theta is tan inverse. Okay, let me write it 180 minus theta only for now. Okay, 180 minus theta. I hope that you are not angry at me. So like this is the location of the pole, right? So the angle will be 180 minus theta. So all these things has been taught to you in basics in mathematics. Okay, so if I write minus 2 into this, right, so this, it is actually minus 360 plus 2 theta, and adding 360 or subtracting 360 does not make any difference. So actually it will be 2 theta. So this g of s actually is 2 into theta, minus 180 minus 2 into theta. Okay, minus 2 into theta, and theta is what? Now I can write the value of theta. Theta would be tan inverse the imaginary upon the real part. So under root 27 by 2 into 1.5, right? Correct. So this would be equals to 3. So under root 27 by 3, that is, okay, that is very weird number. Let me, okay, so under root 27, under root 27 is 9 actually, sorry. No, it is not 9. Okay, what am I talking about? It is not 9. Upon 3 tan inverse, yeah, it is under root 3 actually, yeah. It is 60 minus, so it is minus 60 into 2 minus 120. So it is actually minus 300, right? So again, I have to decode positive results. So I will add 360, that will give me 60 degrees. Okay, so 60 will be correct actually, right? You can verify if you put here negative value, right? I guess you will directly get the plus 60. I'm assuming that if you put here negative value, I'm assuming you will directly get at 60. So it won't matter actually whether you choose positive or negative. Ultimately you will get the same value of the compensator. Okay, so 60 would be your answer for the question. Okay, pretty simple, but understanding this part is the most important thing, right? Equating the angle equation, you can just remember the formulas, everything you can remember, right? You will never be able to solve this question if you remember all the formulas. You will never be able to solve this question if you don't understand this part, because these are my poles, so it has to satisfy my characteristics equation. So the angle must be minus 180, right? Magnitude of this transfer function also must be 1, that is magnitude of this. So this is a very good question. Which of the following statements is correct for any second order linear PID controller? Integral component decreases the residual steady state error. It is true, right? It is true. Integral component does reduce the steady state error. We discussed, right? Integral component actually improves the steady state performance. This is true. Integral component integrates the output signal. No. It integrates the error signal. Integral component increases the steady state error. No, it not does not increases it. It reduces it, right? Integral component integrates the input signal. No, it integrates the error signal. So this is the option A is the correct answer for this question. And I guess with that we are finally done. Okay, we are finally done with the whole control system. If you have enjoyed it, make sure to hit the like button, hype the video, whatever you want to do you can do. Okay, and I hope you have enjoyed control system. Like in around, I guess this will be 5 12 and then around 30 hours, 25 to 30 hours, we have covered the whole control system, of course in a fast manner. Of course I will not be able to cover every single thing, because I thought of making this like a crash course only. So whoever has studied control previously, they will gain some knowledge from this, and it will work as a good revision for you. So yeah, if you enjoyed this video, like the video, hype the video, comment on below. It will obviously help us to reach more people. And with that, I will meet you in the next lecture. Until then, happy learning.